This morning's session, we've got 4 speakers for the first hour. We'll be talking about forests, fire, and of course, snow. And I'm really excited about this morning. There's 4 really good talkers. So let's start with Graham Sexstone from USGS, and he's going to be talking about remote sensing and distributed snow models.
Yeah, thanks for the opportunity to talk this morning. My name is Graham Sexstone. I'm a research hydrologist with USGS, and I'm going to present some work that was part of a Bureau of Reclamation Science and Technology project, and also supported by their snow activity program, in addition to some support from Northern Water as well as USGS. So I want to acknowledge my co-authors, Claudia Leon Salazar with Reclamation, Emily Carbone with Northern Water, and then Dave Selkowitz, Garrett Akey, and Theo Barnhart, who are all with the USGS. Hopefully you guys were able to catch Emily Carbone's presentation yesterday. She gave a great overview of the Colorado Big Thompson project, and this work is really focused in that domain. And the motivation here is really that, our current reservoir inflow forecast methods in this area, particularly in high elevation basins, are often, reliant on snow water equivalent data, historically from snow courses, snow tell stations, and the SNODAS product. And really kind of the late season snow conditions, particularly above tree line, are often underestimated by these SWE data sets. The figure on the top right shows in blue and orange snow tell stations in the Big Thompson domain. And then in green is the SNODAS, snow water equivalent, for this past winter, and highlighting kind of the meltout dates of those snow data sets. And then if we look on the bottom right, that's the hydrograph for the Big Thompson Basin. And you can see past June 24th, we have, quite a bit of stream flow still, really kind of in that receding limb of the hydrograph. And that's kind of the challenge of forecasting often, is that late season flow. On the bottom of the screen, you see the SNODAS conditions from June 24th, completely melted out essentially. But then if we look at some, remote sensing data from Landsat and Sentinel, we see we still have quite a bit of snow coverage in these high elevation alpine areas. So kind of the objectives of the project is look at ways to potentially improve SWE estimations in these alpine areas in late spring and early summer, to hopefully help inform the Big Thompson and Three Lakes stream flow forecasting models that are currently used. For this approach, we've utilized a physically based snow model, as well as kind of incorporated some high resolution satellite remote sensing data to come up with improved SWE estimations. So my colleague Dave Selkowitz is really leading the satellite remote sensing component of the project, and the data sets we're really relying on here are Landsat satellite snow cover area products, which is at a 30-meter spatial resolution, as well as Sentinel-2 snow cover area, which is even finer spatial resolution. And when we can combine these satellite groupings, we can kind of reduce the return interval of satellite observations to around 3 to 5 days. And that's compared to historically, if we used Landsat alone, we get an 8 to 16 day repeat. There's an existing product developed by NASA called the Harmonized Landsat Sentinel product that's provides essentially this harmonized surface reflectance data. And so Dave's been developing this machine learning approach to try to produce near real-time snow cover area from Landsat and Sentinel-2 using this harmonized product. And really it's trying, the machine learning is trying to approximate the spectral and mixing approach that's currently used in the USGS Landsat snow cover area product. In addition to these kind of real-time data sets, we're relying a lot on historic Landsat imagery for this project, and more specifically, the mean annual snow cover persistence. So, Landsat data throughout history, it's hard to come up with annual data sets for snow persistence, because we have this sporadic availability of cloud-free observations, and kind of coarse repeat imagery from Landsat. But when we look at the entire historic record, we can come up with some pretty interesting patterns of mean annual snow persistence. So kind of this more long-term metric can really highlight some important spatial patterns in snow. And so we're utilizing this in our modeling efforts in a model calibration. So the project, we're really focused on, developing this physically based snow modeling approach. We're using, a spatially distributed process-based model called Snow Model. And that model is really able to simulate important snow processes at relevant scales for varying environments. Particularly important in this application is trying to represent processes that are important in alpine environments, high elevations such as wind redistribution of snow. Snow model actually represents, blowing snow redistribution from grid to grid in its model representation. So this is a map of our model domain. It's about a 78 kilometer by 54 kilometer area, essentially encompassing much of Rocky Mountain National Park. So we're west of Denver, northwest of Denver. We're running the model on a grid cell size of 30 meters, and we've kind of developed these historic runs from the year 2000 through 2020, in addition to kind of this capability to run the model in real time. There's a number of SNOTEL stations in the domain, and we're using those primarily in a data assimilation framework. And then one of the unique things we've developed as a part of this project is we've actually tried to, calibrate this snow model. And I'd say historically in our snow model applications, it's not really a model. We've focused a lot on model calibration. It's not a highly calibrated model. But we've done some work using our USGS supercomputing system to try to develop this Latin hypercube calibration approach, really to focus the calibration on these satellite remote sensing data sets. So trying to calibrate the model spatially to better match these patterns of annual snow persistence, as well as temporally to look at kind of domain-wide MODIS snow cover area time series. And really kind of in that calibration approach, we've calibrated parameters that are focused on controlling snow density evolution, wind redistribution of snow, and snow albedo. And then kind of the last step we applied in this project is we sort of further optimized the calibration to this Landsat mean annual snow persistence by applying a bias correction. Essentially, we're looking at the difference in that long-term mean snow persistence of our simulation compared to the Landsat snow persistence, and then we're applying a precipitation correction to future simulations to try to better match those patterns. And so this is accounting for, essentially uncertainties in the model associated with, precipitation bias, but also other biases such as wind redistribution, where, the model's not able to really produce high enough winds in the alpine areas to blow enough snow in some cases. So we ended up with kind of this range of model simulations, 4 different model runs where we have kind of our default version with and without our SNOTEL assimilation component. And then we have our calibrated version. And then finally, this calibrated version with this precipitation correction factor. So this figure shows some of the model traces over 5 different water years. There's a lot going on this graph. I'm not going to go into too much detail here. I did want to just point out we have snow dash shown on this plot in the dotted black line, and then our calibrated model runs are shown in kind of the green colors. And if you look at the highest elevations, you can see that the snow meltout timing is quite a bit later in some of these snow model simulations compared to snow dashes, which was kind of what we were expecting as a part of this project. So I want to jump into a little of the model evaluation, and for that component of this project, we've really relied on ASO data. So big shout out there to all the efforts of ASO and CHASM. I think using ASO data for kind of in an evaluation context is hugely important from a science standpoint. Historically, we haven't had kind of data sets like these to really dig into evaluating science that's focused on simulating or estimating spatially distributed snow properties. So I think there's just so much utility there, and that's really kind of what we focused on because we have these data sets available, which is great. So this is the Windy Gap domain from 2022. You can see these four top panels are the snow model simulations of kind of the default with assimilation, our calibrated version, and then finally the calibrated version with the precipitation correction factor. And you can see ASO here on the top right, and then these bottom panels show sort of the bias compared to ASO. In general, we saw pretty low bias for that default version, and then the assimilation ended up kind of rocketing it to a much higher bias. But then our calibration approaches tended to kind of hone in better towards that ASO SWE product here. And our final version with that precipitation correction showed sort of the best performance overall. These are some statistics based on the 2 flights from last winter in the Windy Gap domain, showing kind of the mean ASO recorded snow water equivalent in the gray bars within the different model versions, kind of as we step through this process. Generally, our final version had the best performance. When we look at kind of the grid by grid RMSE and bias, it tended to improve as we sort of step through this model calibration process. And we can kind of zoom in a little bit here, looking at, this is the Big Thompson domain. So it's about 138 square mile watershed here. And this is a comparison of our simulated snow model SWE compared to ASO, what they measured this winter. So this is, May 21st, 2023. This is kind of our final calibrated version. And so one thing that pops out here is the spatial patterns in snow we're able to simulate really closely match what ASO is measuring, which we were just super excited about. I think that's a huge challenge to try to represent some of these complex patterns in the Alpine. So we just seeing this comparison was really encouraging to us. We looked at kind of the comparison by elevation shown on the bottom here. So we look at mean SWE on the left, broken out by elevation bins as well as volumetric SWE. On the right, snow model is shown in the red color, ASO is shown in green. And again, we see some really nice kind of comparisons in terms of just where this snow is distributed across space. Certainly there are biases here, and especially at kind of the highest elevations, you see ASO is measuring quite a bit more snow in these snow drifts. You can look at the brightness of the yellows here are generally brighter than what we're showing in this kind of snow model simulation. Similarly, the lowest elevations, we see ASO is kind of recording more SWE compared to our simulation. You can just see that the snow line is quite a bit higher in our simulation as compared to ASO. So kind of one of our next questions is, can these real-time snow cover area data sets potentially help further improve our estimations? So as a part of this project, we developed this kind of a real-time snow model application. We can really only run using the NLDAS2 forcing we're using. We can really only run it up to sort of a 4-day latency. And the big thing here we're trying to utilize this harmonized Landsat Sentinel snow cover area observations in sort of a post-processing correction format. And so we've essentially binned this domain up by elevation and aspect and watershed zones. And then we're using those bins to help try to correct for remotely sensed observations of snow cover. This is an example of, this past 2023 winter in the Big Thompson domain. This is April 1st. So our snow model simulated snow cover is shown in the top left here. And then the remotely sensed snow cover observed by Landsat Sentinel is shown in the top right. our initial simulation of snow model is shown in the bottom left, and then the updated simulation is shown in the bottom right. This kind of April 1st simulation, we actually did a pretty good job of matching snow cover. It wasn't really a big effect in terms of update from the snow cover area data. You can see our high elevation snow water equivalent estimate was 365 millimeters, and that compared to SNODAS was 396. So pretty comparable there. But if we sort of fast forward to later in the season, this is June 24th, we see our simulated snow cover with snow model was quite a bit less than what's observed by Sentinel still remaining at these high elevation areas. So when we look at kind of that initial simulation, we have 38 millimeters in the highest elevation zone compared to SNODAS, which is 9 millimeters, almost completely melted out. There's a little more there, but then when we applied our update based on the observable snow cover, we were able to bring that up to a 91 millimeter estimation. So that's kind of an example of what we're trying to go, where we're trying to go with this application. And the more we kind of move forward with this and are able to evaluate with more ASO data sets, we're hopeful this product will be really useful for reclamation in Northern. So that's all I had. Thanks very much for the opportunity. I've got my email here, so feel free to reach out. And if there's time, I'm happy to take a question.
Thank you. That was really interesting. I think we have time for one question, and then we'll get Anne going because she has a hard cutoff at 9:45. So, yeah, over here. It was somebody. Let's see. We'll take a question from the room, and then we'll try and answer those during the session.
Okay, thank you. Baxter View here. And I just had a question. Maybe you talked about this, but you could clarify. When you're dealing with verification of a distributed product, then I'm curious about the bias correction and which parameters were those applied to? Was it physically based or physics based? Or is it just kind of a bulk adjustment factor? And was it mean field bias or kind of distributed bias?
Yeah, great question. So we're essentially applying a precipitation field adjustment factor, and we're kind of it's a long-term mean adjustment over those 20 years, but then we apply that every year in future simulations. So it's a grid by grid adjustment, and it's basically a percentage weighting of precipitation. So it's physically based in that sense that it's everything's running through the model, but that that bias field is based on just kind of the difference we've observed of our historic simulations compared to Landsat. There's more that went into it. It's kind of hard to dig in right now, and I'd be happy to kind of follow up with more details.
Great, thank you. Okay, moving on. Next we have Anne Nolin and Ali Fitz talk from the University of Nevada, Reno. And they're going to be talking about snow albedo and post-fire landscapes all the way from California to Alaska.
Okay, let me get going here. All right, there we go. So I've added some co-authors here because, of course, we never do this alone, and there's always more people that we need to recognize. So Ali and I have been working on this for a while, but also with my former student Kelly Gleason and her student Anton Sarunas, and my former student Ariel Koshkin, who's done a really nice review of some of this work. Okay, so let's get going here. Come on. There we go. All right, so the outline of today's talk is really talking about pre-fire effects and post-fire effects and other post-fire effects. But the real focus is, why do we need hyperspectral data? How will hyperspectral data, particularly from Airborne, from ASO, from ASO, how is that really going to benefit us? And the top photo there is showing some of these kind of dead and dying trees that we see throughout a lot of the Sierra. And the bottom photo there is what it often looks like after a fire in the high burn severity zone. I'm going to start off by showing a plot that you might have seen this before. I've shown this at AGU last year. This is the Sierra Nevada ecoregion, and I've mapped out using MODIS trends in the month of September, the greening versus browning for 2000 to 2021. I'm really excited to include everything up to 2023, so I need to update this plot. But areas in brown are showing a negative trend. Areas in green are showing a positive trend. The brown trends, the dark browns are significant. There's very few significant green trends. The red area is the creek fire perimeter, and I'll focus a little bit on that. So what am I actually showing in order to show this greening versus browning? In evergreen forest, vegetation indices like the NDVI and the EVI from MODIS, for instance, don't work very well because they are not pigment-based. Evergreen forests are green all year round. So how do you actually detect changes in photosynthetic activity, changes in moisture stress, or changes in gross primary productivity? And to do this, forest ecologists, remote sensing forest ecologists, have turned to using the ocean bands, which are used for mapping changes in ocean color, because that's pigment-based, and that's a way of looking at ocean productivity. So there's one here called the chlorophyll carotenoid index, which uses band 11, which is a really narrow band, and contrast that with band 1, which would be nice if it were also narrow, but it's not. So we look at these bands in the green and red wavelengths, and you can really see very distinctly a winter pattern versus a summer pattern in this CCI. Now, the hyperspectral version of this, which has been used with AVRIS, and I hope with ASO, perhaps in the future, is called the Photochemical Reflectance Index, or the PRI. And same idea, it's a pigment-based index. And some work by John Gammon and Fred Humerich have shown really, really nicely that the CCI, this MODIS-based chlorophyll carotenoid index, tracks GPP and moisture stress in evergreen forests really well. If you look at the left plot, the red dots there are the CCI, and the black is gross primary productivity from eddy flux towers at the Wind River site over Doug Fir and Hemlock. On the right, it's showing NDVI, and you can see there's very little sensitivity between NDVI and the same gross primary productivity data. So we don't want to use NDVI. We want to use narrow bands, which you can kind of get from the MODIS ocean color bands, although the spatial resolution is not great. You have to sort of downsample it to 500 meters, which is not always ideal, and especially not for mountain regions. So we'd really like to use finer spatial scale and especially hyperspectral data to do this same kind of thing, and to be able to show that same kind of greening and browning trend. So here's another map, and this one is showing MODIS-based trends in snow disappearance date, and this is from the MODIS binary product. Yes, I know I should be using the ModScag product, but we didn't have this available when we were doing this in Google Earth Engine. But what we see are significant trends showing earlier date of snow disappearance throughout the Sierra Nevada. Now, the hypothesis here is that an earlier date of snow disappearance translates into more moisture stress in September. And when we look at that snow disappearance date and the chlorophyll carotenoid index, we see that there's an R-squared of about 0.51. And again, these are both MODIS data here. And which might not be, seem particularly great, but I was pretty enthused about this. And it is saying, hey, you know what? You can use the snow disappearance date from the spring to be able to anticipate what moisture stress might be in these fire vulnerable forests in September, to looking at moisture stress and the down regulation of photosynthesis at the end of the dry season. So here's taking a closer look at the creek fire. That's why I had that red perimeter in there. You can see that forest greening and browning trend is quite significant. You can see the histogram there on the bottom. So most of the send slope trend values are in the browning side of things, and the same thing for earlier snow disappearance date. So this is just focusing in on one fire, and there's a lot more that we can do with this, and a lot more that we will be doing with this. So moving now to what happens after fire. So we have these vulnerable, dry, crispy forests in September, unlike this year, but we do have a lot of fires late summer. And then if those fires are particularly severe or even moderate to high severity, you can end up with all kinds of guck on the snow. So after a severe wildfire, snow's covered with black carbon and burned forest litter, burned woody debris, and all of that absorbs solar energy. And perhaps one of the more important aspects of this is that the forest canopy is burned off. Now, if you had a complete forest canopy with little or no light coming through, it really wouldn't matter what the albedo is underneath. But this combination of much greater incoming solar radiation at the snow surface and that preconditioned snow with that excess black carbon and burned woody debris really amplifies the melt rates. And this process, Kelly Gleason and her students have shown that it can last for up to 15 years. There's sort of a close-up of what it just looks like in your hand. And so here's some measurements that Ali Fitz has made in the Caldor burn area. And just an inset there showing a photo of what this looks like in the moderate to high burn severity area. And what I want to point out is the high burn severity has, in this particular plot, has actually not the greatest decrease in albedo in the visible part of the spectrum, but the intermediate, it's the moderate or moderate to high burn severity that actually has the biggest decrease in albedo. And we think that's because it's still dropping a lot of dead needles. There's so much more stuff on the ground, on the snow, and you can kind of see it in that photo. But we don't really know for sure. So this is ongoing research, and it's part of Ali's thesis work. So our observations are pretty limited. The spatial scale we know is really important, whether you're going from a ground-based field spectrometer like here to a UAS scale, to tower-based or airborne, or hopefully through the SBG satellite-based mission. But hyperspectral data is really key. We need that information in order to be able to discriminate what's going on in these different burn severities. There is this very interesting paradox, and I know this is a bit complicated, I want to point out. And if you look at part C down on the bottom, I was just showing you a photo of black carbon and charred woody debris on the snow surface there on the lower right. In the middle, you might have a low density forest that's not burned, and you would have sort of fairly light forest litter. On the left, you might have heavy forest litter and a high density forest, but again, you'll have a lot less light, so the albedo and the uncertainties associated with that might be somewhat less important. Now, if you're looking at, so that's the snow albedo, but if you're looking at the landscape albedo, if you're looking, for instance, a nadir perspective from the satellite or from aircraft, you have a completely different trend or change in the albedo before and after a fire. Before a fire, you're seeing dark canopy. And so the landscape albedo before a fire is much darker than it is after a fire. So after a fire on the far upper right, you're seeing just a much brighter scene because the snow is exposed after the canopy has been burnt totally or partially burned away. And so the paradox is that the snow albedo is decreased, and so the hydrologic impacts to that snow albedo are responding to that decline in albedo, but the landscape albedo is increased as long as there's snow exposed on the landscape. And so that's this interesting paradox that again lends some uncertainty to the climate impacts as well as the hydrologic impacts. Moving on to the next post-fire impact, we can see that from work that my former student Andy Wilson and I did in lower elevation parts of the seasonal snow zone, where you've got fairly warm snow and where that we know that those forests are really depending on that snowpack. When you have a fire in that area, the revegetation process, that regrowth really depends on the previous winter's snowpack. So some of the questions that remain is, how does post-fire revegetation change with winter snowpacks at different elevations, and what is that regrowth looking like? Right now, we're just using MODIS level EVI, Enhanced Vegetation Index data, but that doesn't, again, necessarily work in places where you might have evergreen type things like kinnikinnick or manzanita or small evergreen trees regrowing. So we'd also perhaps like to get species level revegetation to really understand gross primary productivity across the landscape. And of course, albedo changes across that landscape. And this is, again, where hyperspectral data can really come into play. So we'd really, really like to have hyperspectral data for this. In a new project where we just had our first season of fieldwork in the Alaskan boreal forest, where we're doing some comparisons between boreal forest and the temperate coniferous forest that we have, for instance, in the Sierra Nevada. We are doing hyperspectral mapping of reflectance and albedo in burned and unburned forests and in open areas in order to constrain these really high uncertainties and accuracy requirements needed, for instance, for the SBG mission across different spatial scales, from the ground to tower-based, UAS-based, and airborne, and of course, satellite-based spectral and spatial resolutions and these different disturbance regimes. The challenge is to understand these differences in these different forest types, and I'll show you what that looks like on a map in a second. But ultimately, we'll be using our data to improve SNCR to include not just black carbon, but chunks of burned woody debris and large chunks of forest litter. So outside of the ME radiative transfer modeling part of the outside of ME theory application. And then we'll also be using these new observations to include better parameterizations in snow model for these burned forest effects. So ultimately, we'd like to see these included in land surface models. So you can see in the map on the right, this green area are the boreal forests, and it's the most extensive terrestrial ecosystem. The red star indicates our area where we're making these measurements. You can see the inset there on the map. From the air, you can see the spatial heterogeneity. It's a very different forest structure than we have in the temperate coniferous forest. And on the left, you can see these birch forests, and the lower left is a burned forest. It looks really different from what we see in the Sierra Nevada and elsewhere across the West. It's a big area, and there's lots to cover, so we're really thankful that NASA has been supporting this effort. So just wrapping things up, we really need airborne hyperspectral data. We're really excited about this opportunity through ASO and really look forward to playing with the ASO data that we have in the Sierras in these snowy forested regions. So we want to be able to assess the pre-fire forest condition using these pigment-based indices like the PRI, and compare that with our MODIS-based CCI to better identify these vulnerable areas on a year-by-year basis and much higher spatial resolution as well. And then compare that to the snow disappearance dates, whether we're getting it from models like Snow Model or from LiDAR data or from some sort of MODIS-based snow disappearance date. We want to be able to map the onset and the downregulation of photosynthesis in evergreen forests. And we have some cool ideas about how to start mapping that. We think that these evergreen forests are probably photosynthetically active in the winter in the Sierra Nevada, because when you have midwinter melt events, that means that you've got liquid water available. But we have to separate out the snow signal from this vegetation pigment-based signal. And we can do that, we think, using spectral mixture analysis. So that's one of the things that we're working on right now, to be able to identify photosynthesis even when there's snow and patchy snow on the ground, to be able to better assess post-fire burn severity and looking at how changes in canopy affect both snow albedo and landscape albedo across spatial scales, especially in places where we have really high uncertainty, like the boreal forest. And then, of course, to characterize post-fire regrowth, revegetation processes, and hopefully at the species level, which we can really only do with hyperspectral data. We also like to put in a pitch for those of us who have spectrometers. We'd be thrilled to use our ground-based measurements and our students and colleagues to provide valuable CalVal for ASO hyperspectral data. So don't hesitate to ask us to pitch in. We're always glad to help. So thank you to everybody. And I might have time for, let me see. Yep, I have time for questions. Thanks so much.
Thanks, Anne. That was really great. Tom has a burning question.
So to speak.
Hi, Tom.
Hi, Anne. Thanks for doing that. And wow, you cranked through that.
I did.
Pretty well. Yeah, I looked down and thought, oh, that's perfect timing. Hey, thanks for the offer on the field spectrometer measurements. That'll be great. And
yes,
our new field spectrometer is coming later. Well, no, I guess tomorrow. And so we likewise will be happy to send you our field measurements. So we don't put on the web the spectrometer measurements, but we will be happy to make those available to you. You know, starting with the radiances, if you want to work from that. But we're also using AtCore 4 with the measured topography, and with that topographic correction to the
for the snow topography.
Yeah.
Oh,
So
that's perfect. That's great.
Yeah. So let's talk about that. But I know you want to see those, and we'd be happy for you to have those.
Yeah.
Going.
Well, one thing that's really important and that Ali is doing is we have a drone-based set of pyranometers here that will be flying an up and a down later this year, and we would love to coordinate with you so that we could have drone-based measurements over the Caldor fire.
Oh, that'll be great.
And in conjunction with field spec data.
Okay. I think a field trip up to Reno is in order sometime soon.
Yes, we'd love to have you. Okay,
all right, thanks.
Visit. Thank you. Any other questions? I have time for
I have one more coming.
One or two. Thanks.
Yeah, good morning. Jordan Baxter with Eldorado Irrigation District. So sticking with the Caldor theme.
Okay.
Super interesting that your observations of hive burn severity not having the albedos you kind of expected. Anecdotally, that's what I saw too. Those parts of the forest that maybe it's a third loss and there's still green trees, just covered in pine needles. So I think that hypothesis is pretty darn true. So very interesting.
Okay.
And thank you.
Thank you, Jordan. I really appreciate that. All right, is that it?
We have more questions, Anne, but I know you have time, so I'll let you.
No, I do. I have a cup time for a little bit more. I'd have to literally be walking out of my office in 10 minutes, but I'm okay for now.
Okay, great. Well, I think we have more questions.
Hi, Anne. It's Jeff Dozier.
Oh, hello, Jeff.
So the question I have is a fairly, I think, an easy one. Well, why don't you think that me theory applies to these charcoal things? You know, aside from the fact that they're not spheres, but particularly the nuisance vague Wiscombe, you know, complex angular momentum stuff is really fast for.
Right. I think they're too big. So we're talking about particles that aren't particles, they're chunks. And sometimes it's bark. And so what Senlin and he and I are doing is kind of invoking a spectral mixture analysis approach in which we are assuming that any burned woody debris on the surface is a perfect absorber, and that any exposed snow is a combination of ice particles and black carbon, which is in the Me size limit. Does that make sense?
Maybe no, but we should talk.
No. Okay. Let's talk, because I don't know how else to model big chunks of black stuff on top of snow.
I think Tom's going to explain it to Jeff.
I'll argue with Jeff on your behalf.
Okay, thanks.
At the coffee.
But loop me in. I'm always wanting to learn more. Thanks.
Hi, Anne. Thanks for the great presentation. It's Ronnie Abalafi-Rosenzweig here from NCAR. I'm working close with Senlin He. And I have a quick comment and then a burning question. The comment is, I'm really excited to see the development you're doing with the SNECAR model at NCAR's end. we've just coupled SNECAR with NOAA MP, which is part of the WRF-Hydro. So I'm
Right.
excited to be doing, to be learning from your research on that.
Mhm.
And then the question is, looking at the correlation between the CCI and snow disappearance, do you think that could potentially be used for like a seasonal fire hazard forecast to inform that type of thing? And
Yeah.
how do you envision that being used?
I do. I think that with some more refinement, I think that we could identify areas of vulnerable forest, that areas of forest that have had multiple years of low CCI in the fall, and then on an annual basis, for sure, that's what I was showing with that R² value, is saying, you know, in the Sierras, what we've shown is that there is a significant correlation between that CCI metric and the snow disappearance date metric, both of which I think could be refined spatially, which would be great. The relationship between the late summer moisture stress index and SDD is stronger than the relationship of that moisture stress index and any summer precipitation or vapor pressure deficit in the Sierras. Vapor pressure deficit is still significant, but the snow disappearance date is important. I'm not saying that snow disappearance date is necessarily the causal factor, but I think it's a really good proxy for a lot of things that affect the downregulation of photosynthesis in the late summer for these forests.
It's really exciting. So thanks for that. And also, Senlin and I are working on a seasonal fire forecasting model, building on our recent ERL paper. So I'd love to touch base later and maybe learn some more. Thanks.
I'd love to hear more about that. Thank you. I'm sorry, I probably have to go.
Thanks a bunch, Anne. That was really great.
Thanks, everybody. Wish I could be there. Bye.
Okay, next up we have Ty Brandt from UC San Diego. He's going to be talking about spatial scales of snowfall patterns from fine scale to much larger scale, and he gets to be in person.
Okay, good morning, everybody. So to date, most of this conference has been spent on sort of thinking about ASO and sort of downstream, what I'm going to call science and management applications. But what happens if we think about this in a different way? Instead of looking down, what happens if we look up? And what I mean by that is there an opportunity that we're missing? Can we use, for example, the Airborne Snow Observatory to refine our understanding of mountain meteorology? So precipitation drives the hydrologic cycle on land. In the Western US, we cede to this kind of dichotomy of often too much or too little. And in the past, our predecessors have sort of tried to manage that or adapt and endure by taking in-situ measurements. You know, the first of which, 1908, was the snow course, right? Today, however, we require more spatial context to that. And so we've built, in essence, QPEs, quantitative precipitation estimates. Probably the most famous of which most of us are aware of, is PRISM. PRISM is baked into almost every QPE in the Western US, as well as in some cases, a lot of snow data sets. Okay, the problem. How do we know that in situ gauges and the products that they create, i.e. the QPEs themselves, actually capture that spatial distribution? You know, you can do cross-validation studies, which is what's often been done in the past, where you leave a station out and you test your QPE at that particular location, or you can do that with whole station networks. For example, you know, DWR's Snow Pillar network. Nonetheless, all these studies are biased. They're biased based on two things. They're biased based on our own perceptions of what should be measured, and in addition to that, what can be measured. And I think Frank Gerke did a great job of showing us that distribution in his first talk on Monday. Now, ASO's changed the game. We've got the first truly sort of gauge independent data set for this year across the entire Sierra Nevada, which truly sheds light on, you know, especially those midwinter flights, on storm to storm and year to year variability in ways that we've never been able to see before. Now, in my mind, good science starts with a hypothesis. There's a bit of a lost art in environmental science these days, but a hypothesis does two things. First, it helps to focus the investigation and the talk. And second off, it helps those in the audience kind of follow along. Now we're going to start with one sort of broad hypothesis that we can kind of split into two. That is, the existing in-situ network of snow pillows and or snow courses, it doesn't matter which, can capture the spatial variability of snowfall at the range scale, so that's the entire Sierra Nevada, for example, and at the basin scale. Now we're going to do this using big years. Big years helps us kind of separate out the spatial variability for the magnitude. When you get precipitation, it's hard to kind of differentiate between the two. A good example is if I was to hold up an apple and a grape, the first thing probably all of you would notice is the size difference, right? Whereas if I was to hold up an apple and an orange, you'd probably notice the texture, the color, maybe the small sort of perturbations. And that's exactly what we're going to do here. Now, there are caveats to this work, especially with working with Airborne Snow Observatory data, which are, snapshots in time. There's wind distribution, sublimation, midwinter melt, rain on snow. But I would argue, when we're talking about signal to noise ratio, those are quite small indeed for what we're planning to use this for. Okay, range scale. What do we see? Well, I've been in California now for a bit more than 10 years. And one of the things I've noticed about, winters here is that in some years we get more snow in the north, and in some years we get more snow in the south. So we might hypothesize if our in-situ network, so we're talking about snow courses here because we're going to go back in time, we're going to hypothesize that this in-situ network sort of responds to that. That would make sense, right? Okay, so we ranked peak sweep from snow courses. We looked at about 200 up and down the state from 1930 through 2020, the idea being we're looking for those big snow years. And lo and behold, these are the big snow years that popped out. And granted, most of these years are sort of etched into our memory here. 1952, 1969, of course 1983, 2017, and 2023. Now, when we look at how the snow courses sort of captured that variability up and down the state, so if you look at the top, you can see Shasta Trinity all the way down through sort of the southern Sierra Nevada and Mona Owens. We can see the difference between Woodill 2023, which is in black. The line itself is the median. The gray shading is the interquartile range. And we can see how that differs with 1952. In 1952, we had more snow in the north. That's exactly the same in 1983, but entirely different in 1969 and in 2017. So this kind of matches with what we would expect, right? But how else can we possibly corroborate this? Well, one of the ways we can do this is we can look to atmospheric reanalysis, which are gauge and aware, but resolve that atmospheric physics. So if we're hypothesizing that storm track matters, that in theory should be baked into these products. And what we find is, if we're just looking at two examples, 1983 versus 2023, you'll note that in the difference map, we can see that 1983, lo and behold, has more snow in the north, and 2023 has more snow in the south. Now, the final way that we can really test our snow course data and the spatial variability and whether it truly captures that range scale is with ASO. And ASO, for the first time this year, flew the entire Sierra Nevada, which is truly an impressive feat, what you think about what goes into that. Now, granted, there's about a month of time lapse in between those ASO flights. But broadly speaking, when you look up and down from the feather all the way down to the cone, if you look at how the ASO data sort of moves up and down, you'll note that the snow courses kind of follow that. Now, for those of you in the audience, you're probably looking at that going, there looks like a bias. And just for giggles, my colleague and I sort of said, hey, let's just take a stab at removing that bias and let's just do a simple mean difference. When you do that, it's amazing how well things sort of line up. But that's a bit of a distraction. The point that I want to make is that at least at the range scale, this in-situ network that we've built over a long period of time seems to be successful at sort of capturing that spatial variability that we're observing. Okay, let's move on to the basin. Now we're going to focus in on the San Joaquin. There's two reasons to do that. The first is that it's one of the most compelling stories for what I'm going to show you. The second is that sans the Tuolumne, it's got one of the most sort of densest sort of flights, especially during the winter itself. Now we're going to look at the mean snow pillow sort of SWE over here, which is nothing more than a snow station index of sorts. It's the mean SWE on a daily basis. What I want you to look at is this period in January, late January, and how the fact that at that point in time, both 2017 and water year 2023 seem to converge with the same amount of snow in the basin. And that's roughly about 0.9 meters or 3 feet of sweep. Now, when we look at these ASO acquisitions and we compare the January flight in 2017 and the January flight in 2023, the first thing that should pop out is how different those spatial distributions really are. Particularly in 2023, this sort of blasting of the northern sort of subbasins in the San Joaquin. So for the same snow pillow SWE, the spatial distribution of snow is entirely different. The key difference, though, is at the extremes. It's not in the means or the medians, it's in the deepest snows, right? So it's these yellows and things like that where the key differences between these water years stand out. And for the most part, that's above our station index. Now, the final point I want to make on this side here is that for the same snow pillow SWE, the volume differences as a result of the spatial differences are huge. It amounts to 0.9 cubic kilometers of water, or 730,000 acre feet. It's roughly approximately 140% of Milliton Lake. Granted, it's not the hugest lake, but still nonetheless, that's a huge disparity that we're looking at. Now, was this just luck? For example, was that January 2023 flight just sort of an oddball? Well, the answer is no. If we look at the peak SWE distribution in March of 2019, we say the same distribution. And in fact, the same sort of differences between 17 and 19 are reflective in the snow pillow network. We can see we had roughly the same snow pillow SWE, very different spatial distributions between these two ASO acquisitions. And as a result of that, very different basin volume differences between them. Now, the interesting part is where this occurs. If we look here at this elevation sort of SWE depth profile, you'll note that the deep snows in 2017 occur at the very highest elevations of the basin, and the snow pillow network is represented by these dashed lines. All that deep snow, well above the snow pillow network. Not only that, it's really interesting to compare 2017 with 2019, where you had much, much sourer depths at the higher elevations. Now, the key thing is, does this depth in 2017 make a difference? And I would argue yes. You can see how the volume really sort of bumps out as a result of those deep snows at those higher elevations. So what drives this? What causes this year-to-year variability that I'm talking about? What's the meteorology? So what my colleagues and I did is we looked at Error 5, and what we're looking at down here is sort of a summation of the meteorological sort of activity from November 1st through the ASO acquisition dates. What's really neat about this is that we've got the magnitude of the storms here on sort of the y-axis. The angle here is the storm trajectory itself. The color is the freezing level of the storm, and then the size of the circles are the mean aerial precip. Now, what's really neat about this is when we look at 2017, you can see these storms coming in from about 210 to 240 degrees. That's about a 30-degree difference. We've got these very warm freezing levels. So warmer air holds more moisture, means you can move up further within that, sort of elevational relationship along that basin and deposit snow at that deeper level. So that's exactly what we saw in water year 2017. We compare that with 2019, notice these very southerly trajectory sort of storms here, which kind of explains the spatial distribution differences. It also explains why that snow wasn't deposited nearly as high within the basin. It's a colder storm system, it holds less moisture. Now, 2023 is this really interesting year. We started off with January, where we had all that snow in the northern subbasins. And then as we progress through March, we kind of fill out and bulk out the basin entirely. And that's because the storm started off in a very southerly trajectory and then shifted west. We had very cold storms. And that's why you see that bulk at the sort of lower elevations. Now, the final thing I want to leave you with is, there were some past studies that looked at idealized sort of precipitation regimes as a result of storm trajectory. And this last one is particularly interesting. They found as much as an 18% change in the precip as a result of a 1-degree wind rotation. When you look down here at 2023, there's 90 degrees of storm trajectory variance. Okay, so how did other sort of forms of QPEs do with regards to the ASO data? We've got the January and March 2017 flights right here, the January 2023 and March 2023 flights over here. We've got sort of a hydrology sort of representation here with VIC, which was calibrated using snow courses. We've got PRISM, And we've got Era 5. Now, some of these are gauge-aware products, some of them are not. Era 5 is just literally atmospheric physics. Yet none of these capture that spatial distribution as observed by ASO, and particularly sort of that northern blasting that we see in January 2023. Okay, conclusions. So our in-situ network, whether it's snow courses or snow pillars, since they're roughly in the same place, we can sort of lump them together, seems to be capable of capturing that range scale precipitation. However, when we talk about the basin scale, that's where things begin to fail. And this has massive ramifications for how we think about truth and how we use things like quantitative precipitation estimates, especially if we're using them to train things like weather models, or if we're using them for downstream science. Think about the volume of science that's used PRISM, for example, over the decades it's been available. I mean, the papers probably stacked from here above this. If you stack them one after the other, they're probably above the roof. The meteorology matters. It's the driving force behind these spatial variations that we're seeing. And it's not just orographic effects. That's really, really important to understand. That's something I didn't quite understand when I first got into this. It's all the way out into the North Pacific that sort of drives that spatial variability. I see an opportunity here for something that we've never done before. What happens if we use ASO to bracket individual storms and develop a library of QPEs? What happens if we leverage programs like CW3's AR Recon and WestWRF, which is a flavor of WRF, and fine-tune the parameterizations based on those QPEs that ASO observes? That's a pathway to a quantitative precipitation forecast that we've never had before. Now, the Sierra Nevada as a location has this storied relationship of being a test bed for new technologies to improve water forecasting. Mount Rose Sampler, good example. ASO, another great example. We have the tools and programs in place to actually go after this problem of the winter distribution of precip. But we need both weather and snow. You can't do this without both communities. Question is are we bold enough to lead again? Thank you very much.
Well, that was pretty good. Let's see, have we got questions? I see Peter down the back here.
This is amazing. My mind is blown because I work in the San Joaquin and the Mono Basin, and the two are obviously related. Mono Lake's there because of the San Joaquin Gap, in my view. But I want to know if what you're doing here could we entice you to look at this both for the Owens and Mono Basin, and including not snow courses, but just the precipitation gauges, and like this year and 69 just had massive amounts of snow, but trying to figure out how much runoff that amount of snow might provide you. I mean, my mind is racing, but this is so wonderful to see how you're evolving this. So is there ways we can have you look east also?
I'm being blackmailed from up front.
Yeah.
I mean, the opportunity, you can take this as far as you want to go. The point is we've got the opportunity and tools to do this. And we could apply this to any basin as well, especially if you're going after individual storms. And, the Mono Basin is an interesting basin because obviously it's a lee side basin relative to the storms themselves. So, like all of this, the sky is the limit. It's as far as you want to take it. There's tons of opportunity here and tons of, places to explore too. Lee side basins are just as important as the windward side basins. So absolutely, we'd be happy to kind of, my colleagues and I, Caden's right next to you at CW3, and Gabe's right in front of you too. We'd be happy to kind of talk to you more about this in person as well.
All right, I've got a question from Chad here.
I just had a couple comments that I think you're going to like. One, great work. Two, there's more drama here than you realize, because the 2020 creek fire really messed up that northern part that, as you pointed out, really got hammered by those southerly cold storms. The Forest Service, for safety reasons, was unable to get numerous months of snow courses, all in that tier. So we were completely blind from a snow course point of view in 2023. Additionally, we didn't have any good snow pillows in that area until we were able, literally at the last minute of last summer, to rebuild the Green Mountain Station. Had we not done that, the San Joaquin would have been completely blind on that face. And so this idea, I mean, not only ASO, but making these like storm scenarios or library, as you say, of storm directions is really going to help those situations when we have interruptions in our in-situ network.
Thank you. I think Agnew Pass was also down too, wasn't it, in 2023? Yeah, and Gem Pass.
Hi, Ty. Thanks for your TED Talk. It was awesome. We need to do more snow-related TED Talks. But so I'm just curious, obviously we have awesome data, and this is such a cool use of ASO data, but how many more, like, are we missing conditions? How many more flights do we need? Or how far away are we from, this quantitative precipitation forecast?
The question that I was hoping to avoid. Really, the best answer to that is from the meteorologists. Like, they're the ones I would want to talk to about what specific sort of mechanisms they would want to target. I mean, AR Recon and ASO fly every year now. AR Recon is out there in the North Pacific dropping radio sondes to kind of refine our AR forecasts. What I'm proposing here is not a short-term thing.
Right.
I think all of us would want a better QPF. I mean, how much easier would it be if we had an accurate spatial and sort of temporal sort of QPF 10-day out, for example? Make our lives significantly easier. Now, that doesn't mean that in any way, shape, or form that we remove the importance of ASO or CW3 AR Recon, because there's always chaos and variability that we can't possibly map or capture. It would just put us in a better space. Now, how many storms do we need? As I said, I want to go to the meteorologists, talk to them, get them to really think about the mechanisms that they'd want to capture. But Mother Nature also has to align. I mean, I was talking with Liz, and I've been talking with Kat for quite some time about, well, how do we even do this? Like, do we get planes to stand by? What types of storms could we fly? Like, obviously, you need the weather window to do that. So there's complications, but the point is that the tools are in place, the programs are in place, and I think we can do some really cool science here and the opportunities here.
Hi, Ty. I know we haven't met yet. I'm Marco Bell. I'm with West Consultants, and I know we're going to be working together probably in the near future. I did some work in the Big Creek Basin back in 2010, and we developed a real-time model that includes a lot of the meteorology and a lot of the snow and water in real time. And we noticed the very same thing that you're saying, that it's very important to capture the weather. And we actually were doing that new, and I think that was about the time that I think I met Tommy. We were talking about integrating the ASO data into the real-time models for this. So there's a lot of data out there. I don't know if you've seen that work or not, but you may want to take a look at that for your stuff.
Yeah, thank you so much. I'd love to see it.
All right, lots of interest, but you can find Ty. He's right here. Ty, you spelt my name wrong. Very good to have you here. Okay, so jumping forward a little bit again, like I said, off-piste, we have Ellery McQuilikin. Now, I've been talking to Ellery on and off for years. She's been working on this stuff since she's been in high school. And so, yeah, she knows this stuff really well. And I'm pretty happy to have her speak at the ASO conference. So she's going to be talking about the Dana Glacier and using ASO data to quantify volumes and runoff and all kinds of things. So take it away, Ellery.
Okay, awesome. I'm just going to quickly share my screen. Can everybody see this?
Yes, it looks great.
Great. Awesome. Okay. Yeah. Hi, everyone. Like you just said, my name is Ellery McQuilikin. I'm currently a sophomore at Williams College, which is in Massachusetts. I've grown up in the Eastern Sierra for my whole life, like lived in Lee Vining, went to high school there. So lots of strong relationships with this area. And for the past 5 or so years, I've done pretty extensive field research on the Dana Glacier, which is a small cirque glacier in the Sierra Nevada mountains. If you kind of imagine driving up Tioga Pass, Mount Dana is there on your left, and the Dana Glacier sits right beneath that at an elevation of 11,500 feet. So over these last 5 years, I've conducted a lot of different research to sort of try and document the ways that climate change is impacting this glacier. So just like for a little contextual orientation, the Dana Glacier is this green marker here, Mono Lake, Lee Vining. You can see it is here. There are 3 other glaciers in the Mono Basin, the Kuna, Coip, and Kness glaciers. Hoping to extend my research into those, but as of now, my research is pretty much primarily focused on the Dana Glacier. So sort of to jump right into it, part of being able to document the Dana Glacier and sort of quantify all these changes that I've worked to observe, ASO has played a super huge role in that, as it's sort of like a starting point for a lot of the quantification that I've done. I've relied really heavily on the snow off data, which is not always the most common use of ASO, because that snow off data gives me a really accurate representation of the actual surface of the glacier and then the terrain around it that actually isn't snow but is rock. So it's this like super important layer that I've used in a lot of different ways in terms of mapping out projects and 3D modeling to create just to sort of to further my quantification of these changes at the Dana Glacier. So to start off with, the sort of the first part of this project was to figure out if the Dana Glacier, which is melting away rapidly, has shrunk a lot in the last decade, to figure out, is it still a glacier? And so in 2019, I conducted a year-long study in which I measured movement of the glacier. I led a team out and we placed 3 stakes across the surface of the glacier and surveyed their location using a laser rangefinder, and then returned a year later and resurveyed them. Over that time period, we identified that the glacier moved around 3.5 meters. So the Dana Glacier is still a glacier. It's moving, which is really exciting news. Sadly, now that data's, I collected it a few years ago, it really could have changed because the Dana Glacier, the environment is changing at a very rapid rate. But as of our most recent information, the Dana Glacier is still a glacier, but it's certainly entering into this slowing down period. It's not moving as fast as other glaciers that are nearby, like the McClure Glacier, and certainly not as fast as, Alaskan glaciers that you can imagine on that really large scale. ASO data played a pretty important role in this research in terms of giving me sort of information about where the glacier ice actually is and helping me plan and map out this trip. When, measuring the movement of this glacier, really important to have the poles in ice and not on snow around the margins of the glacier that could appear to be ice, and ASO data was super important for making that identification. But the next year is when the ASO LiDAR data started to play a much bigger role in my research. So I knew the Dana Glacier is a glacier, but that it's moving pretty slowly. And sort of the next step was to be like, okay, what is the volume of this glacier? Sort of give me another piece of the puzzle. And when is the Dana Glacier going to disappear? How is climate change affecting it? What does all of this look like? And evaluating the volume of a glacier is complicated because there's no way to actually see what the bottom of the glacier looks like. But fortunately, I did have a great piece of this puzzle, and the surface of the glacier had this super high precision LiDAR snow off data that is also, timely. It's not super old data. This is a really accurate representation of the glacier surface, which was super important in having a strong starting piece for creating this model. And I decided that the best and most feasible way to sort of create a model of the bottom of the Dana Glacier, that bedrock surface underneath it, was to use a combination of direct depth measurements and 3D modeling. So to obtain these direct depth measurements, I used a Hoike steam drill, which is this exciting contraption here. It essentially uses pressurized steam that's directed through this hose, allows you to melt small diameters holes through ice. So here I am using this. In October 2020, I led another team to the Dana Glacier, and we drilled or melted 5 holes across the surface of the glacier. We weren't able to reach bedrock in every location because in some places the ice was simply too thick, but was a very important starting point in getting an idea of how deep and how thick this glacier actually is. You can see a photo here. Here's me carrying the Hoike steam drill. Some of my lovely team members, including Greg Stock, who's been a really wonderful advisor throughout all of this research, starting way back in my freshman year of high school. So here you can see the 5 locations where we drilled on the glacier. We were trying to be in places where it was feasible that we could reach ice, so mainly around the margins of the glacier, but also wanted to have a wide distribution, so we tried to spread them out as evenly as possible. So I had these 5 depth points, but I wanted to have more depth points to work with before starting my 3D model. So I took the ASO LiDAR snow-off data and I put it into Cloud Compare, which is a 3D modeling program, and it creates this sort of point cloud, which you can see here. The orange is the glacier surface and the blue is the surrounding bedrock terrain. And I created 5 cross sections of this LiDAR data point cloud. And then in each of those cross sections, you can see that there's a pretty logical line that you can draw that connects the edges of the terrain together in a way that it's like, okay, it's reasonable that the rock would be shaped like this underneath the glacier. So I drew in that line for 5 cross sections on the glacier and then extracted 3 depth points from each of those cross sections. So I then had 15 points representing thickness of the glacier to work with in my 3D model. I also had 20 points that I used to define the margins of the glacier, which were also extracted from the LiDAR data based on the presence of the glacier. So then I had these 35 points to work with, and I used interpolation tools in ArcGIS Pro to create the 4 bedrock surfaces you see here. I determined that the Kriging bedrock surface was the most accurate representation of bedrock underneath the Dana Glacier and used this going forward with my model of the glacier. So you can see here is the bedrock inset against the surrounding LiDAR terrain data from ASO, and then here is the actual 3D model of the Dana Glacier. So you can see it has this super high precision LiDAR ice surface and then this modeled bedrock. And once I had this actual model and 3D representation of the glacier, I could bring out a lot of analysis about actual ice thickness of the glacier. So in this figure here, the darker the color, the thicker the ice. And you can see here's the Dana Glacier. I identified that the thickest part of the glacier is around 30 meters thick. The average thickness is 12 meters, and 50% of the glacier is under 13 meters thick. So just sort of as a starting point, we can see, okay, the Dana Glacier is not that thick. An average thickness of 12 meters is not a whole lot of ice. It's got some thicker parts, but certainly is sort of going along with the data that I gathered from the movement that it's like, okay, it's a glacier, it's moving slowly. It's got a pretty thin average thickness, which corresponds with the total volume that's 596,000 cubic meters, which just for reference is about enough ice to fill the Rose Bowl, which does kind of seem like a lot when you think about it from that reference, but is really extremely small for a glacier. So now that I had this information about thickness of the Dana Glacier and this general knowledge that it's pretty thin, the next step in this research was to actually make a prediction about when the glacier would melt away and measure melt of the glacier. So over the summer of 2021, we went out to the Dana Glacier again. We placed 8 ablation stakes across the surface of the glacier. So in each location, we used the ice auger, which you can see here, to drill a hole through ice, place the pole into the ice, then, glacier freezes around the pole, and as it melts, more of the pole becomes exposed, and that reveals how much ice has melted over a period of time. So we were here during July. It was sort of peak heat wave conditions. This was a dry winter, long summer, and so a lot of melting happened. And you can just see in this video that the amount of water pouring off the glacier is really quite intense. And then here as well is a time-lapse video of the glacier melting over just 12 days. And it's just really a sort of striking and dramatic thing to look at when you see the water that's pouring off, the melt that's happening so dramatically. So the Dana Glacier is really in a big state of change. A lot of change is happening, and it's happening really, really quickly and very much before our eyes. This is also very much represented in the data that I gathered. So to start with, here's the ice auger extended at full length. We drilled 5 meters into the ice. So that's, what 5 meters looks like compared to my height. And then also you can see here, this is the blue pole. When we placed it, it was coming up to, about the height of my knee. And then here, when we retrieved it, just slightly more than a month later, it's more than double my height. So really just sort of dramatic visualizations of how much melt is occurring. And then when we actually look at the data, and I also extended all of this data to be representative of the entire melt season because I was only measuring for a very small fraction of it. This is the extent of melt over this full melt season, which comes out to be on average 5 meters. And 5 meters is just really a lot of ice. That's like, a 2-story building full of ice that melted off the Dana Glacier in a singular summer. And if we go back to thinking about an average thickness of 12 meters, it's really kind of frightening to think about how much one summer can have an impact on this glacier. So to take this farther, I wanted to actually predict when is the Dana Glacier going to melt away. So I again used the Kriging interpolation tool to make this representation of melt across the surface. You can see it's melting more in this lower section because that area gets more sunlight than this upper area. And then I went back to my 3D model of the Dana Glacier, and I essentially digitally melted the glacier. So I subtracted that melt surface from my 3D model of the glacier year after year. And you can see this sequence here. So this is what the ice surface looked like at the end of the 2021 melt season, 2022 melt season, 2023, 24, 25, 2026 melt season, and the 2027 melt season.
Ellery, just real quick, we're not seeing the slides advance. We're still on number 20.
Oh, okay. Huh. Let me
There we
scroll
go. 21. There we go.
Oh, is it changing now? Okay, yeah. Sometimes it does take a second for these to load because they're more.
Great. We're seeing it now, I think. Thank you.
Do you see the red surface?
Yes.
Okay, so this is the interpolated surface I made to represent melt across the glacier. And then now it looks like we're seeing, so this is the 3D model of the glacier at the end of the 2021 melt season. And then we'll see, I think it's going to start progressing through, yeah. So there's the process of the glacier shrinking. And then it grows because I scrolled back, but I'll catch us up now. So we'll see it one more time. This is the glacier at the end of the 2022 melt season. 23, end of the 2024 melt season, end of the 2025 melt season, end of the 2026 melt season, and then by 2027, the glacier is essentially gone. 2027 is, 4 years from now. That's really, really soon. That's, closer than the near future, which is scary to think about. And when I first made this model, it definitely was, a big realization. And I'd always in my head been like, oh yes, this glacier is going to melt away soon. But seeing this visual representation of the glacier disappearing was really kind of shocking to think about things from this extent. Now, it is important to remember, the glacier is not going to melt away in this perfectly linear path. I also measured that melt during a dry sort of drier winter scenario. So there was a really lengthy melt season. So I created 2 other scenarios in which there's a more average melt season because there's a more average winter, and then this wetter winter scenario in which you have some really large winters and so the glacier is not melting as much. We had this really big winter, which does make this initial sequence that I just showed, that changes things. But one big winter in comparison to several large drought years maybe adds 2 years of life onto the Dana Glacier. I think that it's sort of put us more into this average winter scenario. The Dana Glacier likely didn't melt. The ice surface likely didn't melt at all this summer. And hopefully it'll get through most of next summer without melting either. But then after that, we're sort of on the same track. This wetter winter scenario is very unlikely, as it would need to have the 4 or 5 really large winters to have such a small amount of melt occur. And even in this wetter winter scenario, this is the glacier melting away in 2039, all of which is extremely soon. But the real range that we're in right now is definitely the glacier melting away in the next 5 to 7 years. And, this is just, it's a lot to think about. This glacier has been here for a really long time, and the fact that it's now going to be gone, or, essentially all of it will be gone, is really something significant to reckon with. And so I've become very committed to trying to understand and document and quantify as much of this glacier as I possibly can. And so this summer, I continued my research on the glacier. I borrowed ground-penetrating radar from a wonderful scientist at Creel and was able to take this out onto the glacier to map subglacial bedrock, which is really exciting because, of course, I have this really great ASO data that's super high precision in terms of the surface of the glacier. But I was working with for the bedrock was a pretty good model, but definitely this GPR is going to improve that and will give me a really accurate look at what's actually going on underneath the glacier. I haven't done all of the analysis from this research yet, but I'm really excited to put that together and have a much higher precision and more accurate map of the bedrock to use with this ASO data. Also, the big winter will be really interesting to look at in this model in terms of how much snow is on the glacier, which will also allow me to better assess the impact that one really big winter had on the melting process of the glacier. So sort of just to conclude with, clearly some really big changes are happening at the Dana Glacier. This is the glacier in 1883, taken by Israel Russell, and this was the glacier in 2022. So I'll show that again. This is just a really scary thing to look at. And it's clear that climate change is happening. It's having really big impacts. The Dana Glacier is being severely impacted, which will have a world of impacts. And the Dana Glacier supports the riparian habitat downstream in really significant ways, which spirals out into a lot of other really important impacts. And there's also simply so much to learn from this glacier while it's still here, and so much to document in terms of what does it look like for the surrounding environment when a glacier melts away. And I think that when this research I'm doing starts to get really sad, the thing that's sort of a comforting thing to take out of it is that by documenting and quantifying as much as I possibly can about this glacier, we can learn information that might help us predict what will happen in environments in the future and help us be more prepared to deal with these impacts. And I think the ASO plays a really important role in that, because it's allowing for this really high precision evaluation of these environments. It makes remote studies possible. And I think that sort of the most crucial thing we can do in a situation like this, where it's not actually possible to save the Dana Glacier, is to do as much as we possibly can to document it as it melts away, and just learn as much as we possibly can before it's disappeared. So just show one more photo point, sort of the classic Dana Glacier photo point from this lake. To conclude things, I think it's really, really crucial that we do as much as we possibly can to learn what we can from this glacier now. And I'm just super thankful that ASO gets to play an exciting role in that. And they're flying all of the glaciers now is like just really exciting research and exciting opportunities to be able to better pay attention to these environments. Thank you.
Wow, that's really, really great research, Ellery. Tom has a comment.
Hi, Ellery. It's Tom Painter. Thanks for taking the time to do this. I'm as always, I was happy that I got in touch with your dad and made sure that you were going to present. So you're stuck with us, by the way. We're partners on this, and I'm not sure if everybody knows, but we, before we became ASO Inc., going into becoming this public benefit corporation, one of the commitments that we made was that we were going to fly these glaciers in the Sierra Nevada on our own dime every fall, and to make sure that we document their demise. And having an extraordinary scientist such as Ellery making those in situ measurements and then the quantitative modeling just makes that so much more valuable. So Ellery, thanks for that. Thanks for your motivation, and thanks for where you're going to carry us in the future.
Yeah, thank you. I appreciate that.
Thanks, Ellery. I think we're going to skip through because we are running severely late, and that is my fault.
Sounds good.
So if you have any questions, Ellery's email is up there, and also Ellery has to get to school.
Yeah, definitely feel free to reach out with any questions. I'm super excited to talk about all of this.
Thank you. We'll also forward on some of the questions from the Zoom chat to you, Ellery.
Sounds great. Thanks so much.
Amazing. Okay. And so Lisa's going to be talking about the ASO, about the creek fire. So we're just jumping straight back into wildfire land. And there's been a ton of data collected over the creek fire that happened in the San Joaquin. And Lisa's been churning over all of these different sources of data. And so I'm really excited to see where this research is at right now. So take it away, Liz.
Thanks, Kat. And I will try to be as quick as possible. I know we've really gone over in time. And the work that we're going to be talking about today is really in progress. So I'm kind of giving you guys a bit of a progress report in terms of what we've been doing. And this is really a team effort. The research that I'm going to be talking about today is actually a snapshot of a larger set of questions that we've really been delving into with respect to the creek fire. And so this particular perspective is regarding fire severity. And the team that I'm working with is Pratima KC, University of Washington, Eric Roll, and Tim Wallace with DRI, and Van King. Did somebody say something? You stop, we're good? Okay, I'm gonna keep on going here. So as we've been talking about, we were very, very well acquainted in the Sierra National Forest and in the San Joaquin Basin with the impacts of both drought and fire in this particular basin. I'm not going to go into this in too much detail because we've already been talking about that, as we were well aware of, that these forest systems are in flux, and that has implications for both snowpack and SWE. So in terms of the creek fire, again, I was mentioning this is part of a larger research effort. And the first question, and the one we're going to be looking at in greater detail today, is really how did pre-fire forest conditions, active fire weather, and fire energetics interact and influence post-fire outcomes? There's additional work that's going on with this particular study that has to do with structure loss in the wildland-urban interface. And then, of course, the outcomes of questions 1 and 2 informing management recommendations for fuel treatment efficacy and other post-fire conditions, including structure loss. So again, what we're focusing in on today with respect to ASO, Inc. data and other data sources that are at very high fidelity has to do with looking at fire severity and examining fire severity at a very different scale that we've been historically doing. So you all have seen many, many fire severity maps of all sorts of fires, whether you're looking at the Western US or globally. And these information that we generate for fire severity, they're provided to us at 30-meter resolution with Landsat, and they're typically provided to us 1 year post-fire. But in reality, tree mortality and losses that are associated with resultant vegetation severity don't just happen 1 year post-fire. So there's a great deal of information from an ecological perspective that we could be missing, as well as just not capturing the full suite of mortality. So what is so incredibly unique, as of course you've been seeing so much of Anne's terrific research relating to forest fire and snow, is there's just been an abundance of very high resolution LiDAR imagery, hyperspectral data that has been collected both immediately preceding the creek fire and following it. And in addition to those pre and post data, there was active fire energetics information collected at a multi-temporal scale. So instead of just asking questions that say, what was the preceding force structure information and what was the resultant severity at a 30-meter scale, we're kind of decoupling this fire and honing in at very fine resolution, both from a spatial perspective and a temporal perspective, and actually looking at the connective tissues between what was present pre-fire, looking at climate and weather, and of course, fire weather itself and energy releases, and then those post-fire outcomes. And the way that we've been able to do this is to, again, leverage these partnerships with the ASO and many partners to be able to take these very high resolution, multimodal, multi-temporal data and combine it with artificial intelligence to provide a fresh look at what is resultant vegetation severity in terms of forest. And I'm at the University of Washington. I'm a research scientist in the Forest Resilience Lab. And what the Forest Resilience Lab has really been lasering in on, I guess, total pun intended there, is looking at tree patterns, particularly in frequent fire forests. And what we have been doing with that information is we actually model overstory trees from airborne LiDAR, and then evaluate the patterns of these trees across the landscape. So, of course, this is providing an overstory tree perspective and its spatial arrangements, both vertically and horizontally. And we can take our knowledge of what contemporary forest conditions that have fire visiting the landscape and say, how departed are our forest conditions from what we consider to be a state of resistance and resilience? So that's what a lot of the work in the lab has been focused in on. And then my partner in the lab, Pratima KC, and I have been spending our dissertation work really looking at how do we then couple these high fidelity individual tree detection information and combine it with very high resolution imagery and hyperspectral data and actually track the fate of overstory trees through time. And what we've been working on, and I've just been completing my dissertation work, and we're in the process of getting a lot of this information published, is we've come to realize that even if we have a LiDAR data set, in this example, collected in 2010, even into 2018, we can take those LiDAR segmented trees and high fidelity imagery information and track the fate of an overstory tree through time with very high fidelity, and then couple that with artificial intelligence. In this example, that is work that Pratima KC is leading in terms of using convolutional neural networks with a 4-class classification system to capture drought-induced mortality. What we're able to demonstrate is the capability to look at overstory tree mortality over time in very high fidelity and produce high accuracy in being able to detect those changes. And so what we're doing in terms of the creek fire, what we're in progress of doing, is we've got a complex situation in this that is really bearing out across the Sierra and, of course, many areas of the Intermountain West. And that is, we have this pre-fire situation where we had a very significant drought mortality event from 2012 to 2016. And we can use the information that we have available pre-fire to understand what was the drought-induced mortality and biomass that's on the landscape, both using LiDAR and just RGB imagery. Being able to get that rich information, as I was mentioning earlier, regarding the fire weather and energetics at 5-minute temporal intervals from the fire itself. And then with the benefit of this incredible information that the ASO has captured pre and post fire, and along with NAPE and other LiDAR data sets from the USGS, we're honing in on these actual tree pattern and mortality scale changes in this particular fire over time. And what we hope, of course, is that this is going to be able to provide a much richer look at forest resistance and resilience, being able to then inform future fire behavior, snowpack, and sweep. And I say this is what we want to do, but there is a but. And that is if we're migrating from Landsat at this 30-meter scale over to being able to look at individual tree, overstory tree detection and its survivorship status, there's a really important component that we had to be able to do in order to make this happen. And that is, you have to be able to orthorectify the imagery that you're wanting to be able to use to be able to examine these individual tree objects over time. You've got to deal with the fact that traditional orthorectification processes are orthorectifying the imagery to the ground level. And for looking at trees, this causes all sorts of issues because, of course, trees, especially in the Sierra, tend to be fairly tall, and with relief displacement, we're getting a very oblique view of these trees. So what we've been in process with right now with our team is orthorectifying our ASO information from post-fire data to the actual tree canopy. So we can be able to get this nadir perspective, and Anna was alluding to this, that this is critically important to be able to do, to be able to evaluate whether it's vegetation or, impacts and relationships between snow and fire severity. These are important things for us to be able to do to get the proper look and be able to detect and predict overstory tree mortality and the gaps. And so I want to give you just an example of this. This is NAPE imagery that was collected in 2020. So again, we have this immediate pre-fire data, but in this image, you can see this very oblique view of the trees, and our tree segments are what we call tree approximate objects, with the darker colors signaling taller overstory trees. And what you can see is that you really have this really significant challenge in terms of having an alignment of your LiDAR segments and your imagery. And what we've done with the ASO 2021 data is being able to take the ASO's rich 48 centimeter RGB data and align that to our tree approximate objects. And now we're going to be able to create our really robust training and validation data set to take a look at the overstory tree mortality. But when you're looking at this image, I'm sure you probably are looking at this and thinking, yep, really clear to be able to see the resultant high severity here, right? We've lost canopy cover here. And what's important that we're going to be honing in on is where is the presence of seed trees that are going to lend themselves to regeneration in the future. And I really want to draw your attention to the wealth of coarse woody debris that resulted from both the drought and the fire. And this is 9 months post-fire. So not only are we going to be looking at classification of overstory tree mortality to get this ecological look of the resultant severity at an unprecedented scale, we're also going to be examining the presence of biomass and coarse woody debris that's in these gaps that we can be able to take a look at with such high resolution imagery. And in some instances, the NAPE imagery is on nadir and is in alignment. So I wanted to show you that it's not all completely bad news, but in this particular situation, we've got a nadir view of that same location, but overall that is not true. But what you can see, again, this is NAPE 2022 data. You can see the resultant high severity area over there to the east, and the just incredible accumulation of coarse woody debris and very significant mortality that I was mentioning before that isn't occurring 1 year post-fire, right? We're seeing a change between that 9 months and 2 years post-fire, that is really significant. So again, we're going to be focusing on characterizing both the overstory tree mortality as well as the gaps. And we have quite a few next steps. Proxima, though, has already worked on using our tool sets, our classification, and our neural networks to begin predicting the mortality in there. We're going to be continuing to build and make our data sets more robust for being able to capture both drought and post-fire overstory tree mortality and work on these gaps, and being able to create actual maps of overstory tree mortality and really be able to look into the ecology of what is resultant fire severity and get better and more refined information, both about mortality and our future fire potential with these more high resolution, rich information about our fuel conditions. And I want to point out that so much of what we're doing is going to be a complement of the 3D Fuels project that both Eric Roll and Susan Pritchard have been actively engaging on a national level with the Forest Service. And so we're hoping to continue building our understanding of both the ecology and just the nature of fire and fire behavior into the future. And so I'm hoping next year I actually get to make it to the ASO meeting and provide our results in person. And I know you all need a break, and I just want to say thank you so much. And I doubt there's time for questions, but I can definitely stick around and answer things in the chat. Thank you guys so much.
Hi, Liz, it's Tom. I stole the microphone out of Kat's hand. With your last point there, we're going to try to make it easier for you to get here next year. I think we're going to, and for everybody else, I think we're going to move the meeting into August so that people can fly into Bishop or Mammoth and not have to rely on rental car companies to make cars available to them, courtesy of the burners.
Much appreciated.
So thanks for the talk.
Thanks, Liz. That was really great. I think we are going to skip the questions. And so if folks want to jump on and ask a question online, that's always there. 10-minute break. Let's do it. Yeah, we'll come back just a little bit after 11 and we'll keep cranking.
Thanks, you guys.
California Snowpocalypse 2023. Amazing. Okay, take it away, Noah.
Yeah, thanks everyone for your attention, and thanks for the introduction to speak, or the invitation rather to speak. And I want to start by acknowledging the real driver behind this work, which is Leanne Lestak, who really persevered through a lot this past year to get this work done. Other team members, Carl Ricker, Kahan Yang, and many discussions with Chad Moore this winter about conditions. And then the ASO and California DWR teams are mentioned here to be inclusive rather than exclusive. There's just so many people involved from both of those teams. I didn't want to leave anyone out. But Jeff and Tom and Kat on the ASO side, and Ramesh and Sean and Dave on the DWR side have really been instrumental in this work, which was coming together here nicely for the California Snowpocalypse, as I put in the title for 2023, harnessing airborne and satellite data to inform water supply assessments. And the objective here is really to support decision-making with real-time spatial snow water equivalent estimates, to utilize snow water equivalent analyses and real-time models with the aim of improving those models. And then in the context of Snowpocalypse 2023, for the first time with the extensiveness of ASO data, we've had our first attempt to, in operational mode, fuse that airborne data with ground-based and satellite-based SWE reanalysis products. So just a quick intro to the utilization of snowwater equivalent reanalysis in our modeling system. This plot shows you a variety of topographic variables on the horizontal axis and their relationship with measured snowwater equivalent on snow pillows across the western United States. And you can see very few of these topographic variables explain much variability in measured SWE. But this variable on the far right is a historical SWE reanalysis, and you can see that more so than any topographic metric, the pattern of historical SWE explains more variability in observed SWE at any point in time than any topographic variable. So we leverage that in this SWE, what we're calling a SWE fusion system that uses a generalized linear regression model where the dependent variable is the snow pillow observed snowwater equivalent from the 120 plus sensors across the Sierra Nevada, which are then scaled by real-time measurements from satellite of snow-covered area for the pixel that's co-located with the sensor. And that gives us a scaled estimate of SWE at the location of the sensors. And then the independent variables which are used in this regression model include all of the topographic metrics that are part of the PRISM data set that Ty had talked about, as well as the full data cube of historical snowwater equivalent from 1985 to water to 2016, which represent historical snapshots at the daily timescale of snowwater equivalent distribution that can then be sampled and used as an independent variable to explain the distribution of observed SWE on the snow pillows. And we have two versions of this modeling system, one that just uses the historical reconstructions, and then one that also adds in another independent variable, which is the daily mean observed fractional snow-covered area from MODIS up to the date of interest. So basically, if a pixel appears relatively white and snow-covered persistently through time, then statistically speaking, it likely has more snowwater equivalent than a pixel that has appeared relatively brown through time, or green as the case may be. And so when we look at results from this model when compared with ASO data, this plot was shown by Kohan Yang at last year's meeting of the ASO workshop. Everyone, the two linear regression models against multiple metrics here for multiple ASO dates. So you have ASO acquisition dates on the horizontal axis here as shown by my cursor. And then on the vertical axis, different performance metrics. And the orange circles and green squares are the results from our SWE fusion system with that generalized linear regression model. You can see it has higher R-squared consistently than, for example, SNODAS or National Water Model SWE. Consistently has lower root mean square error, with the exception of a couple of sort of oddball dates. Consistently lower root mean absolute error, and consistently has a percent bias that's closer to 0. Now, because this is a workshop focused on ASO, we also have now, with the more extensive ASO data across the Sierra, the ability to do bias correction, not just for the Tuolumne, which historically is where we've been able to do this because of the abundance of ASO data, but now we're able to do some bias corrections across the entire Sierra. The bias correction scheme, which is another statistical model, utilizes a variety of different machine learning techniques that relate the dependent variable of the residuals of our SWE regression model and relates those SWE residuals, or explains the distribution of them rather, based on different topographic metrics as well as the modeled SWE and canopy density. So where we have ASO data, we're able to do this bias correction and apply this, and we're able to apply the bias correction forward in time. Just briefly mention how much the bias correction improves the model. So the red box plots represent the linear regression model. The blue box plots represent the same model, but with the bias correction from ASO. And you can see an improvement in the R squared in forested areas, in alpine areas, and in other land cover types. You can see a reduction in the root mean square error with the bias correction for these different land cover types. And you can see an improvement when it comes to evaluating the basin-wide absolute percent bias, getting closer to 0 with the bias correction in all cases. Now, really what I wanted to get to in this talk is to look at these maps, because the map on the left shows the difference between our linear regression model and ASO data, mosaic for both the February 1st and February 14th ASO flights, which cover a pretty broad range across the Sierra. And what we're able to do now is to be able to evaluate if there are similar relationships between the SWE residuals and the topography across regions of the Sierra, which we can then apply those statistical models for the date of interest, which is, relatively useful. But really where it becomes powerful is when we can take those bias corrections forward in time for time periods when ASO is not able to fly. So the map for the SWE after the bias correction is shown here for February 14th, and the percent of average is shown here on the map, second from right. And then the summary of the percent of averages by watershed are shown at the far right. You can see by middle of February, the Southern Sierra was already clicking well above 200% of average. And the Northern Sierra was up in the around 160 to 180% of average. If we fast forward in time to mid-March, now the map on the far left, which shows those differences from ASO, is now updated to include ASO data acquired on March 1st. And if you actually focus on that map and I toggle between the two, and I don't know how much delay there is on your end, I can actually see. But you can, if you look in the Southern Sierra, you can actually see that when I go from the February 1st and 14th to then updated to include the March 1, the Merced and Tuolumne, for example, are shifting into a darker blue, indicating that our model is starting to overestimate more. And that information, once we then carry that forward in time, is basically going to update the bias correction scheme for future time steps. So we're learning iteratively in time, updating the model as the case may be, as we get more and more information from ASO. And to have that spatially across the Sierra is really where we can start to get to what I've been fantasizing about for a long time, which is to be able to apply bias corrections into these basins like the Cosumnes, the McQuilikin, the Stanislaus, that weren't flown by ASO. So if we can see persistence and relationships in the residual structures, then we can also extend them in space. By March 15th, if you look at the percent of average on the far right, Southern Sierra is now clicking above 300% of average. And the Northern Sierra, for the most part, is at or above 200% of average. And then by April 1, we had now for the Sierra, I don't have this on the map, but or on the screen, but about 40 million acre feet, which represents about 50 cubic kilometers of water for the Sierra, which we were trying to translate into the layperson what they could understand. And the state of California is about 100 million acres. So 40 million acre feet of water draped over the entire state of California would stand about 5 inches high over the entire state. So very large quantities of water. If you look at the residual maps again, and if I toggle back and forth a couple times, you can actually see again the error structures changing through time across the Sierras, depending on whether or not ASO had flown. So more updates here for many of the Southern Sierra basins. And then transitioning into the melt, which I put in quotations here, the quote unquote big melt. I was rather tepid in concerns about the melt this year, just from the perspective of how much water an atmospheric river can deliver to a given watershed in the Sierra. per unit time, like in 24 hours, for example, I think is quite large relative to what can be produced via energetics from snowmelt. So I wasn't real surprised to see that we didn't have any catastrophes, although to some farmers who had their land flooded, I would say they were negatively impacted. What you see here in the residual map on the left when it comes to looking at melt is a persistence of blues, and we see this commonly as we shift into the melt season with our modeling approach, which is that when you're relying on the the snow sensor network, there's a tendency to lean toward overestimation of SWE once the snow line starts to move up near the margins of the elevation of those snow sensors. So it has to do with a representativeness issue of the ground network. The percent of averages, which are shown on the far right, still on the order of 300% of average for the south and 200% of average in the north. I want to walk you through just a few more slides that show the Tableau dashboard that California DWR has pulled together that shows snow conditions as well as full natural flow forecasts for a variety of watersheds. These are screenshots, but if you go to the actual link for it, which I should have put on the screen, but I can put it in the chat, you can click on a given watershed. Maybe someone has already shown this in this workshop. I haven't been able to attend all the talks, but the plot on the bottom is what I want to bring your attention to, shows a number of different snow products. The iSnowball 8 M3 Works is the orange line. Snowdas is the green dots. ASO are the relatively infrequent blue dots. And then our product without the bias correction represents the pink circles. And then with the bias correction represents the yellow circles. And this is for the Feather River Basin this year. And you can see we were coming in much too high initially. And the bias correction within the ASO flight that occurred after our first modeling attempt did a great job carrying forward in time of bringing us more in line, at least with what the M3 Works was estimating, and more in line with the future ASO flights. So we can't know exactly what the truth was. We know from historical comparisons with Snowdas that it tends to overestimate SWE. So we were really happy with how the bias correction helped us here. And it gets updated through time. So you can see that where we missed the mark here, we get updated from that last ASO flight. And that helps us then moving forward in time to the next estimation date. Again, this case for the Tuolumne River Basin, so moving from the Feather down to the middle part of the Sierra, you can see those same time series, and then our bias correction estimates in pink, and then with bias correction in yellow through time. And you can see how the algorithm is adapting and learning as we get another ASO flight, then the bias correction is brought down closer to that ASO value, and that carries forward in time between the ASO flights. And then to show the kern down in the south, just to kind of cover the Sierra geographically, again, you can see how we really missed the mark with that first estimation on February 1, and then with the bias correction from ASO, it's really pulling the SWE estimates closer in line with the other products, and then also carrying forward between the ASO dates, allowing us to do that bias correction both during the accumulation season and during the melt season, and broadly across the Sierra. So I'm out of time, but I wanted to just sort of illustrate what my perception of how this modeling system can contribute to many of the others that have been shown in this workshop, which is as a fusion system to bring together satellites which have the benefit of a large spatial extent, relatively high temporal frequency, continuity with now decades into the past, and efficiency from a cost-benefit analysis. The ground sensor data, which has the benefits also of accuracy, of frequency and time and continuity with several decades into the past, and then bringing together the airborne data, which gives us a real benefit in terms of accuracy and now increasingly spatial extent. And so I see this fusion system as something that can continue to benefit from advances in sensor networks on the ground, in future satellite missions, and as ASO continues to expand, leveraging that ASO data. With that, I can take questions.
Great, thanks, Noah. It's good to see the ASO data now spreading out all over the Sierras to match your extent, finally. Let's take one quick question over here from the room, and then we'll carry on.
Hi, Noah. I'm the East Side obsessed person. And I think you've done some work with LADWP and the Mono Owens watershed using your product. Given that they don't have the especially in the Owens, any ASO history, how have you been able to look at the Owens River watershed and the forecast that they developed versus what might, if you know, were you able to do some corrections and help LA understand that their forecasts tend to overdo it in wet years, and maybe with ASO, they could come in, have a better forecast if you had a chance to analyze this year's data?
I'm going to share with you somewhat of a stream of consciousness from memory during the actual operational time of the year, where when we were looking at the Owens, which we look at closely, and other eastern basins, we're trying to see from ASO data that covers into the east if there's notably different bias behavior in our model in that area. We're very hesitant to apply a bias correction model that's developed from data on the west side to the east side of the Sierra, given how different it is climatologically and meteorologically, I should say. So we did, I don't have a pointed answer to your question, but we did take the opportunity to look at some bias structures, and during some of the operational periods this year, we did separate out the east side into a different into a different category and had its own bias correction approach. The maps I showed, I believe ASO, and someone in the room can correct me, flew some eastern basins this year, and I think we were learning from those to try to pooch our understanding of bias structure over other parts of the east based on where we had those data. I want to say the Walker, but I can't recall off the top of my head.
Yeah, we did, Noah. We hit the Mono basins as well as the Owens basins 3 times each this year.
Yeah, so I just didn't have them on any of these maps, but I wish Leanne was in the room. She would have reminded me that we were developing separate bias correction schemes for the east side based on those data.
That makes sense. Great. Thank you, Noah.
Yeah, I'll stop sharing.
Move on to the next speaker. We have John Woodill from Oregon State University, and he's going to be talking about water supply forecasting and inserting ASO data into one of the forecast models here. So we can see your screen. But we can't hear you.
There we go.
Oh, there we go.
Hey, I apologize. Let me just full screen here.
No problems. Looking good.
Yeah. All right. That was great. No, thanks. There's going to be a little bit of overlap what we're doing here. So it's really kind of cool to see what Noah's up to. Hi, everyone. My name is John Woodill. I'm a research associate at Oregon State University, and I'm going to be presenting some work, some very early work on trying to integrate some of this ASO data into water supply forecasting, in particular, a model that was developed through the USDA called the M4. Now, I just want to point out that mine primarily am an environmental economist and a data scientist, so I certainly have a great group that's helping me work on this. Matt Titus is also a data scientist and mathematician who's been helping with some of the modeling. Lexi and Angus are hydrologists, so they've been helping sort of discern some of the results, and they've been a big help in informing, snow melt and also how it's going to feed into the stream gauges and water supply. And then James Watson is associate professor at Oregon State and my advisor, and he's been helping. He helped to sort of develop this project and kind of get things rolling. So I've got a great group helping with this. I'm very excited to present this work today, and thank you for the invite. So I don't have much time, so let me go ahead and get started. So first off, I don't have to tell anyone here, we've seen significant impacts of snowpack in the western regions here. We see as much as 20% decline. This obviously has downstream impacts on stream flows, which then lead into the availability of drinking water, crop irrigation, reservoir storage, and even regional hydropower. Now, there's a couple different ways to sort of utilize snowpack and integrate it into predicting stream flows. And this gives us the ability to estimate at a certain date what the annual water availability will be for that year. Currently, the way that especially M4 is sort of set up is they utilize snowpack station level estimates, different runoff projections, precipitation, temperature impacts, storage levels, these sort of things, additional like lag stream flow data. And then they're able to project out what they expect basically the stream flow is for the year, which helps water resource managers and people sort of idea about what the expectations for the year are. But sort of the limitation with this is that we're dealing with station level data, and that's where the ASO SWE data really comes in, because it gives us a better spatial resolution that provides a more accurate and robust snowpack data for observations. So the idea here is to try and fuse the two together. There's a couple challenges that come with the M4 modeling. As I mentioned, it leverages environmental data, but this also it leverages environmental data. So again, precipitation and snow station data, and it uses principal component analysis. It gives it the ability to do feature selection, ensemble predictions for a variety. There's like 10 different models in this approach. So things like linear regressions and quantile regressions and neural nets and random forests and all this. And so they sort of just bin everything together and project out ensemble predictions. But again, the limitation with this is that they're using these SNOTEL station level data, which doesn't give kind of an idea of the entire snow pack. But and this also lacks high spatial resolution. But the other issue is that the way this model functions is it actually needs a lot of data. All models need a lot of data, but this one, you're only getting one observation per year. So you need at least 10 years of data. More likely, we need 20, even 30 years of data. And so this also creates a challenge when we're trying to integrate ASO into this model, because we don't have discontinuous timeframes and it lacks year-to-year consistency. And so if we could devise a way to integrate a nice time series of ASO SWE data into the model, then we can test and see if it actually helps improved water supply forecasting. So that's basically what we're trying to do. We're trying to assess how the high resolution ASO SWE can help improve M4. Is it a data set that will really help us predict the stream flow predictions for the year? So we're going to utilize all of the ASO records for the Tuolumne Basin here, and we're going to create a synthetic ASO data set using machine learning and different relationships with environmental data. So the idea here is that what we want to do is say, I want to predict what the snowpack is on April 1st. And we use ASO as a training set, and then we predict for April 1st. And then we use that information and then throw it into M4. I was hoping to have some M4 modeling results to discuss today, but the chunk of my talk is going to be how did we develop this synthetic ASO data set using the observed records at this point. So my case study here is in Tuolumne. And I'm just going to generate, for sort of simplicity in this talk, about 10, 11 years of data from 2010 to 21. I'm going to show you how I get there. Okay, so the type of data that we're ingesting into a model, in order to sort of measure the stream flow, we obviously have stream gauge data. And then we have ASO data in this region for 2013. And then 2016 to 2023. There's no SNOTEL stations in this region, but there are snow station data that I just got a hold of a couple of days ago. So we're going to hopefully be using that. And then I've heard a lot of talk today about PRISM. This is out of Oregon State. It's just a fantastic data set because we get daily records for precipitation and temperature. So we're going to use that. We also have elevation to sort of understand how elevation impacts the different temperature effects as well, along with precipitation. And then Lexi had a great idea to use the land cover or national land cover database to categorize the individual pixels, so we can get, what type of land is in that pixel. Is it forest, desert, or whatever it needs to be? So this is the type of data we're using. The model that we're using is a neural net, which are fantastic when we have a lot of observations. At this point, we have over 20 million observations for our training set, which is great. And the left-hand side here, or the dependent variable in the net that we're going to try and predict, is ASO SWE at the current resolution, so 50 meter by 50 meter. We haven't done any scaling, but we're currently at the resolution that's available through ASO. Now, the type of features that we have that we're using to predict this ASO SWE are latitude and longitude for each of the pixels. And we had this idea to sort of think about a snow day. How many snow days have occurred since the previous year, say September 1? And a snow day in the PRISM data set is just when is temperature below zero and when is precip above zero. And so we just basically count those up from September 1st, and that gives us an integer for the model. The other thing we did is we did the same thing with temperature and precipitation. We just basically sum up the entire temperature distribution from September 1st until the data point that we have available within ASO. And then we have a couple controls as well. We have things like the month that the ASO SWE flyover was observed. We have the day of the year, the elevation again of the individual pixels, and then this land cover database. So we throw all that into a neural net, we train it, and then do some cross-validation through using this checkerboard technique, where you just take a training set of, say, your black checkerboard cells, and then you test on the white cells, and then vice versa, sort of average that out. And we get around 70% R² plus or minus 4%, depending on the training and test set. RMSC was very similar across the training and test set as well. So as sort of a first shot, I just finished this last week, so I was really happy to see we're getting some variation explained in the model, especially when we're doing this cross-validation that sort of takes care of spatial order correlation. So I feel pretty good about where the model is. There's definitely some things that we need to add to help improve this, but this is the current status of the model. And so to make a prediction, in general, our preferred day for trying to predict the snowpack is April 1st. So we just pick April 1st as our day of prediction. We grab the latitude and longitude, the snow days from September 1st until April 1st. Same thing for temperature, same thing for precipitation. The month here is just going to be April. We zero everything else out. We have a day of the year with elevation and then the land cover database. We backfeed it through the neural net that's been trained and saved. And then we get predictions of ASO SWE for April 1st for 2010, 2011, all the way up until 2020 at the ASO spatial resolution that we currently have available. So this is how we can generate a prediction. Now, with the PRISM data set, we can go all the way back to 1980, which is really nice. So we can have 30, 40 years of data, which is fantastic. And we can still keep the same resolution for this. So this is going to allow us to build a synthetic data set that we can then inject into the M4 model, which is really what we need to do. So let me kind of show you what some of this looks like. So this is the Tuolumne Basin here. So across, I just mapped all this out from 2010 to 2013, and then threw up some maps here for April 1st. So you can see basically some of the highest snowpack that we have available, and then some of the other ones a little lower. The scale, it's kind of hard to see the scale in some of these, like 2012 and 2016, 2020. I need to do some adjustments to that, but you can kind of see, like, we are able to generate a synthetic data set that we would expect to see for these years. But that's also to say that we have no ability to ground truth this currently. So we sort of take this is a synthetic data set, but we want to use this for our M4 modeling. Naturally, the next thing that I want to know is, where's the model wrong? Where are we missing? And so I just grabbed the residuals or the difference from the true and the prediction. I just calculated distribution, and I tried to find those that are outside the basis two standard deviations. And so you can see this on a map. I've just thrown up some of the gray dots within the Tuolumne here. And you can see it's kind of available along the ridges here. So we still need to investigate this a little bit, and we got some ideas about trying to clean this up. But I think the majority of these errors are missed because of maybe really high elevations and differences in grade and aspect and slope. And so these are additional things that we want to do for new data sets or for additional iterations of the model. So conclusion, ASO is showing promising for stream flow predictions, but again, it lacks this historical time series that we can get for use in M4, because M4's limitations is it really needs a good amount of data, at least 10 to 20, 30 years of a continuous time series. But I feel pretty good about the progress we've made on this sort of proxy or synthetic data set. As I mentioned a couple slides ago, we want to throw in slope and grade aspect, and maybe even do some long run projections of climate normals to try and capture that trend and changes in temperature, not just the seasonal variation, hoping that this will improve the accuracy. And then ideally what we're trying to do is our standard approach to stream flow modeling is to use the SNOTEL or station level data. And we just want to do a comparison. How well does ASO or does ASO improve our forecasting for the year compared to sort of the old metrics that or the old data that we have available? So that's really where we're going next, is to do some comparative analysis and then also move to other basins. The Tuolumne had the most amount of data, so we figured we'd start there. But again, we don't have SNOTEL and some of these things, but we do want to move to other basins and just replicate this. And this can be in the form of additional models, or maybe even some transfer learning if we don't have enough data, sort of taking what we know in the Tuolumne and transfer learning to another basin. And the other benefit to this is not just the ability to integrate this into M4, but also to be able to maybe stitch in some of the differences across years. So if there was flyover in February, flyover in March, we can kind of look at those differences and maybe predict March, or flyover in February and flyover in April, maybe be able to predict what's going on in March and just capture the trend. Again, this is synthetic data, so it's not, doesn't speak to the real high spatial resolutions that we get with the ASO data. But I do think that it might offer good tools for trying to capture the trend between flights. That's all I have for you. I really appreciate the invite, and hearing the talks, I've learned a lot about snow this week. So I've got my email address up here. I'm happy to feel free to reach out with any questions or emails, and I'm certainly happy to take any questions if time permits. So thank you very much.
Thanks, John. That was really interesting. One thing that came to mind as I was watching that is we update the M3 Works iSnowbar model with each flight as we go forward. And so perhaps that could also be another source of an April 1 image.
Okay, that's great. Yeah, I'll look into that. Thank you.
Yeah, no problem. Okay, we will leave questions to the Gmail there, if that's okay, or the Zoom chat. That's always something you can do. In the interest of time, we're going to kick along. We have 2 more speakers, both from the University of Reno, Nevada, or University of Nevada, Reno, and we are going to try and keep them to their 15 minutes so we can get lunch. All right, extra challenge, Eli. Okay, next up is Eli Boardman. He's going to be talking about sources of water supply forecast uncertainty, and it's something that he's been working on as a part of his PhD work.
Thanks, Kat. I'll get my timer going here so I don't end up talking all through lunch. Hi, everyone. I'm Eli Boardman, and as Kat said, I'm a PhD student at the University of Nevada, Reno, working with Dr. Adrian Harpold. And before I get started, I'd just like to thank our wonderful co-author team on this project, most of which are actually here in person or online. Hi, Bruce. Are you still online? But for those of you who know me, I really like climbing mountains. So this is on the summit of a mountain in the Merced watershed, which is one of our study watersheds this summer when we were doing some geophysics field work out there. And the thing that always strikes me when I'm out in the mountains, backpacking through these complex systems for days, is kind of that our models are able to capture any of this at all. Because when you walk through these forests and you see these really complex landscapes, it's just so dramatically complex and interconnected that that being able to capture this tremendously diverse and complicated system in a simple mathematical formulation is really a striking feat of science. That said, of course, our models are not perfect, and so it's no surprise that in these really complicated systems, we end up with some remaining uncertainty. How does this? What am I gonna? Can we go to the next slide? I'm not sure how this works. So to really kick things off, I just wanted to go over a little bit of terminology I'll be using. we're talking about snow drought and snow droughts. Now, in general, a drought in just the popular conception is when you have less water maybe than you would like to have, or less water than normal, whatever normal means. But what we often are really thinking of is hydrological drought, which is a low amount of stream flow, and that's water coming into your reservoir that's less than you would ideally get. There's also meteorological drought, which is when you have a low precipitation year, and often those things are related, of course. But finally, we're talking about snow drought here, and that's really a snapshot at a single point in time, say on April 1st, when you have lower than normal snow storage for any variety of reasons. And that snow drought could arise either because it was warm, and that's a warm snow drought when you have early melt or an increased fraction of rain, or it could arise from meteorological drought when you just don't get enough snow falling in the first place. So our goal in general with this project is to predict hydrological droughts and a lack of inflow to reservoirs from snow droughts. And that is the general idea of water supply forecasting in many cases. Next slide. Now, some of you may have heard my comment before. I like to call snow water supply forecasting measuring the same thing twice and acting surprised when we get a good correlation. But it's really a fantastic part, again, of saying like how these models have done so well historically is that by measuring the same water molecules when they're up in the mountains and then measuring them again when they come into our reservoir, there's been a really striking historical success of this, these seasonal water supply forecasts. However, management decisions are still often hedged against a probability of a worse than expected drought, because that could be a potentially bad scenario to avoid. So the correspondence between the snow that you're measuring in the mountains and the inflow that you're getting to your reservoir starts to break down during snow drought. In the most extreme case, of course, if you have no snow, then there's really no correspondence between the snow and the runoff. But even in a lot of these intermediate cases where you just have a dry year or maybe a little warmer spring than normal, which is of course expected to become more common in the future climate, that becomes more of a challenge as, for instance, your snow line might start to recede above a lot of your station elevations, so you lose a lot of the informative data that has historically told you how much snow is in the mountains. And additionally, non-snow processes become more important as the snow is a smaller piece of the hydrological cycle. So when we think about uncertainty, there's kind of three large categories that were originally picked out from this Western Snow Conference proceedings paper back in 1985, Schock and Peck, for the Colorado River. And the three main areas they identified were data errors, and that could be in measuring the snowpack or even in measuring stream flow, as Jeff was pointing out yesterday or one day. Model errors, which can be calibration, parameterization of your model, or just the model not capturing everything that's going on in that tremendously complicated landscape. And climate variability, which in this case, we're going to be mainly thinking about post-forecast precipitation, but could also include, a warmer spring after your forecast or any other sort of thing that is in a weather forecast that you can't predict at the time of the initial forecast run. So in this project, we're kind of trying to recreate this forecast uncertainty partitioning plot, updated a few 4 decades later, and additionally, trying to frame this plot instead of just over time, frame it under different snow drought uncertainty conditions. Finally, we'll be looking at avenues to reduce that uncertainty, because if you can partition the different sources of uncertainty, then you can potentially identify which new technologies, hint ASO, might be able to reduce that uncertainty going forward. So we often talk about uncertainty, myself included, as some sort of negative thing. We need to get rid of the uncertainty. We need to reduce the uncertainty. But on the other side of the coin, I want to point out that uncertainty is really important, because uncertainty is inherent in the way these systems behave and in our ability to predict them in the future. In fact, if we make predictions that don't include uncertainty, that's not prediction, that's prophecy. So the defining features of prophecy versus prediction is that prophecy or deterministic picks a single value and says this is the future reality. And that's frankly often wrong. It's hard to be a prophet. I know, my name is Elijah, so maybe I should try it. But And the real problem with prophecies, though, is they can lead to overconfidence, right? Which leads to mismanagement of a system. If we're really confident that there's going to be one answer, but that uncertainty doesn't vanish, it's just hidden. Whereas in prediction, we're looking at things in a probabilistic framework, and we want to be really sure that our beliefs are justified by evidence, even if our beliefs remain uncertain. Next. Now, the hardest piece of this is, what do we mean by our beliefs being justified by evidence? That's sort of a hard thing to quantify. Next. Now, luckily, Bayes, a while back, came up with Bayes' theorem, which lets us quantify our level of justification in a certain belief based on the observed evidence. And it's a little beyond the scope of this talk to get into how we do this, but basically we maximize the probability that our model is correct given the evidence by maximizing the probability of the evidence given the assumptions of the model. So in the seasonal water supply forecasting framework, the way we're doing this is we bring previous years of ASO data and other previous weather observations into a Bayesian calibration framework. And that gives us an ensemble of likely models as well as a distribution of residual errors. Then we can combine those with a current SWE observation in an operational sense to create a real-time predictive distribution for a future forecast. Now, just because something is probabilistic or statistical doesn't necessarily mean we should believe it. I threw this slide in just for fun yesterday because, I love the discussions always of R squared. It's really fun when we get this, measure the same thing twice, get an R squared of 0.99. But at the same time, all four of these plots have exactly the same R squared. And hopefully it's clear to everyone why, say, this plot in the bottom right is probably not a good model of those data. So I don't really have an answer here to should we believe statistical models. The answer is maybe. But I just want to highlight that really looking at the data and trying to understand the physics behind the system and exploring that conceptually as well as just numerically is always going to be an important part of ASO predictions. Now we're ready for next. So this is our conceptual framework of how we're going to be evaluating the uncertainty in these forecasts. And each of these is calibrated and then predicted separately. So we're using different calibrated models based on the snow pillow index versus models calibrated to the ASO record. And with those, we can either propagate through a historical precipitation distribution, like we would in real time when we actually need to capture that post-forecast variability, or we can propagate through a single precipitation measurement from the actual Tuolumne Meadows gauge that was measured in that year, and that's a backcast scenario. And by comparing the different distributions we get out of these three different simulation modes, we can isolate uncertainty from the snowpack quantification method using the snow pillow sites versus ASO, uncertainty from variability in the post-forecast precipitation, and the remaining uncertainty in the hydrological models. So with that same color scheme and conceptual layout, we now have our result plot on average across both watersheds and all four models. On the x-axis here, we have essentially a snow drought index. So it's the fraction of pre-April precipitation remaining as SWE on April 1st. So on the left side, we have very extreme snow drought conditions. Most of the snow has already either melted or fell as rain. And then on the right, we have almost all of the snow remaining on April 1st. Now, as you move up in model skill towards a better model, so the ideal model would have 100% skill. As you move up, you remove certain uncertainty sources. And so on average, we see that about 48% of the total forecast uncertainty is from the hydrological model. And that kind of makes sense because that's just, those are really simple models and they're not capturing the full complexity of the system. About 14% is from that April to July precipitation variability, but around 38% is from the snow pillow-based quantification method as compared to ASO. Now, I also want to note that the Tuolumne and Merced are pretty well instrumented compared to a lot of the sites I'm working in, like in Wyoming, that have basically no snow tells even anywhere close to the mean SWE elevation. So we would probably expect that improvement from moving from the snow pillow index to ASO to be even greater in less densely instrumented watersheds. Now, as you move to more extreme snow drought conditions, the forecast is losing skill. And that's what we expect, again, as we see that decoupling of seasonal runoff from the April 1st snow volume. However, the ASO-based forecast degrades almost half as, twice as slowly or twice as good as the snow pillow index. And that also fits with what we would expect from like the Livna and Badger paper I mentioned earlier, where as you have that snow line moving up above site elevations, you really need to rely on more of the remotely sensed data to still capture the remaining snow skill. We can also compare this in the dry snow drought scenario, looking at those individual individual uncertainty sources. And we see that in general, all of the uncertainty sources become more important during snow drought, and especially during these dry snow droughts caused by low precipitation. But in particular, the post-forecast precipitation variability really becomes a dominant driving factor in those low precip winter scenarios because the potential spring precip is just a larger fraction of the water balance. So again, a lot of these results are pretty intuitive, but I think it highlights a really important part of the forecasting paradigm where we can actually model uncertainty sources as a function of the snow conditions. So for my final key points here, kind of going from more conceptual and broad to concrete, I really believe that quantifying uncertainty is equally important to improving absolute model skill for making forecast decisions. Because if you have a value and you claim that it's really accurate, but you can't quantify just how reliable it is, then it doesn't necessarily matter whether it ends up being correct if you couldn't trust it in real time. Secondly, the uncertainty will likely increase during more common snow droughts in the future, but that loss of skill can be ameliorated by incorporating things like ASO and these distributed full catchment SWE measurements. Finally, looking at ASO specifically in the Sierra for the April to July forecast, even during the coincident extreme warm and dry snow drought conditions, at least 32% of the total forecast uncertainty is attributed to not using ASO and instead using the snow pillow index. So with that said, I would be happy to talk more about this. You can find information at mountainhydrology.com or talk to me any point in the conference. Thanks. I'm happy to take any questions.
Yeah. How do you separate the effects of uncertainty from bias?
You're talking about like bias in the hydrological model?
In the measurements. So for example, the precip gauge, they never overcatch.
Yeah. So that's a great question. And when I mentioned, one of the sources of uncertainty being data error, so that can include errors in things like the precip gauge or in the in the estimation of full natural flow inflows to the Hetch Hetchy Reservoir. So both of those uncertainty sources are getting baked into the statistical errors of the hydrological model in this case. So our model itself models the relationship of the actual full catchment precip to the gauged value. And since that's not a perfect relationship, it's increasing the overall uncertainty of the statistical model.
Great talk, Eli. Thank you. All right, we've made it. The final talk. You made it to me. You haven't survived me yet. Yes. Okay, we have Adrian Harpold from the University of Nevada, Reno, and he's going to be talking about trees and snow, and trees and snow with no title.
I've graduated to getting a talk with the TBD title, which I don't know if that's...
I could have come up with a better thing for TBD, but I'll leave the bad jokes to you. All right.
And I gave a little tongue-in-cheek title here, but it's being very sort of...
You need a microphone.
I can yell really well. Uh-oh. So my talk is, the tongue-in-cheek title I was going to give was Snow Farming, because what I'm interested in this talk is exploring how changes in forests affect our snowpack. And the tongue-in-cheek title has to do with most of this work being on Forest Service land, Forest Service Department of Ag. One of the really important ecosystem services we get out of Forest Service land these days is water supplies to the lowlands. And if you think about a place like California, there's more money associated with that water than with forestry practices these days. It's a better sign. Yeah, and we're doing the Mac to Windows conversion somewhere in this. Oh, there it is. Okay, I fully expect a bunch of things to break along the way here, but all right. Okay.
She's got to go through all the gyrations to make everybody be able to see. Is it good, Mom? Awesome.
Can I do the forwarding? Doesn't look like it.
There it is.
Oh, too well. Can someone? Okay, so I'm going to pick off of Ronnie, who I've never met, but I'm going to find you after this, and Liz Wagtendonk's talk. I don't think I need to do any background, but this really amazing GIF that I wasn't clear who made this, but just very dramatic, these recent fires. We're talking about one of the most important reservoirs in the whole California system. And we care about interactions between forest and water. I think that's been pretty well made through this last few days. So I will give you my take homes up front with some weird animations going here. So picking up on Liz's talk, these disturbances are really complicated, hard to measure. And as a result, it's really hard to simulate and predict these things without sort of tree scale information. And kind of as a consequence of this, we really lack some of the tools that we need from a forecasting management standpoint to deal with these big forest disturbances. Yeah. Why is this so difficult? I think it's the interaction of just different types of disturbances, different severity of those disturbances, and then all these uniqueness of place issues that are so common in the environmental sciences, right? So we can have things like insects, drought, fire, human-caused restoration. Those can be moderate, they can be low severity, they can be stand replacing, and then we're doing that in places with very different pre-existing topography, forest structure, ecosystems, right? And so when you think about the complexity of this, it becomes very difficult to find general rules. And I think LiDAR, I made this figure a long time ago, back in my Boulder days and pre-ASO, and have just been showing this for a long time, because you can go out in a landscape in Colorado above Boulder, and you can walk around the LiDAR field and you can see these incredible patterns in the forest, right? Just right next to each other, you have places where you have this very clear warm edge, cool edge, radiation control, wind redistribution, and then more classic interception. So when you think about these very fine scale, sort of meter scale processes, you have a lot going on in these forests draped over complex topography. So as an example, canopy edges and canopy gaps have been recognized over the last 5 to 10 years as a big driver here. So on the higher radiation sides of gaps, you tend to get warmer edges, cooler edges on the lower radiation sides, but that varies a lot based on how big the gap radius is. So these sort of moderately sized gaps tend to give you the most cool edges, and then you get more warm edges on smaller and bigger gaps. So complexity associated with gaps. And this is kind of, I didn't know Liz was going to give a similar talk, but this is kind of picking up some of Liz's stuff in these next few slides. So the complexity of post-disturbance change, right? You have standing dead trees. These dead trees do a lot. They shade, they emit long-wave radiation. As Nolin was suggesting, they shed black carbon, they change the albedo. So you can see this with LiDAR data again. After a fire in 2011, you see quite a bit of lost canopy. But actually, if you go even farther past that, there's more of a loss of canopy 3-5 years out from the fire than there is immediately after. This is in New Mexico. Understory regrowth is sort of one of these things that hydrologists kind of pretend doesn't exist, but we know that it does. We also know that places adjacent to each other with very similar fires may or may not grow understory. And if you go walk in these places, the way that aspen comes back after these fires is bananas, right? And it can really get to the point where it is affecting snow processes. It's not completely buried, or you're in shallow snowpack zones, you're changing turbulence patterns, you're changing radiation. These kind of things matter, especially several years after fire. So back to my initial point, you have all these different kinds of disturbances, different severities of disturbances. So let's look at an example from one of my favorite places, Seychen Watershed in the Central Sierras. They went out, did a big forest project where they treated this area. You can see the forest gaps here in the imagery. And then in a paper that was led by Kia-Tek Heng, that recently came out in Earth's Futures, we show kind of interpretations of this change via a bunch of different kinds of remote sensing. And I won't go into this much. Liz kind of touched on this in her talk, but you're going to learn different things and come away with a different understanding of this disturbance depending on which remote sensing technology you're using. Which really suggests that none of these technologies is really the silver bullet. Optical has a lot of issues with forest disturbance because you're seeing the trees beforehand. Now you're seeing the snow underneath the trees that you weren't seeing before. It's very difficult to account for that. Radar, we just don't have the technologies to do this at a fine enough scale. So in many ways for forest structure change, we're left with LiDAR. LiDAR is great in very good structure, fine scale structure information, but has a lot of temporal issues. It's a challenge to ingest into models, et cetera. All right, this is a little bit of a busy slide, but how would you go out after a fire and say whether snow changed or not? We're basically left with the tools that we've had since the 1920s, which is either we pair a disturbed and an undisturbed catchment, or we go out pre and post, and we look at how things change before and after a fire. This is really, I mean, someone can correct me if I'm wrong, but I don't think we have too many other ways to do this. We can hybridize these, and we can hybridize them sort of within computer models. I think the future is a hybrid approach, and I want to point to this really nice paper by Park Williams, where he develops a Bayesian approach that kind of takes advantage of control sites and pre and post fire to give a sort of time series of how things change years since fire. Why is predicting this so hard? It's because you have a lot of processes going on: interception, shading, reduction in wind speeds, emission of long-wave radiation, blowing snow and snow redistribution. This is the classic figure from the Varhola review paper, where they take all the studies across sort of North America, and they show through disturbance experiments on the left side. So think of these as pre and post, and then comparison with controls on the right side. So think of this as sort of a control paired watershed approach. These general patterns, right, where more snow with bigger snow forest reduction, more snow with bigger forest reductions, faster melt with bigger forest reductions. The point here that I want to draw your attention to is the scatter across these plot scale measurements, right? Scatter that really is from a positive change to a negative change. Really a tremendous amount of uncertainty if you were going to try to use a slice of this to make some kind of management decision. So one of the tools that we've been using to address this real limitation, this uncertainty associated with these tree scale processes, is a model that runs sort of at the tree scale. We're not the only people doing this. There's a nice model out of Switzerland called FSM2, which really kind of matches our results in many ways. So this Snowpocalypse model was developed by Patrick Broxton about 6 or 7 years ago. And the idea is we can ingest the snow off LiDAR forest structure information. We can use some of the snow on LiDAR information to train the model, and we can get a sense of these tree scale processes. Oh, it was going so well. Will you forward? Thank you. So we validated this with observed snow on data. There's a lot of simplicities to this that I'm going to skip through. If you have interest in this, there's published papers and whatnot. The point I want to take away, and I guess I didn't get the citation on here, but this is a paper led by Patrick Broxton in, I think, 2021, where he took our Snowpocalypse model, he ran it explicitly, that's the black dot, so he ran it at that native 1 meter resolution. He then chunked it out into just canopy and no canopy, which is the red dots, this 2 environment simulation, and then he chunked it out into 4 environments that had a warm edge and a cool edge. And the take home here is that when you are only using open and under canopy, you simply cannot get the energy dynamics correct compared to the explicit simulation. So you're generally putting more shortwave radiation into the model, and you're melting the model earlier, which is a common problem we see in land surface, coarser land surface models. So what's the value of this? Well, we now have a model that we could go pre and post disturbance, take the LiDAR data, feed it in, and tell you something about how snowpack changed. So back to New Mexico, we can do this with the standing dead trees and this snapshot after a fire, and we see this spatially complex result where some places get more snow, some places get less snow. And that actually is pretty consistent with what we've observed in the field. Okay. The other thing that we can do, and I'm going to try to wrap it into the last bit of this talk, is we can do virtual forest thinning experiments. So because this is sort of a tree scale model, we can take out individual trees, and then we can run those two versions of the model and look at the difference of them. And it's way easier to do this than permit actual experiments in the field. So we've done this a lot. This is some work by a former postdoc, Sebastian Crow, where he ran this across the west shore of Lake Tahoe. So this is just a small, tiny domain of the western US, but you can see if you look at these blue dotted lines that are sort of air bounds, or the variance, I guess, that we saw, bounds basically all the previous observations across the world. So my takeaway here is between climate, topography, and vegetation structure variability, you can basically get any answer you want over a pretty small area. So where are we headed with this? Well, I would argue that there's three real values here. We can design forest treatments, we can evaluate forest treatments, or we can forecast post-disturbance water supplies, which I think has been more of the focus of like Ronnie's talk and some other talks. So I'll focus more on these first two. Clearly we have better models, better observations than we ever have. But I recognize that snow is an incremental step to saying something about how streamflow changes. So we're taking this on because I would argue we have better data. It's a simpler process than streamflow change, which we're also taking on, but I think it's a hard one. So this is a recently published paper by Gabe Lewis, who's in attendance today. Again, just a sort of example here of the east and west shore of Lake Tahoe, following removal of all the trees that are shorter than 20 meters tall. The west shore of Lake Tahoe, oh, that's my timer saying I should be done. West shore of Lake Tahoe gets more water, east shore of Lake Tahoe gets less water. This is really important to translate to the water management community. And so we're building out sort of landscape scale predictive tools. So I call these decision support tools. Some people hate that terminology, but I think it really gets at what these things actually do. All right, last set of slides here. Kara Piskey, another former graduate student of mine who's now with ASO, we developed some new processing tools to look at forest snowpacks, especially snowpacks under the forest canopy. What Kara did was effectively treat this like previous plot scale measurements, where she did a control. So she looked at an open control, and then she looked at the percent change in a 30-meter plot between the average of that plot and an open control. So this is basically like how people would do these sorts of experiments in the 1950s, but now we have like 1 million points. So the black points are the Varhola, and the blue points are our LiDAR data. And so it's sort of like 20th century meeting 21st century. I'm gonna skip this slide. The sort of upshot here is that using this and then some random forest modeling, we're able to classify low, moderate, and high response areas to forest loss. So I think the idea here would be, if you're going to go out, and these are the forest treatment polygons. So if
This afternoon, we've got a couple different sessions looking at integration of ASO data into operational models. We will start with a... I'm just the photographer, keep going. We'll start with a few presentations on some of the ASO internal model work. We'll start with the M3 Works fellows talking about the iSnowbow model. You have a special treat not on the agenda discussion about ASO density evaluation and development. Yeah, Kat. And then Dave Gotchis will discuss WRF-Hydro integration and forecasting. We'll have a quick break. And then in the afternoon, we'll hear about River Forecast Center experimental modeling, as well as from Turlock. And we'll try to wrap everything up by around 5. And then For those of you interested in going up to see the snow study site at the Gondola Mid Station, 5:20 is the time to go for that. And then the dinner will be at the Mid Station restaurant. So you'll be up there a little early just for dinner. And that, I believe, starts around 6. I'll confirm that. Anyways, we'll get going here. I'll hand it off to Mark and Micah. Just Mark? All right.
No, it's both of us, actually. First, this is science in real time. I have a theory about the clicker. That's that Kat behind the scenes is turning it off for the people that she wants to watch just stumble around. So, yep, she wanted to watch me stumble around. I'm not smart enough, Kat. Is it just? Okay. Yeah, Mark Robertson. I'm going to be talking about the modeling component of the ASO program, right? So, and the central component of that is ice snowbound modeling. Before, this is like a nice preface for this talk. I feel strongly about this. Underneath everything that we do, I mean, obviously ASO brings so much to the table. Underneath everything that we do in collaboration with ASO is the ground measurement networks, right? Everything from the beginning to the end of what we do with M3, that's the backbone. So I want to tip my cap to DWR, the work they do in California, obviously, but then also more broadly in RCS across the West. Again, without that, none of this is here. The meteorology, measuring the snowpack, everything. So thanks to them. And then also, before I get started, we're really excited to announce that Kahan Yang is coming on board at M3. So super excited about that. Yeah. Yeah. So she's coming from UW, eSciences, brings a great background, will definitely significantly increase the collective IQ. So that's fantastic. She'll start in early October. She didn't make it here, but she'll be at, I believe, the mid-November California Cooperators meeting. So yeah, ASO and physically based modeling. I'm going to give sort of a brief outline of M3, the work we do, the modeling, inputs, outputs, all that stuff. You'll be relieved to hear that I'm only going to do half of this, hand it over to Micah Johnson. He'll do the sort of the second half, which is features and improvements that we've made in the last 2 years specifically, but then since coming on at M3. So, and I should also mention Micah Sandusky. So there's 3 of us, soon to be 4. And I'll talk about a little bit about M3 works. Yeah, I hit this already. Ice snowbound model inputs, and then specifically, and this is the backbone, the ability of ice snowbound to ingest remote sensing measurements, specifically those from ASO. So, right, everybody in this room probably knows this. The big component here from our perspective, the modeling perspective, is the ability to replace measured snow depths, replace modeled snow depths, with measured snow depths. So that's the backbone. You've seen these plots plenty. The blue line here is modeled basin total SWE volume. Of course, when ASO flies, we replace modeled depths with measured, and those are the snaps in the blue line there, snap our basin total SWE back to reality. So that's just, I'm going to keep coming back to this idea. M3 works. We model 28 basins in water year 23 in real time. In California and Colorado is certainly the basis of that. Also a couple of basins near to us in Boise, Idaho. So the Boise and Big Lost basins are sort of test basins, getting us into a different climate. We've learned plenty in those basins as well. I won't linger too long on this. This is sort of a water year 23 overview, going to condense that a little bit. This is the model for the 12 California basins. Actually, this might be 11. I don't think Shasta's on there. And the diamonds represent the dates of flights, and you can see the jumps in the model as we're getting snapped to reality once we get ASO depths to integrate into the model. Brief sort of timeline or history, if you will, of ice snowbound modeling. Of course, it started with Dr. Church. Maybe that's not a direct path, but I feel like you have to put him up there, and I didn't have a picture. Really it was Dr. Danny Marks who published the ice snowbow paper in 1999, which was an extension of the point model snowbow. So that's when ice snowbow really took off in the research space, but began the jump into an operational model when Tom and ASO approached Danny around 2012. They were impressed with how the model performed, specifically during the melt, and for other reasons I'll talk about a little bit later on. But that was 2012. Myself, Micah Sandusky, and Micah Johnson came on at ARS with Danny in 2016, 2017, and we started the work to move that implementation of ice snowbow from a research project to an operational platform. So around that time, when we came on, doing a model run took days to prepare and days to run for one basin. In the time we were there, we sort of extended that. I think 2018 was really the first time it was being run operationally, in my opinion. And then that has since expanded to 28 basins in real time now. At any rate, we faced the same sort of pressures at ARS that Tom and Jeff and those folks did at NASA JPL, which is that the model was never intended to be run operationally at ARS. So M3 Works was the tech transfer landing spot out of ARS, and here we are now. So I'm going to talk about the modeling system. I'll come back to this somewhat rudimentary graphic a couple times just to orient ourselves. We run on the cloud, and we have an instance, is not the perfect word to use, but I'll use it here, a basin instance, a model instance per basin. So encapsulated in that for each basin we run, right, is inputs. We're gathering inputs to the model. Then the machinery of the model itself, we're distributing those inputs, actually running ice snowbow, processing the outputs along those. In that timeline, we ingest and update state variables as ASO provides them. We do a lot of model validation, and then of course outputs. So the neat thing is this is on the cloud. I'm being chased by bugs here. That's okay. That's Tom. The neat thing is with our setup, these scale sort of horizontally, if you will. So, you know, it doesn't matter how many basins we run, we can run that in the same time. We can run the entire West once all that's set up in the same amount of time. So a little bit about ice snowbow itself. It is a physically based, these are tough, right? We got a tough graphic for energy balanced snowpack model and some bullets, but I'll go quick. It's a physically based energy balanced snowpack model. So it solves energy and mass fluxes to create a model snowpack. It is a 2-layer model. Those layers don't correspond to anything, you know, snowpack layers, they don't correspond to any snowpack layers in the strict sense that we're used to thinking about them. If you dig a snow pit, the upper layer, it's a simplified way to do it computationally. The upper layer is interacting with the atmosphere and the lower layer. The lower layer is interacting with the upper layer in the snow, or I'm sorry, in the ground. So those are the layers. One of the really powerful aspects of ice snowbow, and this was all Danny Marks, was it was written even back in the 90s with the idea that remote sensing measurements were going to come online eventually, were going to provide much better information than strictly model. And in the architecture of the model, it is really straightforward to replace model fields with anything you want. So we can replace you know, model depth with measure depth, the same with albedo, the same with temperature, anything, any state variable you want, you can replace. Of course, we can't necessarily measure snowpack temperature everywhere, but who knows what might come on down the line. And then the other big plus is snowbow itself is written in C, but it's wrapped in Python, and the rest of the architecture is in Python. So development happens quickly. It's very readable language. There's a lot of support. So that's a big benefit as well. So we talk about an energy balance model. This is an example to give some idea of what those fluxes look like at different points in a basin across a winter. I think this is Merced, I'm not sure. But we're breaking out these energy fluxes into 4 different components. So we've got net radiation, sensible latent heat, and the snow soil flux there. So the blue box plots for each of those categories are a midwinter value. The orange it's from this year. The orange is from a pre-atmospheric river. And then the red box plots represent that atmospheric river itself, the mean values from that day. And then we also have a spring, April 15th day that we're pulling out. And you can see, we talk a lot about this, right? But net radiation, the spring component far outstrips everything else. So, right, that's when we talk about albedo and all things like that. So you can see the comparison of these different values for some of those fluxes. So I'm going to skip this. It's the same information. So we'll move shortly to model inputs here, but the standard operational configuration for running ice snowbow, we use NOAA's high resolution rapid refresh atmospheric model for inputs. That's a 3-kilometer product. We use the 0 hour of that forecast. NOAA, the HER model does use assimilation of measurements, importantly weather radar. It's the highest resolution operational product that we can get our hands on. Those are hourly inputs. The model has daily outputs, and the standard configuration is a 50-meter pixel resolution. So some other considerations here. Ice snowbow does account for terrain shading, influence of vegetation, sublimation and evaporation, compaction processes, and liquid water processes on compaction and energy transfer. Importantly, it does not account for wind redistribution, although that's something we're working on and will shortly. But the asterisk, right, it does account for wind redistribution once we integrate ASO measurements. So it does in that sense in our implementation, but not on a daily basis. It also does not account for canopy interception. So that might be an area of future research. It does not right now. So a bit about static inputs. The DEM we use the ASO measured DEM where we can. Our model domain is a rectangle, and of course that would be a tremendous waste for ASO to fly. So we do pull USGS data to fill in where we don't have ASO. Vegetation type, we pull from the land fire data set. Vegetation height, and Micah Johnson's going to talk more about this in a little bit. We are now using ASO measured vegetation height, which is going to be and will continue to be a huge improvement for us. Dynamic inputs, that's mostly from NOAA's HER model. I'm not going to go through all those. Far and away, the most important one is precipitation. Uncertainty in precipitation drives everything else. The other uncertainty in the other is secondary, big time. Other inputs, snow depth, of course, from ASO, and albedo from ASO when those are available. Few more words we got to say on inputs. Any outputs are only as good as inputs. So there's a lot of uncertainty in the model itself. There's been a lot of research that's been done. The model performs very well at stations when all the parameters, all the inputs are measured right there. But of course, an atmospheric model across Basin-Scale has a lot of uncertainty in that, and so, right, we get uncertainty in outputs. We can use any gridded weather product, so we're not limited to HER, GFS, European models. And along those lines, we're now producing snowpack forecasts driven with the GFS forecast. So that was a sort of neat development. I think Mike is going to talk a little bit more about that later. Yeah, he'll talk more about that later. And then, I don't know, I forget the others. Okay, here we go. So we can run on 1, 3, or 6 hour time steps. We're sort of driven to run on a 6 hour time step with the GFS because that's all that's available. Station data was Station data was what was being used to drive the model originally. It's just obsolete for operational use now. Could still use it in a research setting, but it's not functional on the scale we're doing. A little bit more about distribution. So from 3 kilometers from the HER, we distribute all the variables down to a 50-meter grid. Importantly, the wind is handled separately. Wind is a little more tricky than just air temperature or precip, right? So we first downscale the wind using Katana, which is a package that the U.S. Forest Service developed for wildfire applications. So we first go from 3 kilometers to 200 meters using Katana, and then a simple, is it inverse distance weighting? I don't, to go to 50, it doesn't matter. So yeah, that's wind. Moving on. So that's the inputs. So this is the exciting part, right? Other inputs, dynamic inputs from ASO. And like I said, of course, everyone here knows the backbone of that is measuring, or is ASO measured snow depths. So this is the Roaring Fork. I was looking, there's probably better ways to show this, and I'll work on that for next time. But when you go back in your head, if you go back to the basin total SWE line, and we get a flight, and this happened a lot this year in California, where the model volume was pretty close once we integrated ASO depths. But it's a little deceiving because every time you're boiling too much into one line, every time we get a flight, the snow is rearranged by the measurements. So this one is a fairly good look at how much the structure changes. Obviously, you can see in the Roaring Fork sort of sub-basin there how drastically different the structure of the SWE depth is there. And of course, the really smooth places are where there was not measurements, and that's model alone. And we already hit that one, so I can skip it. So the next component that has been a huge improvement for us as well is including measured albedo. So this is the Dolores Basin here. The model albedo is tough. It's tough to measure. It's tough to model. There's a lot of components. We know it's important for melt, especially in the spring, and it's often quite wrong, and we know it. And we've developed internal tools, knobs we call them, to force albedo in a certain way, but it requires prior knowledge. And so there's a lot of improvements to be made, and that is ingesting ASO measured albedo, right? So this is near infrared albedo in the Dolores. You can see spatially there's just a huge difference in values there. Here's another way to look at it from the Truckee Basin from this year. The dark blue line is the mean albedo, visible albedo in the Truckee Basin across the full snow year. But when you see that thin green line where the albedo jumps up, in this case, is when an ASO measurement came in. And you can notice two things. One, several things. One, how far off the model albedo was in the first place. Second, how narrow the distribution was. So once we get measurements, it really spreads that distribution out. So this is a huge improvement for us. And I think Mike is going to talk a little bit more about that as well. So that's including measurements where we can. We run the model, of course. Outputs, I'm not going to linger here too long. You're familiar probably with the standard outputs. They are daily, and it's all the snowpack state variables are output. So there's a lot more interesting work that we could do beyond just depth, SWE, and density. We talk a bit about cold content, but there's also snowpack temperature. There's other projects we're looking at potentially for future years about potential snow temperature measurements that might be coming online, and other ways we can validate the model with that. And then, of course, surface water inputs are SWI. That's not a state variable per se, but that's an output as well. Coming back to this. So the other thing we talk a lot about and what we spend a lot of time on is model validation as much as we can. So we take every product we possibly can, including transportation department webcams, to try to validate how the model is doing. The standard ones, of course, ASO surveys is a big one. A time series component, the big ones, right? Snow pillows and snow courses, I guess less continuous for snow courses, of course. But we look at that every day for every basin in the operational season to see how we're doing. Snow covered area from satellite products. And importantly, we also have a testing framework that allows us to validate changes that we're making to the model. So validation is a big piece. We look at things like this, which might be, hopefully is not too boring. Merced from water year 23, we look at these sort of things internally all the time. So on this plot is Tuolumne Meadows site SWE at the station is in orange. In the model is the red line that's following remarkably well. Of course, I picked that chunk of time to make us look okay, but you could pick others where it would diverge quite a bit. But then soil temp, that's a relatively new inclusion for us, distributed soil temperatures. So, okay, how are we doing? Tuolumne Meadows has soil temp, so we can look at that, and we want to see for specific sites, did we get, or is that why we're not getting enough snow? Is that why we're getting too much snow? Did we hit the rain snow line? There's a lot of information there. A few words about station comparisons. These are phenomenal. We look at this all the time. It's important to remember, if you look at this figure on the bottom left here, it's important to remember you kind of have to cross your eyes a little bit. Honestly, it's a bit like radar data. When you try to do a comparison of a 50-meter model pixel and a station value, right? A pillow represents less than 1% of a 50-meter model pixel, and you're wrapping together a lot of processes and averaging them when you do that. And so if we're off from what a station's measuring, that might not be a bad thing. Of course, it's the best information we have, but it's important to keep in mind it's a little qualitative. It's a little bit more qualitative than I think most folks sort of understand. At the same time, there's tremendous information. We should be hitting the melt timing correctly. Those sort of things you can definitely pull from station comparisons. We do the same thing with snow courses. Of course, there's less data, but it's just as powerful. Other validation components, I kind of hit this already. We have an internal dashboard of all these values that we're looking at constantly. And the idea is, we can't correct until we get to a flight. We can't correct a lot of the errors and biases. Biases is probably a better word that we have, but the goal is to be able to describe and understand what they are when we communicate with people what the model is showing. So we look at this sort of information too. These are basin-wide mean statistics that we go through, cold content, evap, temperature. Whoops, went too fast. So we can pull apart if there's a rain on snow event, right? Are we capturing the right elevation? Do we see that in the input data? The other phenomenal sort of aspect that we have here, component, we have all these model runs for our operations, right? What we distribute across California and Colorado, what folks are looking at. But we have a completely independent testing framework of all those same basins and all the same parameters. And what that allows us to do is make testing runs. And this happened a lot this year, right? When melt's coming, of course we had snow the whole time, and then April 1 happens and we start to melt. Flights come in, we realize we're not melting fast enough. And we knew something like that was going to happen. So you go in and start changing parameters. Okay, how we want to mess with albedo, turn some knobs, play with different things, but we don't want to screw up the operational reporting on numbers, and we can do that. And when we hit a set of parameters that we like in the testing model run, we just copy it over and you're good to go. We can run from there. So I think, yeah, that's it. You're free from me, and Micah Johnson will take the rest. Yeah, I should have said this at the beginning. This is also, intended to sort of set up, Kat's probably going to shut that off for you. She probably likes me more. This is intended to sort of set up. No. This is intended to sort of set the runway and set up some of the discussion tomorrow morning. So this is kind of background for that, and whoever's here, we'd love to talk more tomorrow morning. So that's all.
Thanks, Mark. So in the last 3 years, we've been in this incredibly unique opportunity to have all of ASO's data at our fingertips. And we have it all in this great structured way so that I don't have to deal with reprojecting or resizing and getting the grids right. And we've written out this gigantic package to do this analysis. And the result of that is, I think, exponential development. And that's enhanced even further by cooperators talking with us weekly, sometimes sub-weekly, telling us where they think we might be wrong. So I'm going to walk through some of these and show you some places, and some of them you might go, wow, I didn't know that wasn't included in the ice snowbound modeling, but it is now. So This is like a timeline of those things that we've improved upon. You can see they're getting denser and denser as we go on in the years. And again, that's because we now have hundreds and hundreds of flights to go through and tweak and try to get the model parameters right. And I put the infinity symbol there because we have lots more development to do. And Dozier earlier quoted George Box, who famously said in 1976 that all models are wrong, which I firmly believe, but some are useful. So in all this work we're showing you is our goal is to be useful, not just a model. So to begin with, in our first year, we figured out pretty quickly that fire scars were going to change everything. And the creek fire significantly set the tone for that. And at the time, the work for fire was just starting to begin. A lot of people were just starting to dive in and dice up, and we have the ASO data to start doing that. But we had to make some kind of operational judgment, so we came up with a system very similar to what Ronnie showed, and we started implementing that. And you know, it worked pretty good. And we totally saw that as a operational judgment. That's how we thought of it. We just intuitively changed the parameters very subjectively, but in a direction we thought made sense. And that worked. And then the next year we were modeling the feather, and we had this event where this enormous melt happened in between flights that the model just missed terribly. And the conclusion was, after looking at albedo data with Tom, that we need a fire scar. So we took the mildly performing well scar technique from the creek fire, applied it there, and guess what? It fixed a bunch of stuff, which was really cool. And then subsequently we did that in Colorado and a few other places. That's the Windy Gap there on the right and the Big Thompson in the bottom left there. And what this allows us to do is we use the burn index to scale some of these parameters. But additionally, what we do is, Mark mentioned this, we have some albedo tools to help try to twist the knobs to get the right answers. And what we did when we set this up was we knew that there will be some interannual variability from these fire scars. So we added some tools for ourselves to be able to tweak what albedo might be doing in the fire scar based off of like carbon sloughing, which may not be there in 3-5 years, right? But we still have this tool in what we call our static inputs, which we're increasingly questioning as static. Mark mentioned our testing framework. This is a big part of why we can do all this development really fast. We can do parallel runs, we can do multiple years all in parallel, and all that allows us to do this analysis in retrospect. Once we moved over to Colorado, we realized that her precip not only had biases, but they were spatially and subseasonally dependent. So our job suddenly became, we have to look at storms as they roll out and see how the model captured them. And even that doesn't do a perfect job. But when we first told Jeff Deems that we were going to do this, he was quite nervous about it. But in the Blue River, for instance, we said, well, Jeff, if we don't, we'll be 300% off on the SWE volume. So we should probably do something. And he was like, yes, we should. Okay. So that's evolved a little bit in time. Now we have a spatial correction bias system in place that we reevaluate kind of like on a probably bi-weekly basis as we're watching the model go forward. And that significantly helps with certainly the total volume. The spatial distribution is still not where we'd like it to be. Last year we presented on the ground temperatures. We're really proud of that work. That work was not as intuitive, and in the past we've been told that the ground temperature fluxes really don't matter much in the modeling system. And after years of flights reducing the snow-covered area, we concluded that maybe negative 2.5 C, which is up there on my first bullet, is too cold. And we saw that all through the spring period, pretty much always. And then when we switched to the HER distributed ground temperatures, that went away, in part because HER includes some snow-covered area in how they derive those. So we're benefiting from a little bit of satellite product and a more variable ground temperature. And just to further confirm that for you, we went and looked at Dana Meadows just to see, like, what is the ground temperature during this time? And Frank was very gracious to call me up and say, you know, take some of those depths of those temperature sensors with a grain of salt. They may not be exactly where you want them to be. But even there, it's pretty obvious. The pink line shows that negative 2.5 is too cold, almost always. That bottom figure shows some of the snow-covered area in the Merced, I think, right? This year, we ran into this forecasted rain on snow event period that caused a lot of alarm because we had a record snowpack, and they were calling for rain up to 10,000 feet. which was quite concerning. And so the question became, what can we do with the data we have right now to better understand what could potentially happen in the next coming weeks of this rain on snow event? So we tried our best, and I think most of the operators here remember how we, and Jeff and everybody sat down in just a couple of days, developed this idea of what would it take to eliminate cold content in the snowpack. And we came up with an inches of rain by elevation at an assumed temperature, which everybody in here should gasp because that's a terrible assumption. And it was really just to say, like, here's what may, if you had this many inches of rain, would cause problems at these elevations, which is a coarse indicator. But the conclusion was, you know, it'd be better, a real forecast with all of the suite of products that come out of the model. So we ran some of those in the San Joaquin this year, and that's what you're seeing here on the figure is all the forecasts we ran, and that's the SWI coming out of the model. Some of those you can see do pretty well, and some of them don't do very well. So again, with these atmospheric products, we're finding that there are seasonal, sub-seasonal, and spatial biases that are really challenging to cope with. And of course, we have all the state variables available for this, so that's kind of the fun part, is we get to go chop and dice all this stuff. The other thing we've been working on that we're really excited about is there's this CONUS 404 data set that's come out, and it's a 40-year data set, and it allows us to do historical runs with ice snowbow, which is very great, and it helps us start to bridge some of these gaps that we have with the statistical modeling approaches and trying to bring in ASO data. We have this system in the last 10-ish years of ASO data, but a lot of the statistical methods, as all of you know, are kind of hard. We can't just jam that in there because there's other biases that we're trying to cope with. And we're hoping that having this data set and running this in the Sierras and various places will help us begin to understand what are the implications of trying to jam the ASO data into these, methods that we're still using. The cool thing is we get to look at all sorts of spaghetti plots, as we've seen in all the many other types of historical run stuff, but we've been looking at runoff ratios in the Boise and just seeing how those evolve across the years. So those squiggly lines there on the left are cumulative SWI and precip and runoff. And so it's kind of interesting to watch those evolve over time. Because we're working on that, and we're working on historical modeling and trying to figure out what are the likelihoods of various flows, we've started work on our own streamflow runoff model to help bring SWI down the hill, which is always this question of, we have it on the ground, but what does that mean for me here at the bottom where it's coming into my reservoir? And we agree that's a really challenging question. We would rather, and this is why we haven't done much work on the runoff, we'd rather get the SWI right with the right timing of all that stuff. And that's a really difficult problem. And I personally don't feel that it's always addressed frequently. And it's easy to just jam it into a runoff model and see what the output is and move forward. But we haven't been very satisfied in the early years with where the timing of SWI was. So we didn't think there was much point in trying to pump it to the bottom just to see. Anyway, so we have this WSL's or SLF streamflow model that was a part of some work that happened at the ARS and then has since left. Now, the stuff that we're really excited about, this is the stuff we've been working on in the last 6 months-ish, begins here with this idea of, and we've talked a little bit about it, many of the California folks have seen some topics from us about trying to figure out what does a station mean when we see that one of our pillows, when we compare to a pixel, is 100% off, right? Out of 10, and only one looks like that. Do we go chase it? Do we try to figure that out? Do we make an adjustment? And the conclusion was, if you ignore it, sometimes it bites you in the butt. And sometimes if you include it, it bites you in the butt. So there was some inferred weighting that's going on underneath, but as humans, we're terrible at anything but linear math. And so we knew that there's some weighting going on, that each station meant different things to different basins. So we started with making these maps. They're very configurable because we're still learning a lot about them, but we can say, okay, what elevation band does this live in? What aspect is it on? What vegetation's around it? And then we can broadcast that out and create a mask that fits that space and say, all right, in theory, our intuitive sense is that this station might mean something to this area. The work begins with trying to validate that, right? Like, it's easy to say that's what this means, but we all know that the spatial distribution is not as simple as just saying it's something about elevation, right? So we can take the ASO data, apply these masks, and the hope is that it would narrow the histogram, right? in theory, if we're right about these areas, that they should be sort of self-similar. So we've started work on comparing what the model pixel says and what the station is showing and what the ASO pixel at that station is showing, and then what the distributions are for those areas. This has been a lot of work, and it's still not fully validated, and it can be easily poked holes in. So you're seeing some of this in real time, and but what we're really excited about, because we hate being surprised. Sometimes we're 2 or 3 weeks away from a flight, and we don't really know how accurate the model is, which is why I said the other day that uncertainty is kind of this looming thing, which is great that Eli went over that in his presentation. But for us, we look at these stations and we think, what do we do in this situation? So here is an example, and I will submit that this was a miss this year on our behalf. This is in the Kern River Basin. And when we looked at these, this is just before our June flight, we kind of thought this is pretty good. Like, I wouldn't do a whole lot here. Nothing here is that glaring. Minus some of the noisy data. And we presented some of these results for our mid or bi-weekly update. And the current operator said, I think you're wrong. I think you've got too high or too low of a number. Because he was saying, if we go by your number, we should turn it off now. And we were still waiting for a flight. And you know, it's not very often that somebody directly says you're that wrong in a very public manner like that. So we were taken off guard, but it causes us to go ask questions and poke. And in addition to that, all of the flights in the area, the Kings and the Kauai, they had all reduced the volume in the model. So we were kind of thinking we might be high. So when somebody said, we think you're low, it was quite concerning. So what we've done, and this is very preliminary work, is we've used the station representation to begin to try to understand what is the model error at this point in time. And we can use those to create some weights and try to use the station value to estimate how far off are we by TAF. And for the first time ever, and this does not work everywhere, this is just the first time this has happened, we were able to demonstrate before and after the flight that the station plus the representation masks are allowing us to see there's an update coming. And this update in particular, it's predicting that we were going to get bumped up 105, was 120. Now, there's tons of stuff buried in here about where are your stations, how well covered are you, that would not scale everywhere. But we were really excited for the first time we might have a way to actually say, are we high or low? I mean, even if we could just get an indicator, like, is it going to go up or down? So we're very excited about this work. It needs a lot more work, is really the answer to that. The other thing we've been spending our time on is updating the veg height in the model. In the past years, we've used the landfire veg height, and as you can see here, in comparison to the canopy height that we're pulling from ASO, it's pretty bad. That's not a poke at landfire, because if you look at what they're trying to do and define, their veg height is a little bit different than what we might want for hydrologic modeling, because it's the average height of the dominant veg species in the pixel, right? So you can kind of imagine a space where maybe you have a redwood forest and a meadow, and they're gonna not take half of the trees, right? They're gonna just say it's the average of the redwoods. So that's an interesting thing that we're contending with, but there is some serious perks in including some of the spatial variability that comes from just this veg. And here you can see, this is in the Blue River, this is Copper Mountain Ski Resort there on the right. You can see the runs that aren't included in the original landfire data set. And it turns out that has real implications for the energetics. So what we did this summer is we ran without ingesting ASO data, and we just used it as validation. We had a landfire run, and then we used our ASO data set, or our ASO veg height, and then we compared both of those runs to just the flights. So no ingestions going into the model, just looking at how are we doing at these snapshots we get. And there was a lot of work here. This was 9 flights that we had in the Merced to look at, and in general, we saw that with including that veg height, there was a 2.2 inch reduction in the air and a 3.6 inch reduction in the RMSE for the depth errors. And there's a lot more work we could even do on that. But the big one we were excited about is that we were reducing the air in the total water volume by like 12 TAF on average, which means that there's some, and you can imagine, in the spring melt time period that were much bigger than 12 TAF. We were kind of interested to see how this would have changed this year in general. And down here on the bottom, you can see the veg height is being covered up by the snow that we had during this year. And we had this problem kind of come up in 2017, where again, we weren't using a very great veg height model, I'll say. I don't want to poke too much of the landfire folks. We just have a really awesome data set. It's just that great. And in 2017, we weren't able to melt out. And then in 2023, we weren't able to melt out on time either. So that made us think there must be some connection here. The other thing that changed in all of this is ice snowball originally was not, its radiation was not aware of the snow depth. So as you can imagine, as you're seeing in this picture, there is vegetation, especially on a year like this, where 2-meter trees get buried. And the change in radiation suddenly that we go from underneath a tree to fully exposed on top. So those two changes went into the model. Those results are significant improvements. We're really excited to roll those out for all of our operations this year. And with that, I will leave you with a picture of my son asking his own veg height questions this summer on his first backpacking trip. Thanks.
Awesome. Time for some questions. Ramesh was first on the jump.
M3 Works is kind of very fantastic presentation and really interesting research that you guys did. Fantastic. Going forward in what year 2024? That means do we expect the model reservoir inflow from this sweep flow model from you guys? Can we expect that from you guys?
I would say TBD. It's we haven't rolled it out everywhere, so we always have questions when we haven't rolled out stuff yet. So that's probably a question with the meeting of the minds with ASO.
All right.
Be nice.
Yeah, do we need to stand over here so we can see Jeff?
So I have a kind of a short factual question and then a second that's a little more philosophical. Where are you getting your incoming solar and long wave radiation from?
Yeah, that's coming from the HER data set, but then we do some corrections for various things in, like veg and cloud and all these other things.
Well, and where does HER get its values?
Well, it's modeled, but looks like Mark's got a better answer.
This is the solar radiation you're looking for.
I don't know.
Okay.
Hello?
Yeah. Well, I think, people have looked at various products, and in general, I think the series product tends to be the one that people seem to trust. Yeah. Oh. Yeah. So the second one is a little more philosophical, and that is you're driving part of the model by precipitation input from HER. But ASO is sort of predicated on the idea that precipitation models don't work, and therefore we have to measure it. Right. So how do you reconcile that you're using a product that your company says doesn't work?
Yeah, is this on? Yeah, there's certainly issues there. The idea is that we want to get as close as possible to the flights for the central reason of getting density correct. So yeah, from the broad scale in the sense of ASO, does it matter if we have precipitation right because we're getting a measure of it? No, but that measure is only good if our density is good going in. And the only way to get good density going in is to have the best precipitation that we can. That's boxing up and ignoring wind redistribution and those other processes that are very important. And we'll work on that. Is that one working? And now I'm done. I don't know. I'm not sure that answers your question.
My question, this is not working.
It's working.
Okay. Is for, actually for you guys and Ramesh, because this is a theoretical question. You had $1 million. Would you rather spend it on bulletproofing and adding to the snow sensor network, or have more ASO flights? Just that thought experiment. Where would it improve your model the best? More ASO or more snow sensors and bulletproofing the existing ones, since we had so many of the high elevation ones go out this year? So pretend they all could be made to work.
Right. Yeah. I mean, more ASO, right? Like if we could have ASO every day, that would be awesome. It would be amazing. And
No, it's only $1 million.
Oh, only $1 million. Okay. So what is that 5 or no, I'm kidding. Because of how much we learn in the spatial snapshot of what comes with an ASO flight, I would lean towards that. Because we can learn, for instance, there's a ton of stuff to be learned in that albedo data that up to now, we have not ever had, right? Like, and certainly the time series data is super helpful, and I would never say that we don't want it. In fact, part of our representation stuff that's been interesting that's come up is maybe we can use that to figure out where a sensor would best improve, our knowledge gaps or whatever. So a little bit of both. Is that the safest answer?
Yeah, I think we like to add additional sensors, but we have a lot of challenges. Like especially in high elevation. First of all, most of these areas are in on the wilderness. We have to go through this special use permit from the Forest Service. It takes years to get that permit first, and then we have to have other logistics. So kind of that takes time. So like to answer your question, Peter, I think we like to kind of see how we can optimize that, but for the timing, it looks like ASO flights is the best way to go. Although like we have our sensor up there, we like to continue upgrade all of those sensors. So adding additional sensor is a lot of challenges on our end. Thank you.
I wanted to chime in on that topic briefly, as I work for the NRCS and we're covering a lot of the rest of the West. Those are all real challenges. I'm not sure the best way to look at this is one or the other, though. And I think that's sort of what you all were saying, and I appreciate that. I want to switch questions, though. So my question is, you guys are getting a lot more experience as you work in new basins and seeing how the model performs differently in different basins. And I'm wondering, generally, if you're seeing things that are similar changes you have to make the model in similar basins or even across greater regions or not, and what that may or may not say either about the model structure or the inputs to the model. Just make a general comment about that.
Yeah, I mean, what first comes to mind is precip, because we don't do any bias adjustments in California because it's pretty good for the most part, at least in the ways that we can look at it before we get an ASO flight. In Colorado, that's really, we think, predicated on where radar can see into basins, which it turns out is not everywhere, and some places it can't see at all. I think the other thing we've noticed, particularly in Colorado, is that dust is incredibly difficult to manage and understand when it's present and to what extent it shows up. That's a regional challenge that we have to cope with. We have it in California in some ways with carbon and things, but we at least know that event's happened. And so we know we got to go try to tackle it. The dust, we still have this kind of operational challenge of knowing, did that happen? And eventually we see with the ASO data that it's there, but sometimes there can be weeks before we get to know that. And we're scraping the web, listening to Jeff and everybody talk about what's happening there.
That's where our imaging spectrometers.
Right.
And the cadence of those.
Yeah.
I'd throw in, and this is related to what he was saying, but density. We've noticed in Colorado, and this is sort of downstream of precipitation and wind redistribution, but we've learned that the same settings that we have internally, compaction,
doesn't give us as good of results in Colorado in general, which makes sense because Danny developed it in the Sierras, Snowbell, I mean. But there are some parameterizations even in density that I think will change. And we haven't modeled at all, like in the Cascades, and I would guess that there's going to be things that we haven't seen yet that with some of the experience there would be new and different that we would have to address.
I think another important component here is that the spatial distribution of precip biases is also non-constant in time. You were mentioning the kind of bi-weekly cadence that you guys are reevaluating that. That means that we can't, even if we identify a bias in the precip forcings, we can't just say, okay, check, we've got that bias taken care of. It's constantly changing, and that affects any kind of model that you're trying to apply. And that's why it's a recursive thing, right? Like, any thoughts on how you guys are addressing that?
Yeah, I mean, the way we see that is just by watching the stations, and that's why we've built out the station validation work. One of the challenges, this is a real operational challenge that we've noticed, is that we do know that the station values are revisited and sometimes they're corrected. And so it depends on when you're looking at them and when that's happening. And we've actually, on a Sunday, been doing precip bias adjustments and then came back Monday to look at it again and to realize they're not the same. So that's like one of the challenges we have to cope with. The cadence is dictated a little bit on what we see from certainly the first ASO flights, and then what storms are rolling through. And in Colorado, that was even challenging this year because it just kind of continued to trickle in. There's very few places you could say storm. It's just like kept going. In fact, for a while we thought something might be broken, but it really did that. I don't know, that doesn't really answer your question, I think, but. Harrison's got one over there.
Yeah, any plans on how the forecast mode operation is going to roll out this year? Will that be expanded from last year?
Also, maybe TBD. We'll be doing it for sure in some situations. I don't know if we'll be doing it on schedule. I don't know. Mark's looking at me like I don't know all the answers here.
We're going to do it on Mondays. No, there's some, we will definitely expand it. And some of that is sort of undone work. It's like, how useful is it? So you tell me. No, we have interest. There's some machinery that needs to happen and some additional vetting, but the framework is in place. So it's a function of some other things that we can, yeah, we certainly can.
No, I just wanted to thank you guys, from DWR, how much work you've done, M1, M2, wherever M3 is, soon to be K1. That's the question, really. Do you change the name? No, I just want to public acknowledge how much work you guys put in. Anytime any one of us in our program, cooperators included, ask for something, you do it, you try, you help, on our calls, you're very transparent about where you're confident and where, there's these uncertainties, which really helps us all out. So I just wanted to say that. Thank you on behalf of our program.
Thank you. I really appreciate it. It's a pleasure to work with all of you again. But I really appreciate it.
Thank you, guys. Awesome. Now, Kat, are you ready to go? Now Sean is going to do a song and dance routine. We have been listening. Yeah, he's right over there. We've been listening to presentations across the week, and we've decided that it sounds like there's some incomplete understanding of what we're doing internally at ASO when we interact with the M3 Works products to come up with the density field that we use to compute our snow water equivalent products. And so those of you who completely understand that, take a break. And Sean is now, why does it keep showing you? That's awesome. So Kat's going to lead us through a pretty brief explanation of our workflow. Wow, infinite regression. This is crazy. Our workflow in going from the model densities, wrapping in the station observations and the in-situ observations to get to our SWE products. So Kat's going to lead this, and then I and Grayson will provide some color commentary as needed. There we go.
I'm confident you can speak for me. Just give me a shout out.
Oh my, yes, I will. Okay, so this season, Grayson took over a lot of the density work and he really took it to a whole new level. And so I'm standing up here telling the things, but it was mostly Grayson did a lot of this work. But we do this in a collaborative environment, so it's not usually one person sitting there doing everything. We all discuss this together because it is quite important, as everyone points out. So this is a schematic of our workflow, and I'm going to step through each of these little blue boxes so you don't have to memorize this. But we start from the left and we move forward to the right, and then at the end of the day we have a snow density map, thank you, that we think is unbiased, and that is the goal of this. We can never get a truth on the density map, we don't have the obs for that, and the obs aren't the truth anyway. So, okay, so we'll start off, see I've screwed myself now, there we go, yay. Okay, here we go. So we start off by looking at what's happening with the snowpack. Where are we at in the season? Where are we at spatially? Colorado, California, are we at the start of the season, the end of the season? Did it just snow? Has it been melting for a really long time? And all of those things really, sit in your brain when you're trying to evaluate snow density information. So we look at that first. And then we plot up what we have. So the triangles, or the little dots on this plot, are the snow course measurements. So every month we get those coming in. We sometimes add our own in there when we go out in the field. And then the traces you see on that bottom plot there are the sensors. And so this is snow density, backed out from the sensor information. And what you can see here is, general agreement from the sensors, but you see some spikes and some things that you gotta watch out for those, I guess, is the thing. And so we gain an appreciation of what we have, and then we sit back and we think, okay, what do we think needs to happen here? Okay, so we go through and we say, which of these observations are high quality? Which ones are good? Which ones make sense? Are we getting 120 kilograms per meters cubed at the end of the season in May, because that's not realistic, so we're going to ignore that one. So we use our brain a little bit here, but we have a bunch of little techniques that we go through to try and look for things like bridging, look for things like, is the sensor buried? Is one of the things, is the pinger broken? Is it fallen off the thing? Or, obvious Q&A things, but sometimes not obvious if you are not looking at the traces. If you're not looking at these data, you're just picking out a density, you might get a number that makes sense or maybe doesn't. But you'll miss things. So for this, for instance, we're seeing SWE is flatlining, depth is getting higher. There's something going on here. So a density in that period of the measurement record wouldn't be great. But then it seems to come good afterwards. It looks okay over here. And so these things are not static in time nor in space. So you have to look at it all the time. And so we do this. Grayson's staring at this stuff the whole time. Okay, so yeah, like I said before, there's a bit of a spike here that doesn't actually make sense. Why would it do that? There's no physical reason why it would do that. It's a blip. Don't know why it's happening, but the other sensors are not showing that blip. So what we might do is not take the very spike here, even though, the day of the survey would be there, we might take it down to here. So we're using our brain and our judgment to kind of come up with what this information is telling us, and not just automating our way through and picking up a whole bunch of mistakes. And so for this one, we kind of get the general vibe. We say, okay, the general guidance here based on this information, 315 to 385. just a ballpark. And we say, okay, that's kind of what we're trying to look at here. That's what we think it might be. You know, it's obviously varies across the basin, but not as much as people may think. Okay, so now that we've done our appreciation of our in situ and we kind of feel comfortable with the high quality stations, we're not getting confused by, you know, missing data or weird data, we have a look at what the model says. And so this is where we go to M3Works' server and we pull down their density map and we look at it. Cool, so we'll map it, we'll look at it, and we'll see what it's saying. And so in this particular case, it's showing, you know, a distribution here. This basin is Clear Creek in Boulder, or near Boulder, Colorado. May. Should have made you guess. Cool, so there's a lot of, you know, 500s sitting in here. Most of the basin is sitting at about 400. And, you know, there's some low pockets and things like that. So it's not crazy bad from here. So that's great. We'll keep cruising. And now we're going to do the comparison. So one of the tools that we've used to assess the model, because looking at the point-to-point comparison sometimes doesn't give you what you want, and that's for many reasons, and we all know this. So we like to sort of get the general vibe of the thing. And so across here we have elevation and bulk snow density, and we just scatter plot every single pixel from the model onto this plot. The blue is cold snow, so snow that's not, that has cold content, and red is snow that's sitting there waiting to melt. And the reason why we split this up is because it speaks to snow density with different processes. Melting snow is more sensitive to thermal processes. Colder snow, you know, will generally compact a little more, and so we're really trying to keep the physics in this. And so we're looking here at this, and we plot up the observations. The observations are, you know, around 315, 385, you know, quite a bit different to what the model's showing us with those, at those elevations. We plotted again in terms of snow depth. We do this plot because of compaction. Deeper snow gets more squished, basically. And so we can see again that the model is too high. So we'll look at something like this and we'll say, okay, the model is biased. Let's change it. And so we go through, and so this is in May. So again, always thinking about where we are and where in the season we are. So does a value of, I don't know, 350 or something make sense for Colorado in May? Yeah, it does. So it's quite a bit different to California. So you've got to use a brain, you can't just automate it out. So we'll go through and we'll look and we'll say, okay, there's a bit of a pattern here. Like we know that the in-situ network doesn't sample the basin in a really, it's a biased way, but what it is showing us is that we're seeing a bit of a compaction trend here. It may or may not make sense in this situation. I think it does make sense because we were having snow come in at this time. So we look at this and we think, okay, let's do some adjustments, while maintaining what the guidance is telling us. So the guidance is telling us certain things, so we're not going to snap the model to the observations, we're just going to go with the general flow. And so if you look to the right, so this is before we did any changes, this is straight out of our snowball, and this is with our changes here, and you can see we took a nudge, we nudged it down, and we're sitting much better with the observations. And so at this point, if we do our one-to-one comparison, we're down to a zero bias from quite a large bias. And that's all we do. That's it. So we've just gotten rid of that bias straight out of it. We don't do any more. There's nothing more to do here with these data. And so we move on. And like I said before, we do before and after comparisons. Before, the model is way too high. Now at the in-situ measurements, like at the one-to-one locations, we're unbiased. We're not perfect. We don't need to be perfect. The observations aren't perfect. Does it make sense? We go through a review. And this is where the science team will have a big discussion. And we'll talk about it all and figure out whether it does make sense. And so that's it. That's all we do. And I just really wanted everybody to sort of, know that process because it's kind of important to what we do. Yes, good point. We will often iterate with M3 Works during this stage of the process as well. And so we're sort of going through, are you seeing the same things? What do we think is happening? Oh, rain hit the snowpack at this elevation. Does that make sense? And so there's a lot of discussion about the physical processes before we do any kind of multiplying out to get the snow water equivalent.
Back up a couple to the bias corrected. Yeah, that one. So kind of the philosophy here is that the model is representing every environment in the watershed, whereas the station and in situ data or manual data are representing a pretty narrow set of environments, generally flat forest clearings. So in effect, the philosophy here is that we're trusting that the model is capturing the variability within the basin in snow density, but that it may be off in absolute bias magnitude. Our bias correction then, as is demonstrated by this example, that cloud encompasses the range of in situ measurements that are out there, but it represents a greater variability that exists than is captured by the in situ network. So we really think that this is the kind of the best available technique to get to a spatial density until we get some more maybe remote sensing information or 50 times the number of stations that are out there on different aspects and elevations above tree line, et cetera, rather than the narrow set of environments. More information is better. That's why we work constantly with the observational agencies to make sure that the data streams are continuous, that and we can advocate and feed back to what sensors seem to be problem children versus reliable stations. And there's so few station and manual measurements out there that often one single additional measurement is really useful. So that's why we'll send, especially if we're flying San Joaquin, we'll have Grayson or somebody runs up to Minaret Vista and digs a snow pit, because one additional measurement on top of 4 or 5 or 6 is a significant addition, especially if it comes from a different spatial context. So that's something that we're working towards, building out a program to increase the number of manual observations that we can get, because it really does make a difference. Thinking big picture here, getting to this point is our entire process for measuring snow depth from the differential elevation measurements. The biggest component of the spatial variation in snow water equivalent comes from variation in snow depth. And our measurement of snow depth is pretty darn tight, not just as evaluated at the stations, although it's pretty tight at the stations, but we do that spatial bias correction or relative registration between the two elevation data sets, which gives us a homogeneous across the basin bias correction. So we get, so that everywhere we subtract and there's no snow, we read 0 snow depth. But there's also enough of those points where we can get an estimate of the error of that, the spread of those, the errors in the no snow environments at 3-meter resolution. And therefore, and that's down in the single centimeter ranges. When we aggregate to 50-meter pixels because of the laws of error propagation, hey, there's our coyote tongue. Because of the laws of error propagation, that error estimate goes down by 1 over the square root of the number of pixels involved. So it's like 64 or something, 3-meter pixels in a 50-meter pixel. That means that our snow depth measurement at 50 meters is pretty darn tight, sub-centimeter. That's the biggest component of the spatial variability in SWE. That loads the remaining uncertainty onto our density estimation, and we think we've got a reasonable process here to beat that uncertainty down as far as possible. A couple other things that deviate a little bit from this process, and this is captured in the product reports as well. This process will often go from this stage and run a couple scenarios. So you could probably do some different bias correction here and come up with an equivalently good looking estimate of the spatial pattern of density. What we do then is we run a high scenario and a low scenario. Say, okay, well, what if this is our best estimate? What if we overcorrected it a bit down? And that's our low density scenario. Or what if we undercorrected it a bit and we have a high density scenario? We then have a sensitivity measurement of how sensitive the basin SWE volume is to our estimate of density. And that goes straight into our estimate of the uncertainty at the basin scale of what our water equivalent is. So best estimate, and then we bracket it a bit, and it's not that sensitive. We're talking about somewhere between 2 to 10% in the extremes on total basin SWE volume from the density adjustments. So the process can't be viewed in a vacuum. It's part of our continuous chain of data production and built-in structural methods to ensure the minimum error and bias. One other challenge that is really difficult is fresh snow. New snow densities are a pain in the neck, both to measure and to simulate. Fresh snow changes really, really fast. The number of studies out there, if there's any grad students out there that want to do a lot of field work, go measure snow densities during and after snowfall at high temporal resolution and get us some compaction curves in different environments, different temperatures. There's not a whole lot of that's been done, and that would be super useful. What we do right now, and that's part of the time trend that Kat was talking about, looking at the station data, is a big question is, okay, has there been recent snow? And how much and where? And one thing we started doing this year is looking at the change in snowfall, and this wraps back into the M3 works trying to beat down the uncertainty in precipitation fields. We'll look at the change or the addition of new snow from our last ASO flight to the current date. And we'll calculate that new snow as a fraction of the total snowpack. And so areas where it's a tiny fraction, then we're not really worried about the new snow throwing off our density estimation very much. But if it's a big fraction of the total snowpack, if we've only got 10 inches on the ground and we get 10 inches of fresh snow, the uncertainty that comes from the fresh snow density estimation is a big fraction of the total snowpack density. So we can then look at different parts of the basin and do different bias corrections based on what we think the new snow density is doing in those fields. It's actually a fairly small part of the whole thing, especially as we get later in the season when we've got a reasonably deep snowpack. But it's still one way that we're looking to increase our confidence in the spatial density retrieval and kind of bracket it with as good observations and products that are out there.
Oh, please do.
Get the man a microphone.
So NISAR is going to be launched in February. That's an L-band, that's 24 centimeter wavelength or so. The retrieval from interferometry it is sensitive to SWE and only mildly sensitive to density. So you get the depth density product without knowing either depth or density. Now, the problem, of course, with NISAR with that wavelength is there is a phase unwrapping problem, except you know the depth. And so I think it'll be pretty easy to unwrap the phase. Now, it works pretty well, we think, for dry snow. But the idea is that, if we have some NISAR acquisitions that are coinciding reasonably close to ASO acquisitions, we should have at least a few times during the season a map of SWE based from interferometry that corresponds to a map of depth from ASO. And even I can do the math to get density from that.
Show your work.
So I think this is an interesting avenue to pursue, is to use interferometry. And like I said, interferometry has problems when we get to wet snow. Everything in the microwave has problems with wet snow. But for dry snow, at least the math looks like it's pretty good.
So we're going to have 2 Doziers on the payroll.
No, you get this one for free.
No, we want to pay you something, just so we have the pressure. I'll just say, thanks, Jeff. That's something that we've been engaged with the SnowX folks on, and particularly HB Marshall's group, because that is a really exciting prospect and one that we've long looked for. The measurements of density in particular are so hard to come by that a spatial retrieval, even if it's for only part of the domain, would be super helpful, and not just with an ASO flight, actually wrapping it into the iSnowball continuous updates. I think there's going to be a pathway there. Go ahead, Mark.
I just wanted to throw in, you might have said it and I might have missed it, but when the density is bias corrected, that also we take that back. So that goes back into the model, direct insertion the same way depth and albedo is, and we run forward from that time on with the bias corrected density. So
yeah, great point. We did forget to say that. Thank you.
Hey, I had sort of a nuts and bolts question. Kat, you mentioned you grabbed the density data. I assume that's post data assimilation from the snow depth from ASO.
Yeah, there's a timing issue there. We usually grab before we do the update from the iSnowball, but we notice that it doesn't make a huge difference usually. And so that's sort of, part of the model, it doesn't make a difference. It should make some difference, but it doesn't make that much of a difference. And so we look at both effectively, but we do, in the interest of time, we do the bias correction usually pre-update.
And so my second part of that was depending what you're doing, I'm wondering in cases where the model's being changed, the depth is being changed significantly. I mean, do you see that? You must see that effect in the density, but you're saying not really?
I mean, I'd probably defer to the Micahs or Mark on that one, but when I've looked at it, I haven't seen a great deal of change.
Okay.
Any comment on that, Micah or Mark?
The greatest change we see is in situations where the snow depth is greatly changed, and it usually takes a handful of days for that to resolve itself. So, yeah.
So, Kat, did you choose that one because it's like a nominal adjustment or a big adjustment, or? Because it seemed, I'm hoping it's a big one. I mean, we're showing off our internal siloing here, but I mean, like that left-hand side was 40%, and the whole trend of lighter snow at high altitude reverses.
Yeah, that was a relatively big change. And as the Micah said earlier and Mark said earlier, the snow density model in Colorado needs a little different tweaking than California. So that was a big change. That's something that we wouldn't normally make. We'd normally make something less than half that big. But I picked it out because it was just obvious and easy to explain. Yeah.
There was also fresh snow in the southern part of the basin for that one, but not in the north, which made it extra fun. All right, I think one more question and then we'll move along. Dave, you're on deck.
Kat, thanks so much. That was so unbelievably helpful to have. I'm assuming here in this upper one, you're using density from snow pillows and from NRCS Snowtel, as well as the snow courses that Sean's group gets, right? Yeah. Would it be helpful for you if from the snow course measurements, when we go out and we measure the SWE and the depth at 10 different physical locations per snow course, I think right now we just average that number, give that to you. Would it be helpful to have all 10 of those numbers, or however many, for a standard deviation? On one of these you had error bars, but on this one you don't. And just one density in a big meadow, it's going to vary a lot. And one of the M's was saying that's like 1% of a 50-meter grid cell. If you had 10 different measurements in that 50-meter grid cell, could that tighten up your uncertainty? So I think we have thousands of pieces of paper on Sean's desk with all of these hand-scribbled notes. And I don't know whose job it is to digitize that. It's not mine. But I think we could get you all 10 of those measurements, and we're working with our wonderful cooperators, hopefully get all of their data too, to tighten up the uncertainty on your density. This seems like an easy thing we could provide you.
Absolutely, I would love that. 10 tells us, it does give us the variance there, and that gives us more confidence or less confidence as is required. Thank you, that would be amazing.
Yeah, and if there's, we often, a number of our cooperators will give the hole by hole numbers from snow courses. And even better would be a precise geolocation on each measurement. We could do even more with that. But I'm not going to add to the workload. I'm getting the finger wag from both Sean and Dave in stereo over there. But anything more we can get from the snow surveys is great. Also, the core length versus depth is helpful to us too, to evaluate, especially if there's one or two of those 10 measurements is super different than the other. That helps us evaluate whether we think that's a realistic high density spot or whether it's like, no, something fell out the bottom of the tube there or whatever. So yeah, more information is better.
I just have a comment. Oh, sorry. I just have a comment real quick. So with our snow course data starting this year, we're actually going to be asking cooperators to enter in hole by hole points. So that should be able to be extracted from ZDEC. So
that's amazing. Thank you so much.
Yep.
The other thing I came up here, I thought I was done, but I'm not. The other thing is that we have, if people are out taking measurements and we want to give them to us, we will gladly take them. We have a template that we use, and it helps us just hit run and it sort of ingests all those straight into here. Otherwise we have to transcribe things from every single person, and that is unrealistic. So use the template, and if you don't know how to get it, ask Kate.
Come on, man. I want to respond with an additional piece with what Gus was asking about. So Gus, so right now, just in the interest of time and the bulk of data that we have coming through, what Kat described is how we've been handling it. But as the efficiency in our processing continues to improve, what we have discussed is to do that depth direct insertion, let the model run to an equilibration, then do a density evaluation, then come back and bring that through. So a more proper assimilation process. So, but it's just been one of the number of basins and the number of acquisitions that we have been dealing with the size of the team. And, but as everything gets more efficient and those procedures come together, then we're going to do a more appropriate assimilation that way.
Hey, I got a quick one for you, Jeff. So for precise geolocations of the hole, we're still working on our survey style. Would like to touch base with you on that exactly. Here's where we're at right now. So we got those survey grade GPSs. Plan on putting them right underneath the signs, course marker signs, both ends. And if there's two transects, those both ends of those transects as well. And then kind of digitally, like they would take out a tape, as marked on the snow course map. 68 feet to hole 1, then 50 feet to hole 2, using those 20-minute occupations on each side of a post-processing kinematic style. So we should talk about it, but that's kind of quick and easy to execute in the backcountry, we think. But if there's style gains to be made, we would love to hear it.
Yeah, let's chat afterwards, but I definitely appreciate all the efforts going towards that for sure. All right, we'll move along because we've got a lot more content this afternoon. Thanks, Kat, for throwing that together kind of at the last minute here. That was awesome. Next up, Dave Gotchis and crew to talk about the WRF-Hydro hydrologic forecasting work with ASO.
Thanks a lot. It's going to be an interesting transition from talking about
the details of one very specific thing and a couple of degrees of freedom to, I think Eli put it probably best this morning, billions, trillions of degrees of freedom in distributed physics-based hydrologic models. So yeah, we're using a few more assumptions than the last discussion really entailed here. So I will talk about what's been going on with WRF-Hydro and ASO ensemble seasonal water supply forecasting for the California ARSS and Colorado Chasm programs. Why don't we go ahead and go to the next slide? Or do I have a clicker? I do. I may. A little jumpy, there we go. Okay, definitely want to call out the team Jeff just mentioned. We've had a great team of people working on this effort for the last couple years. And an old colleague of mine just walked in the back, Logan Karsten, where are you? There he is in the back room. He was one of the originators who helped us set up and run some of the results we'll show today from some prior years. So it's really good to see him here. We've got a ton of external partners, state of Colorado, and now state of California. Sorry, I didn't put everybody from California's name on here because I hadn't met many people before this week. But lots of love to go around with that one. Here's our timeline with what we've been doing really in this thread of prediction research with WRF-Hydro and seasonal water supply and snowpack. We started in about 2009 doing Colorado radar and flood modeling experiments. Those largely centered on summer, but the idea was the recognition that the mountains are observationally scarce and we needed new tools to bring into the mountains. And so, as Nathan Combs mentioned yesterday, the late Joe Busto funded a series of campaigns moving throughout different basins in Colorado to look at things like gap-filling radar, surface stations, and because he and Tom went to high school together, yeah. They connected, 2 years younger, Joe was. They connected on ASO early on, and that resulted in those early flights that Nathan also showed, where in 2015 now, we did the Colorado Rio Snowflow program, which had a year-long gap-filling radar in Alamosa, as well as ASO flights. And we looked at the impact of that on predictions of seasonal water supply. And this right here is actually Logan's handiwork. You remember that, Logan? From a long time ago. Stepping up to 2018, we started to move into a real-time mode with some funding from the Upper Gunnison Water Conservancy District. That was Sonia Chavez, who talked yesterday, and she's continued to support us. It was actually Frank, I forget Frank's last name off the top of my head right now, unfortunately. Sorry, Frank. Kugel, thank you. And then that's been continued on, and that has been a great partnership for years now. We expanded to the Colorado statewide domain for forecasting in about 2020 and started really ramping up what would become sort of forecast display, analysis, and product delivery. We re-engaged with ASO. We'd been doing research together all along and tromping out in the snow when we could and things like that, but really re-engaged in real-time predictions in about the 2021-ish, 2020 timeframe. And stepping into California then, coming in 2022 with 2 basins, the Feather and the San Joaquin, had about 7 basins in Colorado that year. And then of course, last year, everybody's hair was on fire. More work than we knew what to do with in both states, and really have been continuing to fine tune operations. It is, as you've heard, like processing the ASO data, like doing the ice snowbow modeling, it is a very consuming task to keep all that going. You've seen this slide a couple different times because the model's been mentioned before. I'm not going to go into too much detail here. A lot of arrows, a lot of physics processes. I think the key thing here is that there is a land surface model here, which is handling the precipitation inputs and the energy transfers to the atmosphere. There is a lot of similarities in terms of the snowpack modeling with what's going on with ice snowbow. In terms of the physics representations, there are some differences as well. But this is where we're taking the snowpack estimates coming from that harmonized ice snowbow ASO product. We're taking both the depth and the water content and inserting that into the model. It's a multi-layered snowpack model here, which handles a lot of different interactive processes with plant canopy, mixed phase precipitation, some simplified representations for snow albedo, and so and other processes. And that becomes part of this overall broader ecosystem, which WRF-Hydro is, ultimately leading to products, forecast products. Our workflow is outlined over here. As Mark went into a lot more detail than I will here, we downscale and bias correct a number of different long-term meteorological precipitation, other meteorological records. They come from a variety of sources. There's some overlap with what iSnowbell's doing, and then there's some areas where it's not overlapping. There's some long-term discussions going on about how we can leverage and harmonize some of those things together. We do a lot of model calibration work prior to implementation, new implementations, to try and get as good of performance as we can using historical data. We regionalize model parameters from calibration basins to other areas using some techniques we developed for the National Water Model. And then we run long-term retrospective statistical references. We go into real-time operations. We're doing direct insertion of ASO snowpack estimates as they become available. And then ultimately, we're executing the operational model in a sort of a classic ESP, ensemble streamflow prediction methodology, and generate our products. Okay, there's tons to unpack with that, and definitely welcome more technical questions if people have those that would get into some of the techniques that are used to prepare the data sets and to execute the model. But I wanted to save as much time as possible for results, because I know that the model's been talked about in a lot of the different preparatory discussions and a lot of the different stakeholders about how their impressions were with the model, but I think folks have been hankering for a little bit of actual model performance information. So let's talk about what comes out of the model and how it's being looked at right now. This is the domain that we ran for California. We set this up starting last year, and we've been sort of adding what we would call the forecast basins this year. And as I said, this year we stepped up to 5 basins, including the Feather, Tuolumne, Merced, San Joaquin, and Kings River Basin. So on the cadence of either every ASO flight or on a more regular cadence, depending on what was actually more convenient or needed at the time, we were generating analyses and forecasts. The system updates in terms of its analysis cycle every day, and we maintain an open loop and an ASO assimilated analysis of snowpack. And then forecasts are launched from that, usually again, either on a regular cadence or when we get a new survey. In addition to that, because this is our entire model domain here, we also encompass several of these other California basins. We did not do forecasting for those basins this year, but we are tracking some model performance so that as we look to the future and the expansions that Dave Rizzardo is mentioning, we've got some momentum actually going into those already, and we know what kind of performances and what kind of assimilation increments we are hopefully going to be expecting. Colorado, map's a little more crowded. We've been in Colorado, as I said, a lot longer, and so there's been a lot more different but somewhat disparate efforts that have been going on, starting really with the Conejos and the headwaters of the Rio Grande through the project that Nathan talked about, and then bit by bit adding other basins, and then particularly as ASO started flying in more places, and then last year with the CHASM program more formally, really doing real-time operations across this whole domain here, but focusing on the forecasts and the analyses on all these basins. So these were the active flight basins for this year. So you can see a lot of basins and sub-basins. It ends up, again, being a pretty rapid cadence of work that was being done. Products that get developed. As you can imagine from a process-based, fully integrated hydrologic model, there's a lot you can unpack with this. So in reports, which I'll highlight here in a minute, we were providing things like updated snow water equivalent maps, basin average SWE values, analyses, and forecasts from our open loop model as well as our ASO assimilated model. There's also a SNODAS trace in here. We like to keep track of that. We would also put together the snow hypsography in the basins to see how things are tracking between the different products. This is actually, the blue is the open loop, the green is the assimilated ASO, and the red is the SNODAS there. And this is all from the Tuolumne at this time. We would put together tables of SWE values so that folks could track exactly what the total volumes of SWE are in each one of the basins, with each new cycle of update. This is running now from January 24th through the 25th of June. We just finished our last forecast of the season last week. So this table itself has grown, as have the record of all the other products. We tracked and put together products on soil moisture. This is a basin averaged plot of soil moisture with and without the open loop and ASO assimilated values. And it's really just giving you a relative index of overall basin soil moisture and how things were wetting up during the year and drying out. It is, I would say, not a good absolute metric of how much soil water is up there, but more so relatively how wet or dry your soils are, which in these drought years has been very interesting to look at, particularly as you get into this part of the season where things should be wetting up. And as we know, particularly in California, they didn't in some of the prior years. In Colorado, these traces do look quite a bit different because of the colder climate as well. New experimental products that were generated this year or started to get generated partway through the year were the analyzed and predicted snowmelt applications. I think this is somewhat similar to the SWI product, but I think there are some important differences that we probably need to talk about as well. But you can see what those prediction curves look like for a basin integrated value. We would produce spatial maps of this as well. Again, this happened partway through the season, which is why you don't see full continuous coverage there. We are producing estimates of evapotranspiration, another critically important hydrologic variable in terms of water demand. This does not have dynamic cropping and irrigation associated with it, so it is more of a natural landscape estimate of evapotranspiration, but it's really nice to be able to see how the water budget changes play out throughout the season and where the different aspects of the moisture water budget are going to. We can separate things into these components as well, and I think in the future we are going to be looking at some of those components a bit differently, particularly looking at what components there may be in terms of sublimation in some years versus other years. And then finally, this is really sort of what folks are after then when we talk about implementing WRF-Hydro. It is the production of the river flow and reservoir inflow forecast products for all of the sort of active areas we are. Now, WRF-Hydro being a sort of fully distributed continuous hydrologic model, we can go pull off stream flow forecasts pretty much anywhere in the network on the map, but really having them grounded in observational truth, or at least the best estimates of the observations that we can, is really how we're looking at evaluating the model. And of course, a lot of the critical water control points that people are interested have some type of observation or analysis. This is a quick example. It's already a little bit dated from about 2 forecasts ago of outputs for Lake Oroville. So you can see there's a plume of forecast plots. This is a key plot that we use and distribute. It is basically a reservoir inflow flow accumulation plot. The black line is the observed. There are some probability bands in here, although by this time in the year, they've collapsed pretty well down around the median value, which is centered on the observations here. And each one of these traces is a different ensemble member. The color coding is by how far into the future they're going. And so you'll see there's different plumes of forecasts that come off essentially the observed curve, which is forms the analysis as the season goes on. We have been tracking performance of the ASO assimilated forecast versus our open loop model. Certainly anecdotally in all the forecast discussions we've had, there's discussion of how these forecasts were comparing with other forecasts from the various districts, from Bulletin 120, from the CNRFC and the CBRFC. And I think that's where the bulk of the discussion may end up tomorrow about what's working, what's not, what is some common pathways forward to do some co-analysis of things, what could all models benefit from in terms of observations and things like that. So, yeah. This table? So this table here in the plot is essentially the summary of the specific forecast values. So for the mean and the median for each forecast date, and then the 90th and 10th percentiles and the 75th and 25th percentiles. We, in addition to making this plot available on the dashboard that we also have the ability to dump and output these quantitative tables now. So this stuff is all sort of accessible through that web interface, as is these plots. And those are sort of new developments for this year, is trying to get all this automated and then displayable through that desktop environment. Okay, so all of these products then are wrapped up in the report. So just like the ASO and iSnowball teams are putting together reports when they do a new assimilation, once we get that, run it through the hydrologic model, and collect a number of these different graphical outputs, we will put these into a report. I think our last report for California was on the order of 30 some odd pages, and the Colorado one was probably 70 some odd pages. So it's a bit of work to pull these together. Certainly some good opportunity for more automation in that regard. We try to provide some meaningful discussion, although you can imagine at that cadence we don't get too deep on the prose, but clearly there's a lot of information packed into this. So let's start looking at more actual results then. We'll do California first, then we'll hop over to Colorado. And if I start to get long, just let me know. I can accelerate. So this is the more updated plot, again, from Lake Oroville on the Feather River. The Feather River last year and this year was actually one of our better performing basins. It was nice to see that. This is even in light of the fact of the large fires that Ronnie talked about. But in terms of just being able to have a forecast system which is fairly stable, and we feel like our ensemble was at least bounding in a pretty good way, you know, we've seen some reasonably good performance. And I think that's verified by the fact that the density of the overlying model traces in the ensembles here, and really the collapsing of the probability bands around the observations without what we would call a lot of drift, where all of these ensemble members are sort of capped by the observations on one side or the other, is a good sign. There's clearly a ton of spread though. And I think there's a lot of room for improvement in trying to narrow the bounds of that spread. Now, a lot of that spread is the meteorological spread, right, in the forecasted meteorology, particularly for these earliest season forecasts, which is where all these low members come from. But as time goes on, you know, that's the idea, is that we not only have a system that's relatively unbiased, but it's very reliable with a fairly narrowing range of uncertainty as much as we can. The plot up here showing the open loop versus the ASO forecast, and the dotted line being the expected end of season total. That is hand drawn in there because we don't know what it is yet. You can see how these forecasts bounced around a bit. The open loop in this particular case jetted up pretty high early in the season, then it drifted back down, whereas the ASO assimilated values for the Lake Oroville inflows kind of hovered and bounced around what looks to be the seasonal total line April through October. So, you know, all in all, that's what we like to see, although we'd like to see a little bit less forecast variance and have that continue to shrink as much as we can. But of course, that will also depend on improvements in meteorological skill, as well as getting the snowpack properly into the model from ASO. So that's an example from Lake Oroville on the Feather River Basin. Of course, there's a lot of interior points here I don't have time to go into today. Moving down to the Tuolumne, you can see its snow water equivalent traces here. Just like Mark was talking about, we've got our assimilation increments, or what they were calling their snaps, in their assimilated value. The assimilated SWE traces, the green trace here, the blue is the open loop, and the yellow is snowdass. Here's a couple of points from within the Tuolumne River Basin. So again, not too bad. We ended up forecasting a bit low for the Tuolumne this year, and I think the forecasters from those districts were familiar with that. We actually had some discussion on this, and it was pretty interesting. While WRF-Hydro was a little bit low in its forecasting for this past year on some of the Sierra basins, it sounds like the river forecast centers were a little bit high. And Stephen, was it you that we were talking about, and Olivia yesterday in that conversation about it's nice to have that bounding around what actually happened, recognizing the Weather Service has a priority for being conservative, forecasting for protection of lives and property. You know, here we're really just tuning up. This is our first year in the Tuolumne doing this as well. The other thing I'll have you notice, because I'm going to come back to this for all these California basins now, is this vertical dotted line, which is the end of the April through July period. And so the extreme year this year gave rise to the notion, and it was talked about on the talks on Tuesday, about how much was now going into the late season and potentially into carryover. And these higher elevation basins here in California is really where we were seeing that in our forecasts, and it seems like that played out as well. So that means these traces, all these ensemble traces, were still going through a fairly significant flow accumulation phase fairly late in the season, like into August when things typically would have plateaued. The observations did tend to run off a little bit sooner. So reality was faster than the model. The model was a little slow in its ablation this year for some of these California basins. But I think part of that story is, there is this high elevation snow that is still contributing to runoff in some of these areas. Moving down to the Merced, again, this is flow into Lake McClure. So again, the model was a little bit low. You go up to the Merced at Pahono, which I don't believe has much control above it. Things were doing pretty well. We kind of came in right under the observations, and you see that in the sort of time series of forecast traces here, again, with the ASO assimilated value hovering below what looks to be the final seasonal total. And in this case, the open loop getting a bit higher and a bit more aggressive. Now, the Merced is fairly low elevation compared to, again, the Tuolumne, the San Joaquin, and the Kings River Basin. So part of that influence of the late season flows, which is again going to be highlighted here, is not as pronounced in the Merced. So yes, correct. Yeah, only the San Joaquin and the Feather were done last year as well. So here's an example from Hetch Hetchy. Now, I apologize, that is not in the San Joaquin. I messed up my label there. But you can see this is from a July 5th, and this is where we really started looking at, like, those curves are not plateauing. At the, as we get to the end of July, which is what that line is, even though this forecast was made on July 5th, should have been fairly certain at that point in time about what was coming down, but clearly it wasn't. So moving forward, this is what the end of our last forecast essentially looked like. Things have started to turn over at that location as well. And here down at, this is Lake Milliton. I apologize for blending these two together. That was a mistake on my part. But you see the same impact here down at Millerton and the San Joaquin, that again, the model was still having runoff coming off later in the season. The observations came off a little bit earlier, but still some increasing flows coming in down low. You can see the size of some of the increments here. And so that is certainly something that we have taken notice of in the past year. Last one, Kings River Basin. It's basically the same story as the last one I just showed. This is a headwater forecast for Lake Wishon Flat Reservoir. And you see sort of that same behavior, and then all the way down to Lake Pine Flat, or Pine Flat Reservoir. Okay. Little snapshot on what we've been tracking now in terms of snow model performance in the Yuba, American Truckee, Carson, and Kauai. So the same kinds of plots here, and we can start to see some of the assimilation increments. The color is not as favorable on this display as I would have hoped, but you can see in several of these where we're starting to get some of the increments. Some of them go up, some of them go down. It's not always the same in every basin every time. And so we've synthesized some of the statistics here just to look at the background differences that we saw right at around peak SWE between our open loop analysis and the ASO assimilated analysis at peak SWE dates. And so the Yuba ASO brought down our open loop by about 23%. So that's a pretty significant amount. The American brought down peak SWE about 18%. We didn't have a assimilation in the Truckee before peak SWE, as I understood, or if they did, we didn't get it into the model. So I don't have anything for that. The Carson actually had a 13% increase with ASO, and the Kauai a 2% increase with ASO. So we're starting to get a feel for, what the impact of ASO is going to be in these basins, lacking any other changes going on, or what they at least would have been for this year. All right. Moving to Colorado, a number of more basins to get through here. Again, you can see our model domain up here. So it covers all of the headwater regions and the river systems out to essentially the plains in most areas. Now, we're not generating forecasts in every river basin. You can see some large areas in the Gunnison, Lower Gunnison, the Yampa, down along the main stem of the Colorado. So we're still focused on a lot of the headwaters here. And that's important. So California has a lot of water management. Most of it isn't really up high, right? Because a lot of the up high in California is in the national parks and in the wilderness area and stuff like that. That isn't the case in a lot of Colorado. There's a lot of diversions. There's a lot of interbasin transfers. And so it gets to be very difficult to analyze a lot of these flow forecasts in systems where even above 10,000 feet, you have significant diversions going on. And so the upper Colorado is a pretty good point in case of that. Here's all the different forecast points that we've loaded in. The blue circles are reservoir inflow points. The white squares are USGS gauging stations, and the green triangles are Colorado Division of Water Resource Gauges. Now, of course, we're only generating forecasts of those points that lie within the domain, but it does tend to be a handful. This is kind of a deep dive example for Lake Dillon and the Blue River Basin. The animation that's running here starts, you've got open loop here, and there went the first assimilation into the model. And there's another one, late season. It's not quite as striking a difference as the other one. Now we have upscaled that 50-meter product to 1 kilometer. So that's one key difference that you're seeing here. That's why it's still quite pixelated. But really, you can see the amount of variability that's brought in by using the ASO survey at that time. And it really does kind of accentuate the deep and shallow pockets of snow, particularly in the highest elevations where we're getting a lot of that redistribution that's gone on throughout the season. Different forecasts for Dillon Reservoir. This was May 28th. There you can see the probability bands around the median curve. This one verified pretty darn well this year. That June 1 forecast that came out, we forecasted 136, almost 137,000 acre feet. We're going to end up at 132 by the end of the season. You know, we crept up a little bit with the ASO assimilations this year, but it tended to be a pretty good year. And it certainly was this one was a case where there was a lot of improvement compared to the no ASO scenario there. Other products here, just the basin average SWE, the soil moisture, and the snow hypsography. Moving throughout other basins now, this is going to go pretty quick just in the interest of time, and hopefully folks are familiar enough with these plots to get some intuitive feel. This is the Dolores River Basin. So this is the basin that Susan Bahari was talking about yesterday, and probably owed Susan a bit of a marketing payoff for showing that one. I was really excited of how things turned out in this basin this past year. And if you look at the open loop versus the ASO assimilated, I mean, this is probably one of the best forecasts we've ever produced out of this. It's tightly packed. It is relatively constant throughout the season, so we don't have a lot of forecast to forecast variance coming in. And so this was one where we would say, hey, the flights were good, particularly getting the early flight in really helped correct the Dolores River system early on from a lot of early season biases that we would have had without it. And I think, you know, to Susan's point of how they started making those reservoir operations decisions for McPhee early on, this kind of thing really helped them. And she also had good agreement in this case between the RFC forecasts and WRF-Hydro assimilated forecasts with ASO. So I think they had good confidence as well going into that. So is it all like this? No, I wish it was, but it's not. So, all right, there's the Conejos. A lot of spread going on. Now, the Conejos is an interesting basin. It does tend to be very affected by a lot of monsoon flows as well, a lot of monsoon rainfall. And so that's where you see a lot of these departures and all these traces out here are big sort of monsoon events. Not being a big system, it gets more impacted by large thunderstorms in the area. These plots are scaled, I apologize for that, just so that the traces and the actual length scales line up, but I kind of have to squish and stretch the plots in some way. So this just gives you an idea of the open loop and the ASO assimilated plots here. You know, there's a reasonable equivalence. I think there was a little overestimate in some of the Conejos plots, and Nathan's plot from yesterday showed that, where we were just above the seasonal total. One of the things we've gone in and started looking at is how dry the monsoon was in this area for this year. So even though our historical precip traces have a lot of precip in them, they were 2, sometimes 3 inches below normal in the Conejos River Basin, which is in this area here. So certainly, you know, can't cover for the lack of predictive skill for monsoon rainfall. But again, I think in general, the ASO assimilated products added some value to the open loop. Taylor River Basin. This is Sonia's basin now that her team has been funding for quite some time. You can see the Taylor River open loop. Again, there's a lot of forecast variance here. If you take all these forecasts together, there's not a ton of overall bias, but during the season, there's just a lot of migration. ASO in this case really did help center things around what was ultimately the observed value much earlier in the season. I think the RFC forecast that Cody may talk about might mention some similar aspects to this, because this is another area where I think we were in fairly good agreement this year. Our June 11th forecast for the April through July period was 120. They ended up at 118. Now looking into the whole April through October, we've been right or just under 130, about 129, and last week they were at 128. So in this case, we do feel like ASO is adding some value really in contributing to less forecast variance, which I think leads to some greater confidence in some ways. Sad story with the lack of a really robust monsoon all the way up into the Taylor Basin. They had a really long dry down in soil moisture this year. And they got a little bit of rain in August, but not a lot. So they're going into next year now, lacking any other big storms, drier than what they started last season. And so I think that's an interesting aspect of having these sort of continuously running hydrologic models and these products coming out of this, was that sort of advanced guidance. We'll see how it plays out though. Maybe El Nino will change that. The East Slate River, not too much of a stretch here to figure out what's going on. ASO in the upper East River Basin and the Slate River Basin in particular. Jeff's talked about this at many of the chasm talks about how heavy the snowpack was and how well that was captured in the ASO products, and it just didn't happen in our open loop. Now, part of what's going on in the open loop in Colorado this year is some degradations in the meteorological products that were being used. We had traditionally used In-LDAS with a lot of success in Colorado, but In-LDAS, for those who also may use it, has fallen into somewhat of disrepair in its operational implementation at NCEP, and some of the quality control has started to fall off. The folks at Goddard at NASA have also documented this. And so it just goes right back to that discussion that Mark and Jeff were having, that even though we may like a product at a certain time in a certain season in a certain location, it may not be your favorite product next year or next week even sometimes. And so this is a case where I think we were really suffering from some bad meteorology coming into the model, and ASO really helped correct for that. Roaring Fork Frying Pan, just an example here from Maroon Creek. So Steve Hunter was talking about this yesterday. Again, here was a case where the precipitation was being largely overestimated, and therefore the snowpack was coming in quite high. This trace right here is the one we just did on August 28th, so the dominant portion of that skill is coming from the observations. But you can see that most of those early season forecasts ended up being too high. When we started getting ASO flights into the model, it really did, again, help center things quite well, and it brought down some of the variance. Boulder Creek, brand new basin for us this year. This flows right behind my house, as a matter of fact. So no, I didn't make my own measurements. I probably should, as any reasonable hydrologist should, but I don't. This gauge is probably a half a mile from my house. And again, you can see that we were low in the seasonal water supply forecast coming in without ASO here. This is not unusual in the Front Range. Models do not do well in the Front Range in general. Most of them have some significant problems. And looking at the distribution of snow across the Continental Divide, even though, yes, the Front Range is in the shadow, it does get some wind loading. And so there's some high elevation dynamics that models often struggle with. And while there's still a lot of spread here, and I would not call this an outstanding forecast, we are seeing marked improvement compared to what was available. And this is, there's not a lot of big seasonal water supply forecasts going on in these areas. So the municipalities in some of these areas actually have expressed the need for additional forecasting points and services in these areas. St. Vrain, one watershed to the north of Boulder Creek, similar story. This is a story really, again, of not changing the overall bias in the forecasts a ton, but really kind of helping to constrain the forecast variance as we moved through the season. Kind of trying to move on here and wrap up. This is Michigan Creek. This is an example I wanted to show because this is that upper South Platte River Basin survey zone bounded by this polygon here. The upper South Platte River goes all the way down into here, then up into Denver. This is a basin where we are hard pressed to find any gauge that doesn't have any upstream management to it. So this is the one that we could find, which doesn't have a huge amount. It's got some ditches above it. And California folks, don't laugh. Yes, that's 10,000 acre feet of water. Not a lot of water, right? But again, even at such small scales and in an area that is typically a lot of wind scour, a lot of sort of just high, really almost arid mountain basins, you know, we're seeing very significant differences brought in by use of the airborne LiDAR surveys to help constrain that prediction. It is, again, not what I'd call overall a great forecast. There's some seasonality issues coming here, but to see this tightening of those ensemble members is good to see in that area. Okay, a couple more and then we're done. Main stem Colorado River. This is the Colorado River at Baker Gulch, which is essentially above all the lake systems on the headwaters of the Colorado. This is an area where we think the NLDAS product had some severe deficiencies this year. We had really low precipitation estimates. Our open loop forecast suffered for that. The ASO simulated values really did bring that back into accordance. The model was a little late in melting off, kind of a similar story at this high elevation that we saw in some of the California basins, because you can see the observations really starting to uptick earlier. But things squared out throughout the season, and I think overall we ended up with a fairly unbiased forecast, maybe a little bit on the high side at this gauge. The Fraser River, so I believe Nathan Elder was talking about this station, did I get that right? Was Nathan talking about that one yesterday? Similar story, basically. You can see the observations way up on the upper bound of the plume here, and here we're much more centered into that. Yeah, and so Fraser River at Upper Station, even though this is at almost 11,000 feet, there's still a diversion off the top of this going over to the Front Range side. So yeah, you get what you get. But you know, I think this is showing a reliability of the product here. Okay, wrapping up. Number of different bullets here. I'll try and hit some of the highlights. You know, I think over the past several years, we've certainly been able to demonstrate that we can operationalize these types of products and that the spatially distributed snowpack observations that are properly ground truth, going back to all of the comments of the last session, can have a significant impact on forecasts. You know, compared to open loop and what we would just say meteorology only forced forecasts. And that's an important caveat, because many of the other forecasts coming from the RFCs, coming from NRCS, they're not just meteorologically forced, right? They are using observed states of snowpack going into those. Forecast skill changes across Colorado and California it's highly variable. It is hard, even after doing this for a few years now, to make very general statements. And so, how many flights do we need? When's the best time to fly? You know, what's the impact? Where's the sources of error? In my opinion, I hate to say it, it depends. The basins, the meteorology, as we heard about this morning, and a lot of the specifics within basins are so variable. You know, you really do continue to learn. Even though you can have a process which is transferable, you still have a lot of learning and a lot of knowledge which is wrapped up locally. That said, one of our biggest thorns in our side continues to be anthropogenics as a major source of uncertainty. So even looking down at those terminal reservoirs in the Sierra, and we were trying to use naturalized observed streamflow time series to get at those, the anthropogenics that are happening upstream do impart still a major sources of uncertainty. And so I think that's going to be the case for quite a while. Let's see. Yeah, ASO assimilated forecasts in general tend to produce forecasts that are more centered or hover around the seasonal values, while the open loop forecasts more often than not often drift towards the observational value as the season goes on. Now, it may not necessarily translate into more or less variance. Sometimes it does, sometimes it doesn't. But that's one of the general points that have come out, and that's kind of that second bullet there. As I mentioned earlier, the WRF-Hydro ablation and melt rates across California, particularly in some of those high elevation basins, did appear to be slow. And what that means is when we do the ASO assimilations using a direct insertion method, we're yanking some mass out of the model. And we think that that was one of the contributors this past year to some of the lower forecasts in California. And so now we've seen that play out in a couple of basins. We've got a direct mechanism to explain for that. And also based on what the M3 Works people were doing with amping up their ablation rates during the season as well, we have some ways to go address that particular model shortcoming. This is just to say assimilation methods that minimize mass adjustments, things like particle filters and whatnot, where you're not necessarily just swapping in a new state into the model. They may have some value here, but they have other drawbacks as well. And so there's trade-offs with all these, whether it's needing more ensembles, whether it may not particularly isolate a process to get to the right answer for the right reason, or so on. And then the last point, I think, which was really valuable this year, because we're still learning how the model performs in California, was this idea that using the spatially distributed information from ASO and, sort of a high spatial resolution model, we were seeing, or at least the flag started going up, that typical April through July period was not really going to cut it for covering the full forecast water supply season, and that there would be these late season flows coming in. Now, WRF-Hydro did tend to overestimate that, but in discussions with Stephen and several of the other operators in the area, particularly down on the Kings and the San Joaquin, Matt Meadows, I think, was another one who we were sharing this information with. We started to differentiate our forecasts into our April through July and April through September, providing quantitative differences of those, and then sort of those percentage differences. And as you can see here, I put stars by the high elevation basins. And again, that's where the higher percentages of late season flows are coming from. It's kind of logical, but it's nice to have it sort of mapped out there. And we started seeing that sort of late June, early July, and there was a series of discussions that went on around that. We'll see how it ended up at the end of the season. I think these numbers aren't going to be too far off, though. And that is it. So hopefully, yeah, thanks. Hopefully that filled the appetite of folks wanting to see results from WRF-Hydro as opposed to plans for WRF-Hydro and stuff like that. So, yeah. Questions?
Let's take maybe a question now, and then we'll lapse into the break here, and then we'll have time later this evening at the reception and dinner as well to chat with Dave. So, and also tomorrow's technical session is a good place to follow up on some of, especially a lot of those last bullets. So maybe one question? Gus.
I'm just going to ask, looking at the...
Oh, wait, sorry. No, you're good.
I'm just going to ask, related to the ensemble members, so what exactly are you using to force those different ensembles?
It is all historical weather information, but it is coming from different places. So for California, we're using the CNRFC precipitation, analyzed precipitation, as it gets passed to NCEP, and we use it in what we call our extended analysis and assimilation cycle of the National Water Model. So their precipitation analyses are going into that extended analysis, and it's getting combined with essentially thermodynamic data, temperature, humidity, radiation fields coming out of the HRRR model in a similar, although slightly different process to what the M3 work showed. So that's the analysis part of the precipitation there. And then we will go back and resample that from history, because we've got the long-term time series of those same products from what we call the analysis of record data set, which is, again, a NOAA-based data set, which compiles the River Forecast Center precipitation products. So for California, we're resampling from that AORC climatology.
Okay.
For Colorado, we have been using an LDAS, and we do our own downscaling and bias correction to that as well. But it's really the real time with an LDAS is what seems to have really gotten wonky in the last 2 years. The historical traces probably aren't that bad, but the states that we're getting aren't as good in that open loop model because those real-time analyses have gotten pretty bad.
So when you say real-time analyses, this is kind of what I was trying to get at. Classic ESP is using, historical years from an initialized same starting point. That's basically what you're doing. I mean, I'm correct.
Yeah, exactly.
So then what is the real-time in LDAS? How does that affect what your
the real-time
is?
LDAS has a 3-day latency, so they do produce that product 3 days after real-time, but its archive of that data set goes back to 1979. So we're sampling from that archive going back for the ESP traces. Does that make sense?
Yeah, it does. We'll talk more about it too, I'm sure.
Yeah, sure.
All right, let's take a short break, and then we've got a few more presentations to get through before dinner. Thanks, Dave. All right. In our second operational modeling session this afternoon, we've got a couple more talks to get through. And first up, excited to welcome Cody Mosier from the Colorado Basin River Forecast Center. He and his crew there, as well as some of our partners with the California Nevada Center, have been doing experimental forecast runs ingesting ASO data into the Snow 17 SAC SMA model. So really excited to hear update from Cody today on that. Thanks, Cody.
Thanks, Jeff. I'm Cody. I'm a hydrologist at the Colorado Basin River Forecast Center. Been there about 6 years. Really just going to talk about a summary of results today. Starting just real quick with the modeling method, and then dive right into some of our experimental forecasts where we incorporate ASO data into our modeling. And then looking at, now that we have about 5-6 years of ASO flights in Colorado, bit of a deep dive into some SWE comparisons there. So we're focusing on, here's a map from ASO Chasm. So we're going to be focusing on these basins in blue. So the Windy Gap, Colorado headwaters. This is the Blue River above Dillon, Roaring Fork, down to the north part of the Gunnison, Taylor Park, and East River, and then the Dolores. So we've seen these areas mentioned earlier in the week, but that's going to be the focus of the following slides. So real quick on the method, so we're grabbing that 50-meter gridded ASO SWE product, and we're basically running that through a Python script and spitting out mean aerial SWE values for each catchment in our model. We're replacing our operational snow model SWE with that ASO mean aerial value in a standalone or offline version of the model, and then running it through. So the only thing changing would be the snow states in our model. And then we force that in our ESP model methodology. We're using 91 through 2020 forcings. We get something that looks like this, and then we can take those 30 different hydrographs and come up with a probabilistic water supply forecast, which looks, in our experimental forecast product, looks something like this. So it's a one-page PDF explaining what it is. We got a graphic, and then we got a table here comparing our operational model guidance for that day compared to the ASO SWE model guidance for that day. So in this case, looking, this is example in the Gunnison. So the ASO flight was on the 1st of April, which we put out official forecasts on the 1st of the month starting in January. So it lines up right on top of our official forecast. So yeah, this is basically our unregulated model space. So every morning we run the model in regulated mode. So we're accounting for, reservoir operations and all of those diversions that go on, or all of them that are measured in real time. So a bit more on our modeling. It's a simpler model compared to WRF-Hydro and ice snowball, it allows us some flexibility. We get questions like, if we get 50% more precipitation in the next couple days and the freezing level is 500 feet higher, is that gonna cause my reservoir to spill or some point downstream exceeding flood stage? So we first run the model in regulated mode that accounts for all those water management upstream, and then if we do make any states to the model, those get incorporated into the unregulated ESP run later in the day. So a few of these have been shown. So this is looking in the Gunnison River Basin. I think these are pretty self-explanatory, but I'll spend a little bit of time on how to interpret these. So we begin publishing our ESP model guidance generally mid-December. So the solid black line would be the most probable volume, or the ESP 50, and then we get some ranges here. A wetter future weather scenario could do something like up here with a drier scenario down here. And we run the model every day. We put out official forecasts on the first of the month. And then on this graphic, there's two ASO flights here shown in that cyan blue color. So you can pretty quickly just see, if this comes in below our model run for that day, that's going to mean that the ASO SWE was lower than our model SWE for that day. Just a summary table down here. So there were 2 flights in all basins in Colorado this year. So these tables are included in a couple of these. So these numbers correspond to the May ASO flight. So this would be basically the ESP 50, the middle blue dot there, compared to what our model guidance was for that day. And then starting in April, these would be the observations that come in. And then it's an April through July forecast. So this dashed line is showing that volume. I'm not going to get into verification. There's been some discussion on that earlier in the week. I guess kind of the one thing I will say about that is kind of the 5 to 8% is kind of what I've kind of thought about from the USGS when they talk about measuring the uncertainty in measuring flow is the 5 to 8%, I think, is what's on their webpage. So this is from the Windy Gap flight. This is Granby Reservoir. So in this case, both ASO flights suggesting, well, not suggesting, they were higher SWE values than our model. And, being the forecaster for this basin, I was adding snow later in the season. So I think ASO was on the right track here. June, July precip, 150% of average. Yeah, model SWE was too low, as I was adding snow to the model later in the season, and we were about 5% too low there. Willow Creek, it's been discussed a little bit this week. So they did have that east troublesome fire burned more than 70% of the basin. So just the day-to-day modeling of reservoir inflow has been really challenging to keep up with, in terms of just having to crank the model really hard to match some of those runoff efficiencies. It's a crucial point. This water can end up downstream on the main stem or on the east slope of the Colorado. Just one snow-tail station in the basin, so nice to have another SWE data source as you get fewer gauges in the area. Sticking with the upper Colorado headwaters, this is Fraser Winter Park. Denver Water talked to this area a little bit yesterday, just about 20, we're just pretty small volume here, 20, 25
1,000 acre feet. Pretty similar results. You know, we were within 1,000 acre feet here. So pretty consistent between our model and ASO SWE values. And then here in the Roaring Fork, so we're looking at Rudi Reservoir. So we model a headwater basin, and then this would be the reservoir local basin that we model. 4 SNOTEL stations grouped, distributed that way. Pretty challenging basin when you look at the snow versus flow relationship. So, you know, maybe look here 2020 and 2023, you know, 130 to 140% peak SWE based on these SNOTEL stations. But one year we got 78% observed volume, and this past year we got 97. So I think ASO, while you know it didn't result in an improved forecast for us this year, I think it can answer or help us better understand what's going on here. You know, again, 2021, 2022, right around normal peak SWE, but you know, one year we got 57% April through July volume, and one year we got close to 80%. So now that we have, you know, around 5 years of ASO flights, thought it'd be a nice opportunity to really dig in to this data. So we generated a bunch of these scatter plots. Here's a full list of all of them we made. So based on elevation, various years, different regions, based on SWE magnitude. So the plots look like this. So we did include our model calibration simulations in this in these SWE scatter plots. So just to kind of go over what all this means, cal would be our model calibration simulation run. Ops is our real-time operational model. How many data points or elevation zones are plotted, and then the correlation coefficient between our operational model SWE and ASO SWE. So this is just for all CBRFC. You know, there's lots of data points there. With the calibration simulation points in red in our real-time model in blue. So first, looking at this by elevation, so this would be kind of our meta-elevation zones, 9 to 11,000 feet on the left. So any point, this is the one-to-one line, so any dot or point falling on this side would mean our model SWE is greater than ASO, and vice versa. Anything down here below the line would be ASO greater than our model SNO. Yeah, I'm not gonna really talk too much. It's more of a kind of a summary, and then 11,000 plus feet. So those real high elevation areas, not quite as strong of agreement there. And both cases, I think most or all cases in these scatter plots, I'm going to show that the calibration correlation coefficient coming in higher than our operational. So that could, you know, be, you know, our calibration model simulation is using quality controlled data after the fact. So it's probably a higher quality data set than what's happening in real time. So like this last year, I know there were some gauge issues where SWE had to be estimated. So I think that could be one of the main reasons why the calibration coefficient coming in higher than our real-time one. Now looking by water year, so all the way back to 2018 through 2023. So you can see, you know, we just had the most flights this past year. It covered 104. I guess it would cover 52 of our elevation zones, and there were 2 flights. So it's pretty good agreement this past water year. It's pretty interesting to see kind of broken out by water year. 2021
the SWE data sets had the lowest agreement, but generally, 0.85 and above correlation coefficient for each water year. And then, yeah, no flights in water year 2020. So here we're kind of combining those, these graphics and the scatter plots to try to connect the dots a little bit better. So this past water year, this is in the Gunnison River Basin. So the last 2 years we've had flights there, and this is a case where, in most cases, the dots are falling above the line. So that it's indicating our model SWE generally greater than ASO SWE, which directly corresponds to our forecast being greater than the forecast informed by ASO SWE. And then into the Dolores, so looking at the last 3 water years here, and the correlation plot. So this is looking at all elevation zones and then those upper zones above 11,000 feet. This is the area that has the strongest agreement between our model and ASO SWE. Really big year this past year, really pretty small year, water year 2021, but encouraging to see kind of on the high and low ends the agreement there. The Blue River Basin, so this is Denver Water manages this, again, the last 3 water years. So here we're seeing, certainly compared to the Dolores, a weaker correlation overall. But, if you look at where this middle blue dot is compared to our model on the last 4 flights, I mean, the volumes were almost identical. So I think that's pointing to just the differences in SWE distribution that has been discussed a little bit. That's driving that correlation lower. And then 2021 perhaps playing a role there too. And then broken down by region. So we've seen these 6 plots here already, but this also includes Windy Gap. So this is both Windy Gap, all zones, high elevation zones, and then same for the blue and Gunnison and the Dolores. So I think the takeaway here is that we were seeing the strongest agreement in the Dolores, pretty strong in the Gunnison. The Blue River, we're seeing the weakest correlation. I think pointing to those differences in SWE distribution. So, I think we maybe had higher or more high elevation snow versus ASO having more low elevation snow. And then broken down by SWE threshold, so anything greater than 5, 10, 15, all the way up to greater than 30. You can see the correlation coefficients by SWE threshold there. Pretty good scatter above 30 inches, above and below the line. Yeah. So our goals here is just becoming more familiar with the data. I think we've made some progress with really diving into it past few months and just being transparent about how we're using it and what it's representing. So basins with more flights obviously provide us a larger sample size to work with. Sparsely gauged basins, this could be an avenue that could help us perhaps the most. There's a really good example in the upper green in over a basin that had no snow tell stations in a wilderness area, and using the ASO SWE data resulted in a considerably better forecast there. Yeah, we recognize the potential for this data. When it comes to, in our current operations,
validating our snow model reality check, which is always nice sitting, in that forecaster chair. Eli, mentioned forecast, never perfect, hopefully useful. So, we're putting out 10-day forecast. It's probably going to be wrong, but hopefully useful. Water supply forecast, same thing. So that reality check, really, really good to have. And then as we transition to higher resolution snow modeling, certainly going to be using this data. It's another tool that we've integrated into our operations. We're storing this data to our database now, which makes it easy to, makes those scatter plots and that type of analysis. And then in the future, just continue refining our experimental forecast framework, getting ready for some new basins that are going to be flown this year. And then thinking more about, there are a few cases where the ASO flight doesn't quite cover 100% of the catchment. So for example, in the Roaring Fork, there's, a basin that I think the flight covered like 89% of the upper elevation. So how do we use that? And just, continue making progress with better, just drilling down to our model performance and understanding and coming up with methods to bias correct our model. And yeah, just continuing the verification work. So that's all I had. Thanks to ASO team for putting this on and having me.
Thanks, Cody. That's awesome. And I love the new analysis as well. I have a quick question for you. You're putting a bunch of years into the same scatter plots and doing the correlations that way. Have you guys looked at individual years to see if there's a particular bias in individual years that?
We have looked at it individual years and we have seen differences from year to year.
So your answer is yes. Yeah, awesome. Thank you. One more question before we move on to the next presentation. Scott.
Thank you. Cody, awesome work. It's so cool to see the long-term impacts of, of inserting the ASO data into the RFC framework. Just doing the comparison on Snow 17, it's interesting to see, some years Snow 17's high, some years ASO seems to be a little bit higher than Snow 17. Have you noticed any trends like on the years where Snow 17's higher, how that compares to the say seasonal runoff? Is seasonal runoff higher in those years, or what's the trends you're seeing between when Snow 17's high and seasonal runoff?
I think the clearest case would be this year, where most of the time, most of these points are above this 1-to-1 line. So it's, I think a more clear opportunity to make some decisions about, this is in most cases consistently the same every year. So I think that would give us more confidence in actually making a modification to the model states, because it's a little more consistent as opposed to equal amounts of points above and below the line makes it a little more difficult to decide what to do.
Absolutely. Thank you.
All right, Thomas, comment.
Yeah, just a quick comment. Thanks for doing these analyses and these deeper dives. And I think just for everybody, and we probably will talk about it tomorrow, but it's just important to remember that even though you may be greater than the one-to-one line, you also have a calibration step that comes after this. And so your calibration may be taking that to the right runoff in certain cases. And so there's a tension here between, so considering ASO as the truth on the snowpack, and then what calibration is doing to runoff. And with the interannual variability that we see, that's what makes it difficult to have some sort of direct applicable bias correction. So it's a challenge. We're trying to force a square peg into a round hole, but we also are knocking off the square edges a bit here. And I think there is some that we can do for sure. But it's an important thing to remember.
All right. Thanks, Cody. Really appreciate it. Next, I'd like to welcome Olivia Kramer from Turlock Irrigation District.
Thank you. Appreciate it. All right, while the slides are loading up, I'll go ahead and introduce myself. My name is Olivia Kramer. I'm a utility analyst hydrologist for the Turlock Irrigation District. So to kind of give everyone an idea of where Turlock is, especially for you Colorado folks, I usually like to say we're right in the smack dab middle of California, and we're 2 hours from almost anything. So you want to get to Yosemite, 2 hours. You want to get to San Francisco, 2 hours. So as far as who we are, oh, it's fighting me. There we go. So as far as who we are a community-owned irrigation and electrical utility. We provide irrigation water to 150,000 acres within our service territory, and we serve electrical power to 250,000 customers over 14 communities. Majority of them are considered disadvantaged by the state of California. Taking a look at where we get our water from for irrigation, you guys are not going to get away from the Tuolumne watershed just yet. We operate the bottom end reservoirs of the Tuolumne watershed, so we have our partners upstream, City and County of San Francisco, who you saw spoke a couple days ago, and down below is us. Don Pedro Reservoir is owned jointly by the Turlock Irrigation District and the Modesto Irrigation District, but as majority owner, TID takes on responsibility for operations of the reservoir. As far as demands on the system, top demand is providing flood control. Now that flood control responsibility is at the reservoir with about 340,000 acre feet of flood control space as mandated by the U.S. Army Corps of Engineers. And then we also have some downstream flood control requirements from the Army Corps of Engineers. So that would be at 9th Street, Modesto. And there we have to stay below stage 55 feet. The problem with that is there is a uncontrolled creek called Dry Creek that comes in right before that point. So we have to do the process of forecasting what Dry Creek's going to do, reduce our flows in conjunction with that to ensure that we stay below channel capacity at Modesto. Moving on to our other releases, similar to kind of what Reggie had showed all of you about hierarchy, this kind of goes through our hierarchy. Number one, we have to provide our environmental flows. For FERC licensing issues, there's a minimum release we must make to the river. After that, we have municipal and industrial supply that's provided by Modesto Irrigation District to the City of Modesto, and within a couple of months, TID is going to be providing it to multiple communities within our area that are currently solely groundwater dependent for their water. And then as far as irrigation deliveries, once again, we have the 150,000 acres from TID, and you have about 60,000 acres from Modesto Irrigation District. The supply of irrigation water produces about $4.1 billion on annual average output to the community. So really significant support of our local economy and also the economy of California. And then, you know, the final part of it is the benefit of hydroelectric power. We are a electrical utility. This is something that is, you know, carbon-free production of energy, and it's cheap to our customers. So that is an ancillary benefit, but once again, we have water first priority. You can only produce power on water that you have to release for your other demand purposes. So getting into the, if it wants to move. You mind going next slide? All right, this is a slide that many of you have probably already seen before, and this is where I kind of want to go through the list of thank yous to all of the agencies that are on this slide. We couldn't do what we do without everyone else. There's not a lot of us, there's not a lot of resources, not a lot of time, and we're all dealing with a lot of the same issues. So when we work together, we can continue to move forward even as we're trying to operate under extremes, both from the climate and hydrology, as well as regulatory extremes that we are experiencing too. So the way that we've structured this is all of these inputs, observed data, research data, forecast data goes into HFAM, which is our physically based hydrologic model, kind of the heart of our operations. To kind of give a couple details of how these integrate into HFAM, on the observed side, you have the historic database of USGS flows as well as meteorological data. The historic input to HFAM goes back to 1931 to present. So that's all the data that we use for our ensemble runs. And then as far as now, we have to go into the real-time observed. So that's where ASO comes in, USGS on gauges, all of the MET stations going in to create our current initial states of the watershed. Then on the other side of it, you have forecast data. So we use that forecast data in order to create deterministic forecasts within the model. Look at, you know, if we run 16 days of the GFS, what happens to snowpack? What's the full natural flow look like? What's the reservoir gonna do? So that's probably the one missing arrow that's also incorporated in HFAM, and it's kind of more the iterative part of it is all the reservoir operations components that it forecasts, and then later forecasts what is Dom Pedro going to do, what is the upstream reservoirs going to do. So going into HFAM, I wanted to give a little bit of detail because it's not as common of a hydrologic model. So HFAM started off as the Stanford watershed model, which some of you might have heard of back in the 1960s, and it was ran on a mainframe, not that exact mainframe, but just to get an idea of where we all started. And as you move through time, getting to about 1997, where HFAM was created, where you could actually run a hydrologic model on a Windows desktop. So just showing the progression of where we've come from. And since then, now that we've had HFAM brought in since that about 1997 period, all of the iterations we've come to. So in 2022, we were at HFAM version 2.5.7. Now we're at 2.5.10, just in the last year with all the changes that we've made to it. So it's constantly improving because of all of those inputs that we have coming in, especially on that research side with those partnerships. And to kind of give a look at what we were dealing with this year. So HFAM is ran off of station data. This year, a lot of our stations were buried by the enormous snowpack. So as far as temperatures, either they weren't reporting at all, or they were reporting actually just the temperature of the snow, which might be useful in the future. And then you also have these issues where you have extreme precipitation events combined with wind, likely getting undercatched by your precip stations, your snow sensors stop working. What are you supposed to do if your model has no data to run off of? So that's where you're doing a lot of QA/QC, and you really want it guided by something. What do I tie that QA/QC to? So one of those things would be ASO. Now, the way I like to think of how we use ASO data, there's kind of that kind of pure way of doing it where you're really fixing your model for the long term, making sure you have a good historic data set after the year's over. So looking at that input QA/QC, looking at your model calibration. But sometimes you don't have the time to do that when you're in the middle of reservoir operations, especially flood operations. So that's when you go to those kind of quick and dirty methods of what kind of volume am I going to experience over X time period? And then can I just force my model into a state? And so that's that direct insertion that we've all been discussing before. So kind of getting into the first part of it, that quick and dirty, what we can do. Everyone's very familiar with this gram plot. This is our version for trying to capture Lagrange full natural flow. So that would be for Don Pedro's full natural flow. We happen to use just the Hetchy ASO readings because that's where we have the longest time period of measurements. As we continue on, now that they've expanded to the full basin, maybe in 10 years, we can switch it over. But the way that you can use this in real time is taking the equation, taking your 90, 50, and 10% precip values, throwing them in, and getting a range on what your runoff could look like for the period moving forward. So that's a way to kind of give yourself a volume forecast or an AJ forecast in real time and be able to compare to what is CNFRC saying, what is HFAM producing currently, and we have that kind of input immediately. You can then also take those volumes and do it kind of the old school way where you take the volume and prorate it to all of the runoffs from your history to try and get how would that volume come off. And you can get a range based on history of maybe how that volume would come into your reservoir. And so now going into more of the pure adjustments based on ASO, this year we did some reassignment of our temperature stations. So when we first developed HFAM, there was a lot of our station data that were long-term data that was only daily. Well, HFAM takes in hourly inputs. So some of those daily stations are distributed to hourly. Well, now we have the benefit, those have been switched to actually hourly met stations. And so let's actually make that switch over so we can get the temperature lapse rate and have those improvements in the model. So this was the older version of the temperature station assignments within the watershed. And this was through the process of reassignment of temperature stations within the watershed to try and capture a better temperature lapse rate. And as far as what that did for the system, so I'll walk this through. The far one, that HFAM old, that was that original assignment that we saw, and then you have the HFAM new. And when we compare that to ASO, we see really good agreement. So our goal when we did that reassignment was not, we want to match ASO. Our goal was, we want to improve our model. And it just happened that that also then allowed us to have greater alignment to ASO. It's that good gut check of, yes, that was a good decision. What we did improved the model. You have that further check when you actually go through historic comparisons between your simulation and your observed data. Here you have an NSE of 0.91 and about a percent error of negative 0.42%. So a lot of improvements overall to the model and its production of simulated full natural flow. And then the other thing that you get to, and this is where ASO is more than just volume, right? It's that idea of spatial. Because we've always had that validation of where we can compare SWE and HFAM to a snow course measurement. Or we might be looking at the snow sensors and just seeing, is the overall shape of what HFAM is producing similar to those snow sensors? Maybe not the exact values produced by those. But this year we really honed in on the importance of having that full spatial information, especially because we did get snow levels so low in such low elevations within our watershed. And so one of the things we did is we tested on the peaks we what if it was 15% higher? You know, we didn't actually have a flight on the exact peak sweep date. So was it, you know, 2.6, 2.9? What did you have? We made a 15% adjustment there. And on peak inflows, there was only about a 5% difference between those two volume states. Because the real question for that peak inflow is, what is your snow covered area? Because there is only so much energy input that can be put into the system, and only so fast that your snow is actually going to run off. So that's where the component of peak inflow that you're going to see is more about that snow covered area component. So kind of giving an idea of what this did overall between all of that kind of QA, QC validation that we did, model calibration updates. The blue line represents HFAM's model SWE, the orange is the ASO flights. Once again, our goal is not to match ASO perfectly. Now, it'd be nice if that's where you end up, but what you see is that overall, we have the right shapes. We're really close in the overall production. And at the end of the day, as a reservoir operator, I care about what it's producing on the tail end as far as full natural flow and inflows to my reservoir. So is that actually getting it right there, even if it maybe is not perfect on what's happening with the snowpack? And to tie it back to what does all of this improvement, all of these tools mean when it comes to operations? Because that's the next set of decisions is you run the model, you get this output, now you have to make a decision off of it. So just walking through this water year, we were going into December thinking we were going 4th year of a drought. We were doing drought planning, preparing our communications to irrigators, that whole shebang of going from there to then the 27th of December, having to switch immediately to flood operations. We moved our downstream reservoirs out of water conservation mode to recharge mode. And then we were starting the process of looking at dry creek flows, doing that whole forecasting process. And so you can see we start to bring up our overall releases from the reservoir at that time. As we move through the period, you have that first ASO flight. What that helped us with is that flight happened after all of those events. Now let's see what's happening in the watershed. What is our current state? And it happened that a little bit after that, it stopped raining. So we had a little bit of a break. So the way that we use ASO is more from that mass balance component of, can we now serve all of our irrigation needs? Can we refill Don Pedro? And then after that point, okay, what do we have from a flood control perspective? How much water do we actually need to continue to move out of the reservoir? So that's where we set our, we set our releases here above our minimum flows at that time period, even though we were below our flood control space in that period, but we set it in order to slowly move that volume out, knowing that other systems in the San Joaquin had a large snowpack. So our idea is, let's try and move that volume now because we might not be able to move it in the future if there needs to be relief on the San Joaquin. As you continue moving forward, of course, it started raining again. So you move out of that, you have no choice, you are to max releases. And so that's where the component of these kind of mid flights here maybe don't have as much impact for our operations. We already knew you're at max channel. There's nothing more we can really do. What those help with is communications downstream. So that's where you have the sheriff asking, well, do you guys know what's going on? Can't you just reduce your releases? It's like, no, we have a product here that shows there's an entire Don Pedro sitting up above the reservoir, and we only have so much space. So that's where the usefulness of ASO in those time periods goes outside of operations and goes more to the public communications. And then as you keep moving through those periods, it helps you with those decisions of now we're shifting out of flood control. When can you make that decision of we're moving from flood control to now let's fill up the reservoir? What are the rates looking like? You don't want to fill your reservoir when there's still a lot of uncertainty in your full natural flow rates. There's a certain value you want to have coming in. You want your outflows to match your inflows at that period. We can't spill from Don Pedro, so that's where you give yourself that space. And then kind of finally writing out the year. Just to kind of give an idea from an economic perspective of the benefits, especially in this time period, having ASO to make decisions, we have a water first priority, right? So we have to really prove that those excess releases have to go down. In that case, we were able to save our ratepayers about $6 million through hydroelectric production during that time period, because we were ahead of all the other groups, because usually prices go down once everyone's flushed with water. So at that time period, we were ahead of the curve, able to save our ratepayers money when we were seeing extremely high gas prices for our purchase power and fuel. So that completes my talk. I want to thank you guys for having us here, and happy to take any questions.
Thanks, Olivia. That was great. Any questions? Comments? Random thoughts? Joe says thumbs up. Dr. Dozier? Molly, wing a microphone at him. Yeah.
Oh, gosh, what's going on? So what would it take to actually run your hydrologic model with the distributed data?
So if we were to do the direct insertion of ASO?
Into the hydrologic model, yeah.
Yeah, so we do it in a kind of, it's not the same way that iSnowball can do it. It's not as clean. So the way we would do it is creating a initial condition that matches really closely to it, and then you would run from there. So you can do that. It just becomes a headache overall when you're trying to keep track of what initial condition can I run from, which one has the right states for the snowpack, especially if there's multiple people who are trying to work on the same model, rather than that no matter which initial condition you run off of, you're going to produce similar results for the future time periods.
Okay.
Hopefully I answered your question. If not, it really is not as difficult to create initial condition. We find something in history and we have an adjuster where we can move things up and down. There's less desire as far as like full direct insertion of ASO data, possibly full insertion of the depths, but not the SWE.
Yeah, I'm guessing I'm thinking, like Jessica Lundquist has done a lot of work on the sort of variability of things like travel times and also in a mountainous watershed, because of the different sun angles that occurred during the day. The sort of generation of water is sort of spread out in a sort of space-time. That sounds like a buzzword, I'm sorry. Yeah. But I mean, one of the things we've always talked about is an era where distributed hydrologic models would show promise. And I think that's been true for the last 40 years, that someday they would show promise. And I'm wondering what your thoughts are in terms of the rest of your career, which will be long.
Yeah, I mean, I think overall we've been really happy with the way that HMAN's produced it. Like when it produces forecasts, it is on a land segment basis, so you are getting that full distribution of every single land segment, what it's producing as far as inputs to the system, and what the energy and mass balance is for those individual land segments throughout the watershed. I think there's a lot of interest on our side of how can we maybe start incorporating machine learning into the model? How would we see improvements on that side from those integrations? I think there's a lot of possibilities. I like to say right now we're in this like hydrology renaissance. There's a lot of new data. The processing power allows you to actually utilize that data. So I think there's going to be a lot of movement going forward, and especially now we are seeing that gap bridge between academia and operators, and so you're getting this application of research immediately rather than you have to wait 20 years and you see the research finally being applied.
Thanks, Olivia. All right, we have one more talk in this session, but Sean has graciously offered to kick off our modeling session tomorrow morning with that, which will allow us to proceed uphill